वेरी गुड मॉर्निंग बच्चा लोग. एम आई ऑडिबल? वेरी गुड मॉर्निंग. वेरी गुड मॉर्निंग. हाउ आर यू पापाला? वेरी गुड मॉर्निंग. एम आई ऑडिबल एवरीवन? प्लीज कंफर्म. So बच्चा लोग, I welcome you to today's session where we are discussing the marathon on for thermodynamics. So as you know, मैंने promise किया था that I'll be taking the complete, you can say, marathon on to thermodynamics in detail. So this is the session that I will be taking in detail for you बच्चा लोग. So are you ready for this session? Tell me. Are you ready for this session? Audible sir? Okay. So बच्चा लोग, this will be around 5 hours session and I'll try to cover up everything in detail. So यहाँ पे ये चीजें अभी connected नहीं है इसमें. Referee AC, you can say, and IC engine and power plant portion is not there in today's session, that I'll be taking separately in the marathon of, you can say, application of thermodynamics. In the application part of thermodynamics, I will be taking that session. So very good morning बच्चा लोग. यहाँ पे we will start with first of all what is thermodynamics. Okay, so thermodynamics is nothing but it is a combination of two words, that is your heat and power. Okay, so always remember that it is the conversion of heat into, you can say, any form of, you can say, usable energy. Very good morning Nitish. So it is the conversion of heat into any useful form of energy, that is known as thermodynamics. So it is the branch of science which deals with the energy interaction between the system and the surrounding and its effect onto the property of the system. Remember this, energy interaction between the system and surrounding. One by one we will be discussing what is system, what is surrounding. Okay, so it is a branch of science which deals with the energy interaction between the system and the surrounding and its effects onto the property of the system. So energy interaction आप लोगों को याद रखने हैं are always of two type. Sir, one is your heat interaction and second one is your work interaction, and in the complete subject we are focused on heat and work interaction only. In the complete, you can say, subject we are focused on to heat and work interaction only. Are you getting my point बच्चा लोग? So यहाँ पे अपन लोग बात करेंगे about the, you can say, basic terms related to the thermodynamics. तो सबसे पहले what is the, you can say, system? Sir, quantity of matter or region in space which is under study or investigation is known as the system. That means अगर मैंने कुछ एरिया को सिलेक्ट किया है for which I am doing the study, that is the quantity of matter is known as the closed system, मतलब fixed mass system. Open system, that is a specific region marked in the space which is under the study is known as the system. Remember this very well, quantity of matter or region in space which is under investigation is known as the system. Sir, anything which is outside the system is known as the surrounding. Anything outside the system is known as the surrounding. And boundary, वैसे I have shown with a required thickness, but boundary is not having any thickness. यहाँ पे just आप लोगों को समझाने के लिए मैंने boundary को thickness दी है. But always remember, boundary is the interface that is shared between the system and the surrounding. Mathematically, the thickness of the boundary is 0, hence it is having neither volume nor mass. Remember this very well, boundary is not having volume nor mass. And always remember, universe is the combination of system and surrounding. Everything I will provide you concisely. आप लोगों को PDF मिल जाएगा. Remember this very well, आप लोगों को ये PDF मिल जाएगा. Everything I am giving you in a very short and a simple way. Okay, so are you getting these terms बच्चा लोग? Tell me, ये चीजें समझ में आ रही है to all? ये चीजें समझ में आ रही है everyone? Very good. So I think this much is clear. आगे बढ़ते हैं. So basically there are two types of boundary. Boundaries can be real or imaginary. Boundaries can be rigid or flexible. So real boundary means the wall of the pipe. We have taken you can say liquid flowing through a pipe. तो आप लोगों के जो pipes के walls होते हैं, they can be considered to be the real boundary. And I'm marking some specific cross section, let's say cross section 1 cross section 2 for the analysis. So these cross sections will be called your, you can say, imaginary boundaries. These cross sections will be called your imaginary boundaries. Okay sir. Boundaries can also be rigid, that is fixed boundary, or flexible, that is movable boundary. So another word for rigid I can use is fixed boundary, And another word for flexible boundary that I can use is movable boundary. Okay, so as you can see that this is a rigid container. As you can see that, just give me a minute. As you can see that we have a, you can say, this rigid boundary. Now what is the rigid boundary? Means boundaries cannot change during the interaction of system and surrounding, and here the boundaries are movable like the boundary of the piston. Now here once again the cylinder boundary is rigid, but your piston boundary is movable according to the interaction between the system and surrounding. That is dependent on to the interaction between the system and the surrounding. Dependent on to the interaction between the system and the surrounding. Is this clear? So basically discussing the type of system. So there are three types of system. Sir, closed system, open system and isolated system. इस पे वापस आते हैं, पहले थोड़ा आगे पढ़ ले about what is open system first. Sir, the system in which both mass and energy interaction can take place is known as the open system. That means mass can also cross the system boundary and energy in the form of heat and work can also cross the system boundary. Okay, open systems are of two types. The first one is the steady state and second one is the unsteady state. What is steady state? Sir, the properties remain constant with time at a particular location. Steady state means property remains constant with time at a particular location. That means none of the property changes with time at a particular location. That means your mass flow rate, you can say, will be dm upon dt will be 0. Energy interaction d by dt will be 0. And second one is unsteady state, where dm upon dt is not 0. That means there is some change of, you can say, properties with time at a particular location. So this is the example for steady state and this is the example for unsteady state. Itna yaad rakhiye, unsteady state, none of the properties changes with time at a particular location. That is steady state, and at unsteady state properties changes with time at a particular location. Okay sir. Sir, kabhi kabhi open system ki jagah we are using the term control volume because mass is entering to the system, mass is leaving the system, but you can say that's why we have to mark certain region for our analysis and that region marked will be called control volume. आप लोगों को कोई भी doubt हो, you can ask me in between. So first of all, in the open system, your mass can cross the system boundary, your energy in the form of heat and work can also cross the system boundary. I hope the open system is clear with all. आप लोगों को दो तीन चीजें याद रखनी है इसके बारे में. Many a times in GATE and engineering services, they are asking you the example based question. What they are asking you? They are asking you the example based question. Okay sir. Second one is the closed system. Slowly करते हैं. Sir, mass interaction can't take place, but energy interaction can take place in the closed system. That means energy interaction in the form of heat and work. Now, basically, we will be having two types of boundary in case of, you can say, closed system discussion. The first one, let's discuss about the rigid boundary, and second one is about the movable boundary. तो याद रखिए, अगर आप लोगों का क्लोज सिस्टम है जिसमें you are having, you can say, all the boundaries as rigid boundary, तो यहां पे आप लोगों का displacement work done जो होगा zero होगा. Okay, a gas that is enclosed in the container, ऐसे questions आते हैं. In the numerical, they will not be directly giving you this, but they will be mentioning that there is a gas in a closed container, and for that case, your displacement work will be zero. And for that case, your displacement work will be zero. And this is the case of movable boundary. In case of movable boundary, our displacement work will not be zero. In case of movable boundaries, our displacement work will not be zero, but a piston cylinder assembly without the engine valves is also considered to be an example of closed system. अपन जब एयर स्टैंडर्ड एनालिसिस की बात करते हैं, तब व्हाट वी आर अज्यूमिंग दैट आप लोग एक ही एयर को वहां पे आप लोग कंप्रेस कर रहे हो, वापस हीट सप्लाई करके हीट अप कर रहे हो. सो दैट विल बी द केस. आर यू गेटिंग माय पॉइंट बच्चा लोग? सो रिमेंबर दिस, that for rigid boundaries, closed system with the rigid boundaries, the displacement work will be zero. In this case here, the displacement work will not be zero because we are having flexible or movable boundary. And the word that is used in place of closed system sometimes is also called control mass. Sir, what are the example of closed system? Sir, compression stroke and expansion stroke. Because उस समय पे in case of your 4-stroke IC engine, your inlet and exhaust valve both are closed. So compression and expansion stroke of a 4-stroke IC engine are considered to be the example of the closed system. Is this clear, bachcha log? So let's go on to the table. In closed system, mass interaction can't take place, but energy interaction can take place. Mass interaction can't take place, but energy interaction can take place. Okay, sir. Last one is the isolated system. Now, first of all, in the isolated system, neither mass nor energy interaction can take place. That means mass can also not cross the system boundary and energy can also not cross the system boundary in the form of heat and work. In the form of heat and work. Okay, sir. Sir, in the isolated system, energy transfer can't take place, but there can be energy transformation. That means here, there can be a reaction of, you can say, fuel, which will be giving us the combustion and we will be getting the byproduct as flue gases. So, wo ho sakta hai. Although, in the isolated system, heat transfer is totally zero. In case of isolated system, the heat transfer is totally zero. Mass transfer is also zero. Mass transfer is also zero and displacement work is also zero. So this is the case of, you can say, isolated system. This is the case of isolated system. Are you getting my point? Sir, heat transfer and work transfer both are zero and mass transfer is also zero. But when we talk about a term that is called insulated system, sir, insulated system means your heat transfer is zero. Interaction in the form of heat is zero. Interaction in the form of heat is zero. But due to the change in internal energy, yaad rakhiye, due to the change in internal energy, we can get the work transfer. So in case of insulated system, heat transfer cannot take place, but displacement work or work transfer in any form can take place. Are you getting my point? Heat transfer cannot take place, but work transfer can take place in case of the isolated system. Sorry, in case of insulated system. So you have to remember 2 points. Let me take a page and write this for you. Okay. In case of, you can say, isolated system. In case of isolated system, your heat transfer Q dot is equals to 0. Your work transfer is also equals to 0 and your mass flow rate is also equals to 0. Energy interaction in any form cannot take place. But when I talk about the insulated system में क्या होता है सर? हीट ट्रांसफर इज जीरो बिकॉज द सिस्टम इज कंप्लीटली इंसुलेटेड, बट वर्क ट्रांसफर इज नॉट इक्वल टू जीरो. वर्क ट्रांसफर may take place. Hello Guru, work transfer may take place. You can say what is the point, what is the point we are considering? Generally, insulated system is a hypothetical assumption for number of our ideal processes. For number of our ideal processes where we don't allow the heat transfer to take place, but we allow the displacement work to occur. When we will be discussing this in the case of constant volume, constant pressure, isothermal processes, this will be clear. Okay, this point will be clear, and here also the mass flow rate is zero. Okay, so these examples will be clear as we will be moving on to the, you can say, further on topics. The point is in case of our thermodynamic study, actually I'm not having the phone in the hand, so not able to read the chats. I'll be reading the chats now. Okay, so what is the case in our thermodynamic study? Generally we are, yes, like piston being insulated, you can also say that this is our, you can say, assumption for a process to be occurring, you can say, as per our hypothetical assumption also, you can say. Now the point is, you can say, many a times, what is the point? Many a times whenever you are talking about this in the thermodynamics, we are generally only focusing on to the energy interaction and mass interaction. Generally in our thermodynamics, we are focused on to the energy interaction. But in case of, you can say, this topic, we are not having at all, you can say, isolated system is not having energy interaction. That means we are not studying this in detail. Remember this, we are not studying the isolated system in detail. So यहाँ पे आप लोग देख सकते हैं, for the isolated system, mass transfer, energy transfer both can't take place. Just give me a minute. Mass transfer and energy transfer both can't take place. Mass transfer and energy transfer both can't take place. Is this clear? Okay, chaliye now. Moving ahead. I hope you are clear with the difference between the isolated system and insulated system. Now, discussing about the properties. Sir, what are the properties? Sir, characteristics of the system to which the numerical values can be assigned. Means your density, your mass, your volume. You can obviously assign a numerical value. Bole to density of water is 1000 kg per meter cube. Sir, mass I brought, you can say 2 kg of sugars. Next is what we are calculating, volume. Okay, but color को आप लोग न्यूमेरिकल वैल्यू असाइन नहीं कर सकते, so that is not the property of the system. So remember this, characteristic of the system to which a numerical value can be assigned is called the property of the system. और properties दो टाइप की होती है. The first one is the extensive property and second one is the intensive property. Remember this, the first one is the extensive property and second one is the intensive property. Sir, what are the extensive properties? The properties which depend upon the, you can say, extent or size or mass of the system. The properties which depend upon the extent, size or mass of the system are called your extensive property. मतलब वो mass पे depend करती है system की. I will give you a very good example. I will give you a very good example to understand the extensive properties and intensive property. Your mother is cooking, you can say, a very favorite dish of yours. Let's say any favorite dish of yours. That maybe as it is, we are having the, you can say, Sankranti day after tomorrow. So let's say your mother is making gajar ka halwa. I don't know the English word for that. So we'll take it gajar ka halwa and it is very hot. It is very hot. Inside that utensil, वो बर्तन के अंदर बहुत गर्म है. So आप लोगों ने थोड़ा हिस्सा अपनी प्लेट में लिया. You are taking some part of it in your plate. You are taking some part of it in the plate. What will be the temperature difference between the piece that is there in your plate and the total volume that is there in case of, you can say, the complete vessel? Will there be any temperature difference? Will there be any temperature difference? आप लोगों की प्लेट में जो है और उसमें है, उसमें will there be any temperature difference? Can you tell me? Will there be any temperature difference? Will there be any temperature difference? No. No. Okay, generally no. Bhumit is telling generally no. Okay, what about others? क्या वहां पे कोई temperature difference होगा? क्या वहां पे कोई temperature difference होगा everyone? Will there be any temperature difference? आप लोगों की प्लेट में जो गाजर का हलवा है, no, that's another thing, Guru. That's not the thing at present we are discussing. That's slightly another thing. You are taking a part of it. Very good morning, Jyoti. You are taking a part of it. That means temperature is not dependent on mass. Let's say you took 1/4 of what your mother had cooked. आप लोगों ने उस गाजर के हलवे का 1/4 ले लिया. You are taking 1/4. So generally there will be no major change in the temperature. So obviously temperature is not dependent onto the mass of the system, and that's why temperature is intensive property. Temperature is intensive property. The second example is volume. As you see, if I divide the container into number of parts, अगर मैं इस container को number of parts में divide करता हूँ, so the volume of the system will also get divided. That means extensive properties are additive in nature. Sir, what is the meaning of additive in nature? What is the meaning of additive in nature? To find out the complete value, आप लोगों को उसके हर part को add करना पड़ेगा. You will have to add the complete, you can say, proportion of all the parts. Is this clear? The property which depends upon the extent or size of the system is called extensive property. Am I audible now? Actually, I was silencing the phone. Okay, I think I'm audible. Actually, there was a call, na, so I was cancelling out that call, so I had silent the phone. Okay, I think I'm audible. Actually, there was a call, na, so I was cancelling out. Okay, now everything is fine. So, what are extensive properties? Sir, the properties which does not depend. याद कैसे रखने का? How to remember this? Sir, intensive properties start with IN. Intensive properties start with IN and independent word also start with IN. An independent word also start with IN. Sir, it is the properties, these are the property which does not depend upon the extent, size or mass of the system. As I told you, temperature. As I give you a very beautiful example, temperature. Intensive properties are not additive in nature. Always remember, intensive properties are not additive in nature. Sir, ratios of two extensive property is an intensive property. Example, density. Sir, density is equals to mass per unit volume. Mass is an extensive property. Volume is an extensive property and density that we are getting is an intensive property. Ratio of two extensive property is an intensive property. Is this clear? Ratio of two extensive property is an intensive property. Sir, specific properties are nothing but extensive property, not intensive. This will be extensive. Extensive properties per unit mass. Specific properties are extensive properties per unit mass. Let's say if I am telling specific volume, अब specific word आया, so obviously it is intensive. अगर specific word आया, so obviously it is intensive. Let's say volume per unit mass. Now volume is an extensive property, mass is also an extensive property, but any extensive property divided by mass will always give you specific intensive properties. याद रहेगा, they will give you specific properties that will be intensive. Some very beautiful engineering services question like electrical charge. Sir, electrical charge is the, you can say, Q is equals to N into the charge of an electron, where N is the number of electrons. That means once again it is dependent on to the size of the system. Number of electrons, एक system में कितने electrons है? So always remember, electrical charge is also an extensive property. Electrical charge is also an extensive property. Magnetization, you know, मुझे अच्छे से याद है, when I was in school ना, I think in 6th or 7th science, maybe in 8th 9th also, I don't remember the exact year, our teacher used to tell that all of the, you can say, materials are having the dipoles, but the arrangement of the, you can say, dipoles makes the magnetization property of say, some materials. Arrangement of dipoles, that means directional arrangement. So number of dipoles present are the indication of the magnetization. So once again, sir, number that is dependent on to the size. So this is also an extensive property. So this is also an extensive property. Chemical potential, that is coming in chemical engineering. And Cp and Cv, our value of, you can say, specific heat at constant pressure, specific heat at constant volume is an example of intensive property. So you have to remember, these three have already come in the examination, already came in the exam. Remember this, bacha, I have given you the example also. These things have already come in the examination. Is this clear, everyone? I hope you are enjoying the thermodynamics with me. I promise you, today we will have the session of 5+ hours and we will complete the thermodynamics. We will complete the thermodynamics. Is this clear? We will complete the thermodynamics. Chaliye. Now, approach of thermodynamics. Approach of thermodynamics. Sir, basically there are two types of approach. The first one is the molecular approach and second one is the average approach. Sir, molecular approach means microscopic approach. We are going at a microscopic level and macroscopic level means ऊपर से करना and overall study. I am not going into the detail. It is an overall study. Are you getting my point? We are not going into the detail. This is called the overall study. So let's discuss in short what is microscopic approach and what is macroscopic approach. Sir, microscopic approach, that means we will be considering one by one the behavior of the individual molecules. One by one the behavior of individual molecules, and that's why it will be a time consuming approach and we can actually not predict the behavior. So to predict the behavior we will have to apply the statistical thermodynamics because we are not having any tool to understand properly the microscopic behavior of everything. तो वहां पे अपने को क्या लगाना पड़ेगा? Statistics and probability. Okay, statistical tools we will have to apply, and that's why microscopic approach is also called the statistical thermodynamics. Microscopic approach is also called the statistical thermodynamics. Is this clear? Okay, sir. Sir, what is macroscopic approach? Sir, it is based on to the average behavior. It is based on to the average behavior. Average behavior means I will be considering if there are 100 molecules, I'll take the average behavior of the molecules in total. Like what? Sir, pressure. Now, how do we measure the pressure? We don't, and you can say measure the individual value of force acting on every molecule. We don't measure the indication of, you can say, force acting onto the every molecule, but we measure the pressure of the complete system as a whole. We measure the pressure of complete system as a whole. So this is a less time consuming approach, and this type of approach in which the statistical tools are not required is called classical thermodynamics. And bacha log, to be honest, in our analysis, our classical thermodynamics is surely competing very properly with the statistical thermodynamics. अपने को जो area मिलता है of results is matching with the actual statistical thermodynamics also. Yes, pressure and temperature, they are not based on to the molecular study. They are not based on to the molecular study at the grassroots level. I hope you are getting this. Okay, so that's why it is called classical thermodynamics also. Sometimes in the interviews they might ask you that what thermodynamics are you studying? So bacha, we are studying classical thermodynamics and not statistical. We are studying classical thermodynamics, not statistical. Okay, so whatever we are studying, this is a part of classical thermodynamics. Okay, sir. Sir, what is a state? Sir, state refers to the condition of the system as described by its property. The properties define a state. बोले तो we are having any condition where the piston cylinder assembly is there and air is at a pressure of 3 bar and volume of 0.5 meter cube. Okay, sir. Sir, I am supplying the heat. Anyways, I am supplying the heat. So as I will be supplying the heat, obviously the piston will be moving up, and let's say the pressure is decreasing. As the piston is moving up, the pressure is decreasing up to 1.5 bar and volume increases up to 2 meter cube. Now, this can be called the first state of the air, and this can be called the second state. So always remember, for a given state, properties are having fixed value. एक स्टेट पे प्रॉपर्टीज हमेशा फिक्स्ड होती है. अगर प्रॉपर्टीज चेंज हो गई तो स्टेट चेंज हो जाएगा. इफ द प्रॉपर्टीज चेंजेस, द स्टेट चेंजेस. सो रिमेंबर दिस, स्टेट रिफर टू द कंडीशन ऑफ द सिस्टम दैट इज डिस्क्राइब्ड बाय इट्स प्रॉपर्टी. State refers to the condition of the system that is described by its property. If the property changes, the state will change. Is this clear, everyone? Chali. Now, next thing is, a process is said to have occurred if the system moves from one equilibrium state to another equilibrium state. You know, the point is when we are talking about constant pressure process, we are focusing on to the initial state and final state only. I'll tell you what is the constant pressure process. So remember this, a process is said to have occurred if the system moves from one equilibrium state to another equilibrium state. Okay, sir, we'll discuss this slowly in detail. Just now go with the definition. So basically there are two types of process. Now this is going very interesting now. This is going very interesting. So basically there are two types of process. The first one is called the non-quasi-static process, and the second one is called the quasi-static process. The first one is called the non-quasi-static process and second one is called the quasi-static process. The first one is called the non-quasi-static process and second one is called the quasi-static process. Okay, sir. Sir, what is first of all a non-quasi-static process? Okay, let's say I'm having a piston cylinder assembly and I'm having any gas. मेरे पास कोई gas है which is at pressure of 3 bar and volume of 1 meter cube, and there is a dead weight kept over the piston. There is a dead weight kept over the piston. There is a dead weight kept over the piston. Understand this very well. There is a dead weight kept over the piston. There is a dead weight kept over the piston. Okay. Now let's say I'm suddenly removing the dead weight. I'm suddenly removing the dead weight. So what will be the case? This gas will try to come in equilibrium with the surrounding. ये gas equilibrium पे आने की कोशिश करेगी, and that's why as the pressure balance, atmospheric pressure कम हो जाएगा, atmospheric pressure will be less as compared to the inside pressure. The piston will be moving upward. The piston will be moving upward very rapidly. Understand the feel, the piston will move up very rapidly. But as it will move very rapidly, what will be the case? There will be lesser pressure in the molecules that are very near to the piston. there will be less pressure in the molecules that are very near to the piston, but the molecules that are far from the piston still will not experience the change of pressure suddenly. And slowly they will be taking a time to have the, you can say, pressure uniformity throughout. That means I can say that as pressure is an intensive property, in a rapid process intensive properties are non-uniform. In the rapid process intensive properties are non-uniform, and such process in which the intensive properties are non-uniform throughout the system is known as non-quasi-static process. That means non-quasi-static process is a rapid process. That means non-quasi-static process is a rapid process. Is this clear, bacha log? So non-quasi-static process is a rapid process in which the intensive properties are non-uniform throughout the system. Remember this, intensive properties are non-uniform throughout the system. Non-quasi-static process on the graph is always represented by dashed lines. That means the dotted lines. Dotted lines don't have enough time to evenly distribute. Yes. Okay, so whenever you see dotted lines onto the graph, that is indication that you are not able to achieve the equilibrium state. You are only having the initial state and final state, but your intermediate stages are not in equilibrium. And that's why non-quasi-static process do not have a well-defined path of a process. Non-quasi-static processes do not have a well-defined path of the process. Is this clear, everyone? Non-quasi-static process do not have a well-defined path of the process. Very clear, sir? Okay, so I hope the first example of non-quasi-static process is clear. You can say rapid process in which the intensive properties are non-uniform throughout the system. Okay, sir. Second process is, let's understand, instead of putting a single dead weight, I'm putting number of, you can say, small thickness weights. I'm putting infinite number of very small thickness weight. You can say very thin layer of weight I am putting, and during this process, once again it is at a pressure, you can say 3 bar, volume 1.5 meter cube. I am removing this dead weights one by one, layer by layer, slowly. Sometimes in some of the book you can also understand this as an example of rice bag, where you will be removing grain by grain. So as you will be removing this, you can say slowly the piston will rise up, but the piston will rise slowly, and it will take infinite number of time to reach to the top. Slowly, and due to the slow process, the pressure will have enough time to uniformly distribute throughout the system. And that's why a very slow process, you can say, approximated by removal of dead weight layer by layer or removal of rice grains one by one, can be considered to be an example of, you can say, quasi-static process. A very slow process in which the intensive properties are uniform throughout. You know why I'm focusing on this? Many a times they are asking you statement based question like quasi-static process is a rapid process. True or false? Non-quasi-static process is a very slow process. And you should be clear with the basics. So it is an infinitely slow process in which the intensive properties are uniform throughout the system. Quasi-static process on the graph is always represented by the solid lines that indicate the achievement of the equilibrium state. We always feel as the system is having enough time to get in equilibrium with the surrounding. So series of equilibrium state through which the system passes is known as the path of the process. I hope this is pretty clear. Okay, I hope everyone will be clear with the quasi-static and non-quasi-static process. Now, thermodynamic equilibrium. Sir, a system is said to be in thermodynamic equilibrium if it is in thermal equilibrium. That means equality of temperature. That means the temperature should be equal throughout the system. Mechanical equilibrium, that means there should be no unbalanced forces, or else the pressure should be same throughout the system. And third one is the chemical equilibrium, equality of chemical potential, or you can say that in easy words, no chemical reaction should take place. inside our system. So this is an example of thermodynamic equilibrium. So thermodynamic equilibrium is a combination of thermal, mechanical and chemical equilibrium. Yes or no, bachcha log? Thermodynamic equilibrium is an example of combination of, you can say, thermal, mechanical and chemical equilibrium. I will provide you this PDF also. Bachcha log, those who are watching the class, I will give you the way to download this PDF also. Very sure I will be giving you this PDF. It is already ready. Okay, now let's discuss about the properties. Now let's discuss about some key points related to the properties. Sir, properties are exact differential. Exact differential bole to we can write this. Can you see this? Exact differential means you can write this very easily, that the change of volume for a given process, the change of volume for a given process is V2 minus V1. The change of volume for a given process, whether it is passing from the path 1A2, whether it is passing from path 1B2, or whether it is passing from the path 1C2, the change of volume will be same. The change of volume will be same, and that's why remember this, that properties of the system are exact differential or the point function. Okay, I'm not going into the detailed discussion onto this. These all things I've explained in the my courses, but at present I'm giving you the final conclusion that properties are exact differential and they are also known as point function. Remember this, they are also known as the point function. Yes, path independent. And properties are point function or state function. Generally they will ask you in interview. The properties are actually first of all called the state function. Remember this very well. The properties are called state function, and the states, this is state 1, this is state 2. State is represented by a point onto any of our thermodynamic diagram. That's why state functions are also known as point functions. That's why state functions are also known as point function. Is this clear? Be very specific with your words for the ISRO interview, BARC interviews. Otherwise you will miss a very good rank. Okay, moving ahead to another classification of process. We have already discussed the non-quasi-static and quasi-static process, and now we will be jumping onto the internally reversible and externally reversible process. Now we will be jumping onto the internally reversible and externally reversible process. Sir, a reversible process is a process that can be reversed, means you can come back to the initial state without leaving any trace onto the surrounding. You can come back to the initial state without leaving any trace onto the surrounding. So always remember that in a reversible process, it is possible only if the net heat and work exchange between the system and the surrounding is zero. That means net heat transfer, net work transfer for a reversible process will be zero for the combined forward and reverse process. Okay, so basically reversible processes are of two. Am I audible now? Am I audible now? Okay, is my voice clear? Okay. I had to mute the. Actually, no one will call you any day, but when you are having the marathon, na, everyone will call you. Happens with me. Okay, so we'll discuss this. What is quasi-equilibrium, compression and expansion? What is heat transfer through a infinitesimal temperature difference? Now, these are very, you can say, bhari words. We'll discuss them easily. First of all, internally reversible process. Internally reversible process. A process is said to be internally reversible process if no irreversibility occurs inside the boundary of the system. A process is said to be internally reversible if no irreversibility occurs inside the boundary of the system. Inside the boundary of the system. Okay, sir. Now the point is always remember, in this case you can say frictionless quasi-static process. Frictionless quasi-static process is always an example of internally reversible process. Frictionless quasi-static process is always an example of internally reversible process. At every intermediate state of an internally reversible process, all the properties are uniform throughout. That is, the closed system passes through the series of equilibrium state. That is, the closed system passes through the series of equilibrium state. So you have to remember The example of, you can say, internally reversible processor. What are the examples? Sir, first of all, Cauchy equilibrium compression or expansion. Cauchy equilibrium compression or expansion is an example of, you can say, internally reversible process, and phase change process can be considered to be internally reversible. Total phase change process. Is this clear, everyone? That means there should be no, you can say, reversibility inside the boundary of the system. No irreversibility inside the boundary of the system. A process is said to be externally reversible if no irreversibility occurs. If no irreversibility occurs outside the boundary of the system. If no irreversibility occurs outside the boundary of the system. Sir, examples are, always remember, heat transfer through negligible temperature difference. The point is, in our Carnot cycle, what we are having, that the source temperature and the temperature of the system are nearly very same. There is no major difference between the source temperature and your, you can say, system temperature. That means the heat transfer is taking place at negligible temperature difference in case of Carnot cycle. In case of Carnot cycle, in case of generally all the reversible cycle, the heat transfers are taking place at negligible temperature difference. But when you talk about Otto cycle, diesel cycle, the system temperature is comparatively, you can say, changing with respect to your source and sink temperatures. That means there is a change. You see, Otto cycle, diesel cycle, the system temperature is high as compared to the sink temperature, and that's why there is a finite temperature difference. And when there is finite temperature difference, then it is called externally irreversible. Whenever there is a finite temperature difference, it is called externally irreversible. But whenever there is a negligible temperature difference, then it is called externally reversible. Is this clear? That's why Carnot cycle is called totally reversible cycle, but Otto cycle, diesel cycles are internally reversible and externally irreversible. Internally reversible and externally irreversible. Is this clear, everyone? I hope this condition is pretty clear with you. Yes or no? Okay, chaliye. So what are the key points to remember? Sir, frictionless quasi-static process is an example of internally reversible process, and heat transfer through negligible temperature difference is an example of externally reversible process. A totally reversible process will be the one which will be internally reversible plus externally reversible. Totally reversible process will be internally reversible plus externally reversible. Is this clear? Okay. Now these are the details, not important at present. Okay, what are the causes of irreversibility? Remember this, sir. Friction, unrestrained expansion of, you can say, unrestrained means, you can say, unstopped expansion. Mixing of gases is also irreversible. Heat transfer through finite temperature difference. Electrical resistance, heat is a low grade energy, na? What is the point? Heat is a low grade energy. Whenever heat transfer will be taking place, there will be loss of some heat, and that's why when the heat transfer is taking place across the finite temperature difference, you cannot reverse the process, because some of the heat will be lost to the surrounding. Some of the heat will be lost to the surrounding. So this is the example that heat transfer across the finite temperature difference is also called, you can say, an irreversible process. Electrical resistance, this is also irreversible. Inelastic deformation of solid, that means plastic deformation of solids. Chemical reactions generally are irreversible. Hysteresis or magnetic losses are also irreversible. So these are the examples. I've given you what is required for the topic. Okay. Cyclic process. Sir, if a system undergoes number of process such that the initial and final state are same, then such process is called the cyclic process. And cyclic processes are used to get the continuous effect, continuous heat transfer, continuous work transfer. So we are using the cyclic processes for continuous heat transfer, continuous work transfer. Okay, sir. Now a classification of system based on to their phases: a homogeneous system and a heterogeneous system. Sometimes the question has been asked from this also. Homogeneous thermodynamic system is defined as one whose chemical composition and physical properties are same in all parts of system. That means it is chemically congruent. It is chemically congruent. In the pure substance, we'll be discussing about this in detail also. So a system generally which is in single phase is termed to be, you can say, homogeneous system. A system which is in single phase is generally termed to be the homogeneous system. Sir, mixture of air and water vapor, water plus nitric acid, mixture of air and water vapor, water plus nitric acid is an example of homogeneous system. Is an example of homogeneous system. Is this clear? चलिए, heterogeneous system, sir, it is defined or deemed as, you can say, consisting of two or more homogeneous body. Water plus oil. Now water is homogeneous with itself, oil is homogeneous with itself. So when you are mixing the two, the two homogeneous bodies make heterogeneous system, and these two different homogeneous bodies generally can be defined to be phases. General cases can be defined to be phases. So sometimes the heterogeneous system is also known as the multi-phase system. Multiverse नहीं, Avenger से बाहर निकलो, it is multi-phase system. A system that consists of two or more phases in general is called heterogeneous system. Water plus steam, ice plus water, and all. Is this clear? चलिए. Now I'll tell you a story. एक कहानी सुनाऊंगा. I will tell you a story. How did we get universal gas constant? How did we get? Yes, immiscible one. Yes, you can say that generally immiscible one. That's why I took the example, Guru, of water and oil. That's why I took an example of water and oil. Now this is very interesting, because from this I will be defining the compressibility factor for you, that how did we get universal gas constant. So let's say for air, for, you can say, different states at a constant temperature, you are measuring pressure, volume, and ratio of PV upon NT. For different states of, you can say, the piston positions, let's say at state AA, state BB, state CC, you are measuring this, and you are plotting this over here at a constant temperature. वापिस से you will change the temperature, you will change the condition, and you will plot this. So when you are plotting this graph at temperature T1, you are plotting a graph of PV upon NT versus pressure. Okay, we are plotting the graph of PV upon NT versus pressure. So let's say these are the results of different state at constant temperature T1. So results of different state at constant temperature T2, results of different state at constant temperature T3. Results of different state at constant temperature T1, T2, and T3. This one is for air. Okay. So what I did, I tried to, you can say, join the lines to the PV upon NT axis. I tried to extend the line. मैंने कोशिश करी कि मैं lines को extend करूं. And what I found as I was extending the lines are generally meeting at one point. Okay, sir. Sir, then I called Guru and I asked him that please perform the same experiment on nitrogen. Calculate the pressure, the volume, the PV upon NT for the different states at temperature T1, for the different states at temperature T2, for the different states at temperature T3. So what did Guru did? Guru plotted the graph and came to me. Sir, I got this graph. Can you see, sir, I got this graph. And I was like, okay, Guru, did you copy my work? Because our graph is same. My graph of the analysis on air and Guru's graph of analysis on nitrogen is same. When we were performing this experiment, I got to know one thing, that for all the gases, if you plot the, you can say, values of PV upon NT for, you can say, given temperatures, they will be converging to a common point only. Yes, they will be converging to the common point, and that common point on the PV upon NT is a constant for all gases. For any gas, you will get the same value, which is called your universal gas constant R bar. Chalo, I called Nitish and I told him, do for helium. He told, sir, I'll do for helium, don't worry. And when Nitish did this experiment for helium, he brought the same graph. And that's why it was confirmed that this is nothing but universal gas constant, 8.314 kilojoule per kilomole Kelvin. I am not going on to the detailed discussion of this experiment. This much is enough. 8.314 kilojoule per kilomole Kelvin. 8.314 kilojoule per kilomole Kelvin. Is this clear, everyone? So for all the gases, now understand this. What is your, you can say, universal gas constant? Sir, universal gas constant is a constant on PV upon NT versus pressure diagram. PV upon NT versus pressure diagram, and mathematically, just a minute, you can represent this, and mathematically you can represent the universal gas constant at limit P tends to 0. Have you observed this? The pressure was 0. Where the pressure was tending towards 0, sir, limit P tends to 0, PV upon NT, limit P tends to 0 on PV upon NT axis is given by R bar. Yes, you know, okay. You see this, the pressure is tending to 0. Sir, pressure tending to 0 onto PV versus NT diagram. Pressure tending to 0 onto PV versus NT diagram. So if they are asking you the mathematical representations, generally in the ISRO interviews, they will ask you that what is the mathematical representation of the universal gas constant. Sir, limit P tends to 0 on PV upon NT axis will be given by, you can say limit P tends to 0, PV upon NT is nothing but R bar. And value you know that very well, 8.314 kilojoule per kilomole Kelvin. Now two important points. Sir, what are reduced properties? Sir, properties at a given state divided by the property at the critical point. Property at a given state divided by the same property at the critical point is known as reduced property. Property at a given state divided by the property at the critical point is called the reduced property. Reduced property is a dimensionless parameter, and at the critical point the reduced properties are always equals to 1. At the critical point the reduced properties are always equals to 1. Is this clear? At the critical point the reduced properties are always equals to 1. Okay, sir. Sir, next is compressibility factor. Compressibility factor, Z is very, very important. What I did, I got to know that mathematically the compressibility factor is defined as the ratio of PV upon NT upon R bar. PV upon NT upon R bar. Remember this, it is defined as PV upon NT upon R bar. Upon NT divided by R bar is nothing but compressibility factor. Not going on to this detail, just leave these details at present. Okay, so always remember, whenever the pressure is tending to 0, your compressibility factor Z will be equals to 1 because PV upon NT will be equals to R bar. Okay, remember these two things. Whenever the pressure is tending to 0, your compressibility factor Z will be equals to 1. Okay, sir. Okay, sir. Now, this is your generalized compressibility chart. What does Z tell us? I'm coming on to that only. Don't worry, Guru, I'm coming on to that only. This is your generalized compressibility chart. Okay, let's say this is for air. This is for air. Okay, this is for air. We are plotting this for air. So we are plotting, you can say this graph of, you can say Z, that is your compressibility factor, that is nothing but PV upon NT divided by R bar versus the reduced pressure. PV upon NT divided by R bar versus the reduced pressure. So first of all, you are plotting the line of reduced temperature TR equals to 1. So this is the line of reduced temperature TR equals to 1. Sir, this is the line of reduced temperature TR is equals to 1.1. This is of 1.2. Sir, 1.3, 1.5 and 2. 1.1, 1.2, 1.3 and 2. Sir, what is the meaning of this? Sir, what is the meaning of this? That reduced temperature TR is equals to 1, reduced temperature TR is equals to 1.1. We are plotting the, you can say, corresponding pressures, and at reduced temperature TR is equals to 2, we are getting a near straight line, and this is, you can say, up to the reduced pressure of 4 bar. This is up to the reduced pressure of 4 bar. Now this is for air. This is for air. Okay, this is for air. This is experimentally plotted graph. This is for air. Understand this very well. This is for air. Now let's say we are plotting this for another gases also. We are plotting this for another gases also. Now, as Guru was asking, sir, what is the physical significance of the value of Z? So let's say if we are knowing only the critical properties of any gases. So when I plot for any other gas like nitrogen, helium or any other gas, I will be getting a similar compressibility chart only. Beyond 4, it is, you can say, a radical change. So we are not focused on to that. Generally, you can say reduced pressure 4 times. This is not 4 bar. I'm sorry, I'm telling this 4 bar. This is not 4 bar. Sorry, because this is reduced pressure. This is 4 times the corresponding pressure. This is unitless quantity. I take my words back. ये 4 bar नहीं हो सकता. This is 4 times the corresponding quantity. So generally, all the applications are not going beyond 4 times the pressure. So the changes are not very important. The changes are not very important. This is reduced pressure, na? So the point is, if you plot this for any other gases, you will be getting a similar generalized compressibility chart, whether you plot it for helium, whether you plot it for, you can say, nitrogen. So whenever you are knowing only the critical properties of any gases, whenever you are knowing the critical properties of any gases like critical pressure, critical temperature only, so you can calculate the different, you can say, property changes using this generalized compressibility chart, comparing it with the standard values, because this graph is same for air, this graph is same for nitrogen, this graph is same for all other, you can say, gases. So using the generalized compressibility chart, you can calculate the different behavior of gases and when the critical properties are known. Are you getting my point? You can calculate the, you can say, general properties of gases when the critical properties are known. Is this clear? This is the physical significance. This is the physical significance. Now, using the generalized compressibility chart, there are 2 to 3 points that I want to give you. Sir, when the reduced temperature is 1, reduced pressure is 1, the value of Z is minimum. Remember, the value of Z is minimum at, you can say, the critical point. When is the reduced temperature 1? When is the reduced pressure 1? Sir, it is at the critical point. So remember this, the value of Z, that is the compressibility factor Z, is minimum at the critical point. The value of the compressibility factor Z is minimum at the critical point. Are you getting this, everyone? The value of the compressibility factor Z is minimum at the critical point. Okay, sir. Sir, whenever the reduced pressure tends to 0, whenever the reduced pressure tends to 0, your compressibility factor Z is equals to 1. I will be using this only. Just remember 3 points from this graph. Nothing to worry about this graph at present. Whenever the reduced pressure tends to 0, your compressibility factor Z is equals to 1. Second thing is, whenever your reduced temperature is greater than or equals to 2, whenever your reduced temperature is greater than or equals to 2, that is equals to 2, and at greater than or equals to 2, your compressibility factor Z will be 1. At greater than or equals to 2, your compressibility factor Z will be equals to 1. So there are 3 important points. सुन लो अच्छे से. One thing, the value of Z compressibility factor is minimum at the critical point. That is when your reduced temperature and reduced pressure are equals to 1. Is this clear? Reduced temperature and reduced pressure are equals to 1. Secondly, when the reduced pressure is tending to 0, the compressibility factor Z is equals to 1. When the reduced pressure is tending to 0, the compressibility factor Z is equals to 1. When your reduced temperature TR is greater than or equals to 2, then also your compressibility factor Z is equals to 1. Then also your compressibility factor Z is equals to 1. Are you getting my point, bachcha log? These are the 3 points only that you need to remember from this. Okay, sir. Sir, now what are ideal gases? Sir, real gas can be any gas for which your compressibility factor Z can be less than 1, your compressibility factor Z can be equals to 1, your compressibility factor Z can be greater than 1. But for ideal gas, the compressibility factor Z is always equals to 1. For the ideal gases, your compressibility factor Z is always equals to 1. So what are the physical differences between the real gases and ideal gases? Sir, first of all, what is the meaning of compressibility factor Z is equals to 1? One thing is, sir, Z will be 1 when your reduced pressure is 0. Reduced pressure is 0, bole to P upon PC, that is the pressure upon the critical pressure is 0. And when can this condition be possible? When your pressure is very low compared to the critical pressure. Bole to your pressure is very low compared to the critical pressure. So that condition will be called, at low pressure we are having ideal gases. At a very low pressure, the real gases can be idealized to be ideal gases. Are you getting my point? At very low pressure. Okay, sir. Sir, second condition is when the reduced temperature is greater than or equals to 2. When the reduced temperature is greater than or equals to 2, that means your T upon Tc is greater than or equals to 2. That means your T upon Tc is greater than or equals to 2. That means your corresponding temperature is 2 times high than the critical temperature. Yeah, critical temperature for water is around 220 degrees centigrade. I'll tell you that later on. So at very high temperature, the real gases are assumed to be behaving as an ideal gas. Is this clear? Is this clear, everyone? So at very low pressure and very high temperature, we are assuming the behavior of gases to be as equals to ideal gases. That means at very low density. Now this is the compressibility factor Z. Let's read the points. Any real gas having Z as 1 behaves in an ideal gas. As the values of Z deviate from 1, more is the deviation from the ideal gas behavior. Minimum value of Z occurs at the critical point. Okay, sir, this is clear. I hope everyone, those who are there, I hope you are enjoying the session. बोलिए बच्चे लोग, आई होप यू आर एंजॉयिंग द सेशन. एक बार भाई शेयर कर दो सेशन को थोड़ा. ओके, very good those who are there. We will be taking a break at around 1:30. Yeah? We will take a lunch break at around 1:30. Till then we'll go very smoothly. I hope it is fine. I hope it is very fine. We will be taking a break at 1:30. 1:30 or 1:45 we'll be having a lunch break of around half an hour. Okay, around half an hour we'll be taking the lunch break. Okay, sir. Sir, what is the physical meaning of ideal gas? What is the physical meaning of ideal gas? Sir, there are two things that are defining the ideal gas. Sir, negligible intermolecular force of attraction. Now, what is the meaning of low pressure and higher temperature? Sir, the molecules will be very far apart. The molecules will be very far apart. Okay, so negligible intermolecular force of attraction is the first characteristic of ideal gas. Second thing is, sir, volume of the gas molecules is negligible as compared to the container volume. This is not, you can say R should not be there. Volume of the gas molecule should be negligible as compared to the container volume. Is this clear? Volume of the gas molecules is negligible as compared to the container volume. So these are the two characteristics that defines the behavior of the ideal gases. Negligible intermolecular force of attraction and volume of gas molecules is negligible as compared to the container volume. So now when you go for the interviews, sir, don't tell ideal gas is the one which follows the ideal gas equation, PV is equals to MRT. वो definition पुराना हो गया. Now you are engineer, you should know this onto the basis of the compressibility factor Z in the terms of reduced pressure, in the terms of reduced temperature. I hope this is pretty clear. Now ideal gas equation. Sir, when Z is equals to 1, that means PV upon NT upon R bar is equals to 1. PV upon NT upon R bar is equals to 1. That means PV is equals to NR bar T. So this is your first ideal gas equation. Is this clear? And we know that very well. That number of molecules N, we have defined this over here only. Number of molecules N is equals to mass upon molar mass. Number of moles, not molecules, I'm very sorry. Number of moles is equals to mass upon molar mass. Always remember it is given by mass upon molar mass, M upon capital M. So I can put this over here. This will be given by, you can say for place of N, in the place of N, I can write this as mass upon molar mass. Now, what will be the case? Sir, R bar upon M, that is the universal gas constant divided by molar mass is giving us the characteristic gas constant R. So this is your second equation. This one is your first equation. PV is equals to NR bar T. This is your favorite one. PV is equals to MRT, and R, that is your characteristic gas constant, is given by R bar upon M. So what is the unit of universal gas constant, sir? 8.314 kilojoule per kilomole Kelvin. 8.314 kilojoule per kilomole Kelvin. But what is the unit of characteristic gas constant R? Sir, kilojoule per kg Kelvin. Kilojoule per kg Kelvin. And for all the gases, remember this, it is dependent on to the molar mass. The gas which is having the minimum molar mass will be having the higher value of R. The gases which will be having minimum molar mass will be having the higher value of your characteristic gas constant. Is this clear, bachalo? So you can calculate this for the different gases very easily. Okay, you will have to check the characteristic gas constant for air. You will have to check the characteristic gas constant for air. This is your homework. I think you know that very well. So that's your homework. Let's see, you will do that. I don't know at present. Okay, chaliye. Moving ahead on to the ideal gas equation. PV is equals to MRT. Sir, Just a minute. PV is equals to MRT. जग रहे हो सब लोग, सो रहे हो? Now, when we allow the mass to come to the left hand side, we are getting one equation, that is your P into specific volume upon RT. This is one useful equation. Many times we are using this P into specific volume is equals to RT. That is the molar mass of air, and when you allow the volume to go to the right hand side, we are getting P is equals to rho RT. Very helpful for the open system analysis. Very helpful for the open system analysis. So these are the different forms of ideal gas equation. I hope this is clear. I hope this is clear, bacha log. Tell me, is this clear, everyone? Now, van der Waals equation of state. Van der Waals equation of state. Van der Waals equation of state. Sir, P plus A by V square into V minus B is equals to RT. Sir, what is this constant A by V square and V minus B? So in this case, A by V square, this accounts for the intermolecular force of attraction. Remember this, this accounts for the intermolecular force of attraction. This accounts for the intermolecular force of attraction, and this value, you can say constant B, accounts for the gas molecules. This accounts for the volume of the gas molecules as compared to the container volume. Sir, what were the two assumptions? Sir, for the characteristic of ideal gas equation, sir, negligible intermolecular force of attraction. Negligible intermolecular force of attraction and volume of the gas molecules is negligible as compared to the container volume. So when we want to remove this characteristics, we get the real gas. So always remember, first of all, van der Waals equation of state is valid for real gases where we are having the, you can say, behavior of intermolecular force of attraction, and we are assuming that there is a volume of gas and it is, you can say, accountable as compared to the container volume. Is this point clear, bacha? Accounts for the intermolecular force of attraction and accounts for the volume of the gas molecules. Okay, sir. Sir, one thing is pretty clear. If your both the constants become zero, what we are getting? Sir, we are getting our favorite ideal gas equation. Remember this, we are getting our favorite ideal gas equation. We are getting our favorite ideal gas equation. Is this point pretty clear? Those who are there in the class. Now, very interesting point. What are the units of A and B? What are the units of A and B? Constants of van der Waals equation of state. Many times they are asking in your XC paper, in your mechanical paper. Okay, and most of the students are not remembering them. So one thing you can do, you know that very well, whenever mathematically any property is there in the brackets, their units should be comparatively same. They can be equated with the 0, and from this I got to know that the unit of B is given by meter cube per kg. The unit of V, that is specific volume, is equals to the unit of the constant B. So this is meter cube per kg. In the dimensionless form, it can be written as m minus 1 L cube. M minus 1 L cube. Is this clear? M minus 1 L cube. Similarly, the unit of A, you will compare P plus A by V square with respect to 0, and the unit of A will come out to be, you can say, meter raised to the power 5 upon kg second square. Meter raised to the power 5 upon kg second square. मेरे साथ बोलेंगे meter raised to the power 5 upon kg second square. So the dimensionless form will be A m raised to the power minus 1 L5t minus 2, m raised to the power minus 1 L5t minus 2. Is this clear, everyone? M raised to the power minus 1 L5t raised to the power minus 2. Meter raised to the power 5 upon kg second square. Many times they are asking. Are you clear with this? Many times they are asking this. Many times they are asking this question. Many times they are asking this. Chaliye. Now, what are the values of the constant, you can say, A, B and R of the van der Waals equation? R is your characteristic gas constant. Sir, A, first of all, B is given by Vc upon 3. Critical volume upon 3. Vc upon 3. A is given by 3 Pc Vc square. याद कर लो इसको, रट्टा मार लो. B is given by Vc upon 3, not going on to the derivation. A is given by 3 Pc Vc square. Not just the interview question, they are there for your examinations also. Remember this, they are there for your examinations also. And R is given by 8A upon 9 Vc Tc. That is, R is given by 8 upon 3. You put the value of A, 8 upon 3 Pc Vc upon Tc. 8 upon 3 PCVC upon TC. So sometimes they can ask you the value of the Z at the critical point also, ZC. Sir, what was ZC? Sir, ZC was nothing but PV upon NT divided by R bar, PV upon NT divided by R bar. Okay, PV upon NT divided by R bar. Z was nothing but PV upon NT divided by R bar. So instead of this, can you write this PV upon, you can say, P specific volume will be equals to RT. We can write this, na? Not like this. Not like this properly. Can I write this as PV upon N R bar T, and this can also be written as PV upon MRT? Okay, at the critical point I can write this as PV upon RT. Specific volume I am taking. When I am taking specific volume, at the critical point this will be PCVC upon RTC. Put the value of R. When I put the value of R, this will be 8 by 3 into, you can say, PC VC upon TC multiplied by PC. This is also VC upon TC. Everything will get cancelled out. Everything will get cancelled out, and you will be left over with only 3 by 8. So the value of Z at the critical point is 3 by 8. Are you clear? The value of Z at the critical point is 3 by 8. This has been asked in the examination. This has been asked in the examination. Is this clear, everyone? Is this clear, everyone? I hope you are understanding the beauty of thermodynamics. I am going very slow. I am going very slow. Not to worry about the completion, but I'll go very slow. But I will go very slow. Is this clear? This already I have written. See, 3 upon 8. This already we have discussed. 3 upon 8. I hope you enjoyed this. I hope you enjoyed this. Chaliye. Now, very good, everyone. Now, what is the difference between the ideal gas versus the perfect gas? What is the difference between the ideal gas versus the perfect gas? Sir, ideal gas is one which is having Z is equals to 1. Okay, sir. Then semi-perfect gas and perfect gas. Sir, what is the perfect gas? Sir, on changing the temperature, the value of CPCV and I can say that gamma also do not change. The value of CP, CV and gamma does not change. For an, you can say, perfect gas, on changing the temperature, the value of CP, CV and gamma does not change. But for a semi-perfect gas with respect to the change in temperature, for a semi-perfect gas with respect to the change in temperature, the value of CP, CV and ultimately gamma also changes. The value of CPCV and ultimately gamma also changes. So this is the difference between the semi-perfect and perfect gas. Always remember, the monoatomic gases are considered to be perfect gases, and diatomic gases between the temperature range of 150 Kelvin to 600 Kelvin are considered to be the perfect gases. Is this clear, everyone? Is this clear, everyone? Tell me, is this clear? Is this clear? Chaliye. Now, this was the graphical representation. Okay, this we have already discussed, that R will be constant throughout CP and CV. For, you can say, the perfect gas will be constant. CP and CV for the perfect gas will be constant. This is the graph for the perfect gas. You can see that CP, CV for the perfect gas are constant. So R is also constant, gamma is also constant. But here the CP, CV values are changing. And you know, I'll be telling you the value of gamma ultimately decreases. The value of gamma ultimately decreases. Most of the student feels like that CP, CV are increasing, so gamma will increase, but gamma will not increase. I'll tell you later on. So now, obviously, we have completed the first part of thermodynamics, and now we are jumping onto the thermodynamics processes. Constant volume, constant pressure, constant temperature, adiabatic and polytropic. Constant volume, constant pressure, adiabatic, constant temperature, adiabatic and you can say polytropic process. So first one, starting with your very favorite, your very own, the constant volume process. Starting with your very favorite, the constant volume process. How's the Josh, everyone? How's the Josh? Hi, sir. Chalo. So now, first of all, the constant volume process for any gas when the volume is constant. For any gas, the volume is constant. So it is also known as, sir, isochoric or isometric process. It is also known as isochoric or isometric process. Remember this, it is also known as isochoric or isometric process. Sir, for a constant volume process, the best example is a rigid container. And we know that very well. For a rigid container, the displacement work is always zero. Whether you are having, when you are having the isochoric heat addition, the displacement work will be zero. Similarly, the piston cylinder assembly having stoppers on both the sides. The piston cylinder assembly having stoppers on both the sides, on the application of heat, the volume will not change. And when the volume will not change, your displacement work is zero. And that's why remember this, for a constant volume heat addition or heat rejection. For a constant volume heat addition or heat rejection, the displacement work will always be zero. The displacement work will always be zero. Okay, sir. Sir, representation of constant volume process onto the PV diagram, sir, vertical line. Heat addition, sir, pointing towards upward. Heat rejection, you can say pointing towards downward. Okay, sir, very good. Constant volume heat rejection and heat addition. Sir, onto the VT diagram. Pehle PV pe tha, now on the VT diagram. So this is a horizontal line. Sir, constant volume heat addition pointing towards the right hand side. Constant volume heat rejection pointing towards the left hand side. These notes are for you, bacha. These notes are for you. Okay. Analysis for an ideal gas, you can say undergoing a constant volume process. We know that very well. Our very own, very favorite ideal gas equation. Our very own, very favorite ideal gas equation, PV is equals to MRT. So we can write this as P is equals to MRT upon V. Sir, here volume is constant, and always remember M and R will also be constant. Sir, M and R cannot change. For a gas, the values of M and R cannot change. So can I say that P upon T will be equals to MR upon V? P upon T will be equals to MR upon V. So can I say that for an ideal gas undergoing a constant volume process, understand this very well, for an ideal gas undergoing a constant volume process, for an ideal gas undergoing the constant volume process, pressure upon temperature is constant, or I can say that pressure is directly proportional to temperature. Pressure is directly proportional to the temperature, and this is nothing but our first law of ideal gas, that is our Gay-Lussac law. Sir, Gay-Lussac law, that pressure is proportional to temperature, or P1 upon T1 will be equals to P2 upon T2. P1 upon T1 will be equals to P2 upon T2. So this is nothing but your Gay-Lussac law, that for an ideal gas, for a given amount of mass. Why, sir, given amount of mass? Because here mass is constant. I told you mass is constant. Remember this very well. The mass is constant. So for a given amount of mass of an ideal gas, for a given amount of mass of an ideal gas, this is constant. This is constant. That is the mistakes that you are doing. So for a given amount of mass of an ideal gas undergoing an isochoric process, for a given mass of an ideal gas undergoing an isochoric process, absolute pressure is directly proportional to absolute temperature. For a given amount of mass of an ideal gas undergoing an isochoric process, absolute pressure is directly proportional to absolute temperature according to the Gay-Lussac law. According to the Gay-Lussac law, for a given mass of an ideal gas, for a given amount of ideal gas undergoing an isochoric process, absolute pressure is directly proportional to the absolute temperature. Is this clear, everyone? Is the first law clear, everyone? Is the first law clear? Boliye, is the first law clear? Very good. Sir, second is, now we have completed a constant volume process, and we will be jumping on to the constant pressure process. Now we will be jumping on to the constant pressure process. So there are two things. First of all, we are having two things, that pressure is the function of temperature and density. Always remember, pressure is the function of temperature and density. I told you that constant pressure process, मैंने शुरुआत में भी बोला था, it is always seen that the pressure is constant at the initial state and final state, बीच में कुछ भी हो, so we are not worried about this. In between, the pressure will be changing, but the pressure is constant at the initial state and final state. So always remember, as the temperature increases, the pressure increases. Generally, as the temperature increases, the pressure increases, and as the density increases, number of molecules are increasing, so force applied by the molecules on the container increases, so the pressure is increasing. Remember this, as the temperature increases, pressure increases, as the density increases, the pressure increases. So we will be using this. We will be using this. So let's say we are assuming any gas undergoing a constant pressure process, that is isobaric or isopistic process. नाम क्या है इसका? Isobaric or isopistic. Isobaric or isopistic process. Okay, sir. So this is a, you can say, piston cylinder arrangement, and let's say inside pressure is 5 bar. And let's say inside pressure is 5 bar, so you are having rise bag or infinitesimal number of weights, infinite number of weights. Okay, sir. So you are removing the rise grains one by one, or else you are removing the dead weights one by one. So what will be the case? As you will be removing the, you can say, chalo, you are not removing the rise bag. Don't remove the rise bag. Okay, just understand one thing. Let's say if I am supplying the heat. Let's say if I am supplying the heat, then due to the, you can say, supply of the heat, there will be a pressure difference between the inside pressure and the outside atmospheric pressure and the weight of this piston. There will be a pressure difference, and so for slight increase in temperature, there will be a slight increase in pressure also. For a slight increase in temperature, as we are supplying the heat, so the pressure will increase. Okay, sir. Sir, when the pressure increases, the volume increases. As the piston will move upward, the volume will increase. Sir, volume increases, so volume is having inverse relation with the density. Volume is having inverse relation with the density, so density decreases. So the density decreases, and as the density decreases, remember this, ultimately the pressure will decrease. That means the end state, the pressure will be same. That means at the end state, the pressure will be same. That will be balanced by the dead weight of this rise bag plus the atmospheric pressure against this internal pressure. Are you clear? So isobaric process is constant pressure only at the end states. In, you can say, the path of the process, the pressure may change. During the, you can say, interaction, the pressure may change. At the end states only, the pressure is considered to be constant. How many of you are feeling the, you can say, constant pressure process? How many of you can feel this? How many of you can feel this? Tell me. How many of you can feel this? How many of you are feeling the beauty of, you can say, this process? Yes or no? Okay, so remember this. This is isobaric process. Many times they are asking the question onto the, you can say, balancing of, you can say, the pressures. Balancing of the pressure. Sir, what is the balancing of pressure? What is the balancing of pressure? Sir, here they are asking the question onto this topic. Many times they are asking. Sir, from inside, let's say P is the pressure of gas acting onto the piston area A. Now, the atmospheric pressure will also be applied onto this piston, which is also applied onto this area A, not deducting the area that is covered by dead weight. Okay, now this dead weight, W will be acting downwards. So can I say that for the pressure balance, P dot A will be equals to P ATM local dot A plus W. P dot A can be called as P ATM local dot A plus W. Okay, sir, if you divide by area, so what you are getting, sir, pressure will be equals to P ATM local. The pressure will be equals to P ATM local plus W by A. Now one thing is very clear. Now throughout the process, the value of W upon A will be constant. Throughout the process, the value of W upon A will be constant. Similarly, the local atmospheric process will also not change generally. So this is also constant. When the right hand side, both values are constant, so left hand side pressure will also be constant. This is the mathematical representation. This is the physical representation of constant pressure process. This is the mathematical representation. And bacha log, they will be giving you, you can say, P ATM local. They might give you pressure, so they might ask you W. They might give you W, so they might ask you the pressure change for that, pressure values for that. Are you clear? Such questions are asked. Very easy questions are asked from this, you can say, topic. Is this clear? Is this clear, everyone? Chaliye. Now constant pressure process onto the PT diagram. Constant pressure process onto the PT diagram. Sir, horizontal line, constant pressure heat addition acting towards right, constant pressure heat rejection acting towards left. Constant pressure diagram on the PV, constant pressure process onto the PV diagram. Sir, pressure is equals to constant, so constant pressure heat addition always pointing towards right, heat rejection pointing towards left. This is pretty clear. Now analysis for the, you can say ideal gas. Analysis for the ideal gas. Okay. What will be the analysis for ideal gas? Sir, PB is equals to MRT. Now here we will allow the pressure to go into the right hand side. So now what is the point? Sir, MR is constant once again. Sir, here the pressure is also constant. So volume is directly proportional to temperature. Second law, volume is directly proportional to temperature. So can I say that V1 upon T1 will be equals to V2 upon T2? Remember this, V1 upon T1 will be equals to V2 upon T2, and this is given by Charles' law. So once again, for an ideal gas, for a given amount of mass of an ideal gas, what is the definition? Sir, for a given amount of mass of an ideal gas undergoing a constant pressure or isobaric process, volume is directly proportional to absolute temperature. Volume is directly proportional to the absolute temperature. For a given amount of mass, according to the Charles law, for a given amount of mass of an ideal gas undergoing an isobaric process, volume is directly proportional to the absolute temperature. Absolute temperature बोले तो temperature should be taken in Kelvin. Absolute temperature बोले तो temperature should be taken in Kelvin. Are you clear with this? Are you clear with this? Tell me. Absolute temperature बोले तो temperature should be taken in Kelvin. Okay. चलो. Now third one, isothermal process. Third one, isothermal process. Sir, what is isothermal process? Sir, temperature remains constant for any gas. Now beautiful conclusions are coming from here. Questions are coming. Sir, always remember that temperature remains constant for any gas. Okay, sir. Sir, what is the case as you are supplying the heat at constant temperature process? As you are supplying the heat, you can say at constant temperature process. So as you supply the heat, sir, energy of the system increases. First of all, the energy of the system increases. Understand this very well. Why there is no absolute volume, sir? Absolute volume means there is no zero volume. Na? Absolute means comparing it with total zero, Guru. So we cannot have absolute zero volume. Na? Volume can never be zero. Volume can never be zero. You cannot, you can say, see, it is nearly difficult to say what is a perfect vacuum. Are you getting my point? A perfect vacuum is nearly difficult to say. There will be pressure less than the atmospheric pressure, but zero is another thing. Are you getting my point? Okay. Okay. That's why absolute zero temperature is also not possible. You know, absolute zero temperature is also not possible to achieve. I'll tell you this later on, where we will be moving ahead in today's thermodynamic session only. We will be discussing this. So what you are doing, as you are supplying the heat, sir, the energy increases, internal energy increases. First of all, internal energy increases. Okay, internal energy increases. Okay, sir. As the internal energy increases, the temperature of the gas also increases. Remember, understand this very well. The internal energy increases, then the temperature also increases, because temperature is the function of internal energy. But what you'll do, you will remove the dead weights one by one. You will remove the dead weights one by one. As you remove the dead weight one by one, as the temperature was increased, obviously the pressure would have increased. And now as you remove the dead weight one by one, the piston will move upward. Sir, piston will move upward, and here the, you can say, energy interaction will be done onto the basis of the internal energy. यहाँ पे energy कहाँ से लोगे? You will be taking the internal energy. So once again, the internal energy of the system will decrease. First of all, it will increase, then it will decrease. So once again, the temperature will decrease. Once again, in isothermal process also, there will be, you can say, temperature constant at the end state only. There will be constant temperature at the end state only. So bacha log, this condition is true for ideal gas only. That means, remember this, for an ideal gas, heat can be supplied at constant temperature, but that heat will be completely converted into displacement work. That heat will be completely converted into displacement work. Are you getting my point? That heat will be completely converted into displacement work. For an ideal gas, heat can be supplied at constant temperature, but heat will be converted into work for ideal gas only. We don't know about other gas, because real gases are having a very, very different behavior. We cannot predict for them. So we are assuming them to be ideal gas, and we are doing our analysis. Are you clear? Not going in more detailed discussion. So for an analysis of an ideal gas, we know that very well. PV is equals to MRT. Now here MR is also constant. Your temperature is also constant. So can we say that PV is equals to constant? So PV is equals to constant. That means pressure is inversely proportional to volume. So you can say that according to Boyle's law, for a given amount of mass of an ideal gas undergoing an isothermal process, pressure, absolute pressure is inversely proportional to volume. For a given amount of mass of an ideal gas undergoing an isothermal process, absolute pressure is inversely proportional to the volume. Absolute pressure is inversely proportional to the volume. According to Boyle's law, for a given mass of an ideal gas undergoing an isothermal process, absolute pressure is inversely proportional to volume. Is this clear? Boliye Marathi. Is this clear? Chaliye. Now, very interesting question. If you plot this onto the PV diagram, sir, pressure and volume both are constant. Pressure and volume both are constant. You can say that P dot V is equals to constant. So it will be a rectangular hyperbola. Now, what is a rectangular hyperbola? You know, I was a faculty of engineering drawing. Okay, I was the faculty of engineering drawing in my initial days of career. I have taught engineering drawing, I have taught mechanical drafting, because our engineering drawing for, you can say, mechanical branch is having some detailed mechanical drafting of, you can say, shapes and all separately. So I have taught both the subjects, and rectangular hyperbola is the one where you can project this onto both the axes. You will be getting the same, you can say, proportionate area. Whether you project this onto the volume axis or you project this onto the pressure axis, the area under this hyperbola will be same on both the axes. Are you getting my point? So that is a rectangular hyperbola. So for a rectangular hyperbola, integration of, you can say, x dy is equals to integration of y dx. Remember this very well. The characteristic equation of rectangular hyperbola is integration of x dy is equals to integration of y dx. That means integration of p dv is equals to integration of v dp. Is equals to, don't go on to the signs or minus integration of VDP. So integration of PDV is nothing but the closed system or displacement work. Integration of PDV is nothing but the displacement work of the closed system. Integration PDV is nothing but the displacement work of the closed system, and integration of VDP is nothing but the constant volume work of the open system, because open system is also, sorry, control volume work of the open system, because open system is also called the control volume. So for isothermal process, for an ideal gas undergoing an isothermal process, displacement work of the closed system integration PDV is equals to the control volume work of the open system integration of VDP. That is not zero. That is not zero. We are discussing about open system. For the open system, control volume work will not be zero. I will be telling you what is the difference between the control volume work. You can say what is the difference between the constant volume work for the open system. For the closed system, don't worry. Don't worry, it will not be zero. For closed system, it is zero. I will be telling you. That's why I told this in the initial only. Don't worry, all the doubts will be cleared. So remember this, a very regularly asked system. Sorry, for closed it is correct. For closed it is correct, but we are having not dV. We are having constant temperature process. No? Here we are not having constant volume. So it cannot be zero. It cannot be zero. We are not having constant volume. It is zero for constant volume only. Okay. So remember this, that your displacement work for a closed system, that is integration PDV, is equals to the control volume work of an open system for an ideal gas undergoing an isothermal process. That means this is a very regularly asked question. Very regularly asked question, that open system work is equals to closed system work for a, you can say, for a isothermal processor. Why it is same? Because for the closed system work, you are projecting the process of PV diagram onto the volume axis. Remember this, for a closed system work, you are projecting the process of PV diagram onto the volume axis, and for open system work, you are projecting this onto the pressure axis. Is this clear? We will discuss this also in detail. Is this clear? Now, what is the conclusion? What is the conclusion? For ideal gas, isothermal process on a PV diagram is represented by a rectangular hyperbola symmetrical to both pressure and volume axis. That is integration PDV is equals to minus of integration VDP. Minus of integration VDP. Is this clear? Okay, sir. Sir, displacement work of the closed system is equals to the control volume work of an open system provided that the initial and final states are same for a isothermal process. For an ideal gas undergoing an isothermal process, displacement work of the closed system is equals to the control volume work of the open system. Is this clear, everyone? I hope you are getting the beauty of thermodynamics. Now, fourth process, sir, adiabatic process. Sir, fourth process is nothing but adiabatic process. Sir, what is adiabatic process? Sir, the process in which your heat transfer will be zero. The process in which your heat transfer will be zero. The process in which your heat transfer will be zero. So what will be the case? As you will be removing this राइस ग्रेन्स और डेड वेट वन बाय वन इसको एक एक करके रिमूव करोगे सो द पिस्टन विल मूव अपवर्ड ऑन द एक्सपेंस ऑफ द इंटरनल एनर्जी ऑफ द सिस्टम on the expense of the internal energy of the system. So in an internally reversible adiabatic process, the work is done onto the expense of internal energy of the system because heat cannot be supplied. In case of isothermal process, heat is supplied and that is completely converted into work. That is completely converted into work. So here the internal energy will decrease. Ultimately the temperature will decrease but volume will increase. Internal energy decrease, temperature decrease, pressure decrease, but volume increases. Remember this, for an adiabatic process, internally reversible adiabatic process, internal energy decreases, volume decreases, internal energy decreases, temperature decreases, pressure decreases, but volume increases. Is this clear? The conclusions are very, very important. Okay. Now, basically, the adiabatic processes, this was an internally reversible adiabatic process in which the heat transfer is zero. This was an internally reversible adiabatic process in which the heat transfer is zero. This is an internally irreversible adiabatic process. Irreversible adiabatic process. What do we want? In irreversible adiabatic process, we want still, as it is an adiabatic process, our heat transfer should be zero. Our heat transfer should be zero. Okay, sir. Sir, for the heat transfer to be zero, what I will be doing? I will be suddenly removing the dead weight. And as I suddenly remove the dead weight, the piston in a very fast rate will come to the top. Piston at a very fast rate will be come towards the top and there will be nearly time rate will be zero for the heat transfer. So we can ideally assume a very rapid, you can say, process to be an internally reversible adiabatic process because still the heat transfer can be hypothetically assumed to be zero. Are you getting my point? Are you getting my point? That means you can supply the heat without doing anything. So this is another thing. This we'll discuss later on. Okay. Now there are two important formulas for perfect gas. Remember this. These PV raised to the power gamma is equals to constant. This condition is valid for perfect gas only. And in terms of temperature and pressure, I can say that Tp raised to the power 1 minus gamma upon gamma is equals to constant. But I am not going on to the derivation. At present, we don't have time to teach every derivation to you. This is a marathon session. I have to teach in 5 to 6 hours what we have discussed in around, you can say, 60 to 80 hours. Okay. So Tp raised to the power 1 minus gamma upon gamma is equals to constant for, you can say, adiabatic perfect gas undergoing an internally reversible adiabatic or isentropic process. In terms of temperature and volume, this is given by Tv raised to the power gamma minus 1 is equals to constant. Is this clear? Tp raised to the power 1 minus gamma upon gamma is equals to constant and Tv raised to the power gamma minus 1 is equals to constant. Is this clear? Is this clear, everyone? Tell me, is this clear? I hope you are getting everything properly and enjoying this also. Chaliye, moving ahead. Now, this one is a very beautiful question. This one is a very beautiful question. Can you see something? Can you see something? Clear, sir. Very good. Chalo. Can you see something? Okay. Acha, GATE will be updating. IIT Kharagpur director, sir, has already told that they will be clearing the condition of GATE examination very soon. Okay. I regularly check the updates, bachalo, and very soon we will be getting the updates related to the examination. Remember this very well. We will be very soon getting the updates. Okay, because there is a, you can say, some types of panic situation in the minds of students. So thoda bahut hai, I hope you get the answers very early related to the situation of the examination. Related to the situation of the examination. There is slight of a panic situation in the minds of students. And I totally understand that. I totally understand that. Happens sometime. Thank you very much, Pushpendra. Actually, I think the director of IIT Kharagpur had given the interview to, I think, NDTV or any one of the news channel, I don't remember, where sir had told that they will clarify at the earliest, because they are also worried. Some students, they might lose some of the days in this tension. Okay, chaliye. Now, which diagram has more slope onto the PV diagram? Isothermal process or adiabatic process? So first of all, you should know the slope of the process. So slope of the isothermal process, I'm just directly going on to the final conclusion, is given by minus P upon V. dP upon dV, that is the slope. Always remember, we were writing, I hope you are aware, so slope is given by, you can say slope of any curve is given by y2 minus y1 upon x2 minus x1. Okay, and that's why the, you can say, slope onto the PV diagram will be given by P2 minus P1 upon V2 minus V1. P2 minus P1 upon V2 minus V1. Yes or no? P2 minus P1 upon V2 minus V1. So this will be dP upon dV. This will be dP upon dV. So for an isothermal process, dP upon dV is given by minus of P upon V. For an isothermal process, it is given by minus of P upon V, and for an adiabatic process, it is given by minus of gamma times P upon V. 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 Remember this? So we got to know that the slope of isentropic process dP upon dV is equals to gamma times the slope of, you can say, isothermal process. The slope of isentropic process is equals to the gamma times the slope of isothermal process. Sir, why it is negative? Why it is negative? What is the meaning of negative? What is the meaning of negative? You see this? When the, you can say, volume is increasing, the pressure is decreasing. When the volume is increasing, the pressure is decreasing. And secondly, if we will be doing this for compression, so when the pressure will increase, your volume will decrease. That's why it will be having the negative slope only. Always remember. So remember this very well, that the constant temperature and adiabatic process both are having the negative slope onto the PV diagram. Both are having the negative slope onto the PV diagram, and you can say that the slope of isentropic process, that is minus of gamma times P upon V, is always equals to gamma times the slope of isothermal process. So obviously the slope of isentropic process will be more. So when you plot the graph, this is the diagram of isothermal process with a less slope. This is the diagram of isothermal process for which PV is equals to constant. PV is equals to constant, and this is the slope of, you can say, isentropic process, internally reversible adiabatic process, PV raised to the power gamma, which is having more slope. PV raised to the power gamma, which is having more slope. Are you getting the point, bacha log? This is having more slope and this is having less slope. Always remember in the clockwise direction. Always remember to measure this in the clockwise direction. Is this clear? Okay, I hope this is clear. ऐसे questions भी आते रहते हैं. Okay, so first of all, let's discuss now for the polytropic process. Okay, then we will be discussing. Now, there is a very beautiful question. There is a very beautiful question they are asking in the examination. What they are asking? Sir, when the perfect gas is expanded isothermally and internally reversible adiabatically, separately from same initial state to same final volume. Same initial state to same final volume. Which process will have more volume? From same initial state to same volume. Same initial state to same volume. Okay, which process will have more final volume? Which process will have more final volume? Okay, so you are expanding this from, you can say, same initial state isothermally, and you can say same initial state adiabatically up to the same pressure. So obviously the volume of the isothermal process will be more than the volume of isentropic process. Can you see this? The volume of isothermal process will be more than the volume of isentropic process. Is this clear, everyone? Is this clear? They can ask you this. Similarly, in the second case, you are expanding a perfect gas isothermally and internally reversible adiabatically up to, you can say, same final volume, up to same final volume, then the pressure will have more final pressure, in which case pressure किसमें ज्यादा होगा? So same final volume, so this will be your isothermal expansion, this will be your isentropic expansion. So obviously we can see that pressure of the isentropic process will be more than the pressure of isothermal process will be more than the pressure of isentropic process. Pressure of isothermal process will be more than the pressure of the isentropic process. Is this clear? So volume of the isothermal process is also more, and pressure is also more, Chaliye. Sir, polytropic process means, poly means many and tropic means changes. Poly means many and tropic means changes. That means volume will not be constant, pressure will not be constant, temperature will not be constant, and your heat transfer will also not be zero. Volume will not be constant, pressure will not be constant, temperature will not be constant, and your heat transfer will also be not be equals to zero. So remember this, polytropic process for any gas is given by PV raised to the power n is equals to constant. PV raised to the power n is equals to constant, where n is the polytropic index from, you can say, greater than 1 up to gamma. In terms of temperature and pressure, once again you can write this as Tp raised to the power 1 minus n upon n is equals to constant. This can be applied for ideal gas. In terms of temperature and volume, you can write Tb raised to the power n minus 1 is equals to constant. कुछ नहीं करना, gamma की जगह replace it by n, gamma की जगह replace it by n, gamma की जगह replace it by n. Only do this. Okay, sir. Sir, for a polytropic process, now what will be the slope of polytropic process? The slope of polytropic process is given by minus of n times P upon V. Minus of n times P upon V, and the value of n is greater than 1 but less than gamma. So this is your polytropic process. This is your polytropic process. This is your isothermal, this is your polytropic, and this is your adiabatic process. Is this clear? Isothermal, polytropic, and adiabatic process. Is this clear, everyone? I hope this is pretty clear. Okay, sir. Now representation of various processes onto the PV diagram. Representation of various processes onto the PV diagram, starting with the first one. You can say let's start with the polytropic first of all. So we will be making an initial assumption that PV raised to the power k is equals to constant, because ये k की वैल्यू से अपने को पता चलेगा what will be the slope. ये k की वैल्यू से अपने को पता चलेगा what will be the slope for the given process, what will be the slope. So for a polytropic process, PV raised to the power n is equals to constant. That means for a polytropic process, k is equals to n. For a polytropic process, k is equals to n. Is this clear? Okay, sir. Now for internally reversible adiabatic process, your Q is equals to 0. Q is equals to 0 and PV raised to the power gamma is equals to constant. Now comparing it with equation PV raised to the power k is equals to constant, we are getting this as k is equals to gamma. K is equals to gamma. Okay, sir. बताता हूँ इसका use कैसे करेंगे. Now for an isothermal process, your temperature is equals to constant. That means PV is equals to constant. That means you can say that PV raised to the power k is equals to constant, or else k is equals to 1. For an isothermal process, the process index k is equals to 1. Remember this. This is the process index. ये क्या है? Process index है. For an isobaric process, sir, pressure is constant. PV raised to the power 0 will only making this equals to 1. अपने को V को कट करना है, V को 1 करना है. So V raised to the power 0 only will be equals to, you can say, constant. So can I say that PV raised to the power k is equals to constant, or k is equals to 0? Or k is equals to 0. Is this clear? And the last one, isochoric process. Now most of the students are not, you can say, knowing about this. They are mugging this up. So what will be the case? Isochoric process, volume is equals to constant for any gas. Now P dot 0 into volume will be equals to constant. So we want to find the index of, you can say, V. We know that very well. PV raised to the power k is equals to constant. So what we can do? Divide this by, you can say, k into the power. मतलब P raised to the power 1 by k and V raised to the power k by k. So we will be getting this as 1. मुझे यहाँ पे 1 चाहिए. So for getting this over 1, t raised to the power 1 by k into v raised to the power 1 is equals to constant. That means 1 by k is equals to 0, or the process index for a constant volume process k is equals to infinite. This means process index for a constant volume process k is equals to infinite. For isobaric process k is equals to 0. For isothermal process k is equals to 1. For adiabatic process, internal reversible adiabatic process k is equals to gamma, and for a polytropic process k is equals to n. बोलिए, ये चीज समझ में आई? ये चीज समझ में आई? बोलिए, ये चीज समझ में आई? ये चीज समझ में आई? वेरी गुड, वेरी गुड. सो नाउ लेट्स प्लॉट इट. नाउ लेट्स प्लॉट इट. सोने पे सुहागा, देर क्यों करना भाई? जस्ट गिव मी अ मिनट. Okay, chaliye. Now see this. Keeping the, this is your, you can say, line where k will be equals to 0. Remember this horizontal line, that means k is equals to 0. Vertical lines, that means k is equals to 1. Suno dhyan se. K means nothing but v raised to the power 0. So can we say that this is the direct indication of the slope? So when the slope is 0, the line is horizontal. Remember this, for a horizontal line, the slope is 0, and for a vertical line, the slope is infinite. I'm giving you the mathematical feel also. For the horizontal line, the slope is 0, so this is k equals to 0. For the vertical line, this is slope is infinite, so k is equals to infinite. Now this yellow curve is the one for which your k is equals to 1. This yellow curve is the one for which your k is equals to 1. Just see this. Isothermal process. K is equals to 1. This is your isothermal process. Now for this process, k is equals to n. Polytropic process, pv raised to the power n is equals to constant, and this is adiabatic process, pv raised to the power gamma is equals to constant. So in the clockwise direction, isobaric process k is equals to 0, isothermal process k is equals to 1, polytropic process k is equals to n, adiabatic process k is equals to gamma, and isochoric process k is equals to infinite. Isochoric process k is equals to infinite. Now this was for expansion. For compression, turn this, you can say, by 180 degree. Turn this by 180 degree. So this will be your constant pressure process. This will be your isothermal. This will be your polytropic. This will be your adiabatic, and this will be your isochoric. That is your constant volume process. Is this clear? So always remember, in the clockwise direction, the value of k is increasing. In the clockwise direction, the value of k is increasing. I hope you are enjoying this. I hope you are enjoying this. Tell me. I hope you are enjoying this. You are enjoying this. Yes. Okay. Chaliye. Now, zeroth law. Acha, zeroth law and all we will discuss at the end. First of all, let's discuss the. Chalo, let's discuss the zeroth law. It will be better for now. What is zeroth law? I hope you are clear with the processes. Before going on to the heat and work interaction, we need to discuss these things. Okay. We are still going on to the formulas of heat and work interaction. Don't worry, our first chapter is actually completed. At present, our first chapter is actually completed. Okay, so zeroth law of thermodynamics. Sir, when a body is in thermal equilibrium with the body B and also separately with body C, then they are also in thermal equilibrium with each other. Very easy. So temperature A is equals to temperature B. Temperature A is equals to temperature C, then we can say that temperature B is equals to temperature C, and this is used for the calibration of the, you can say, thermometers. Zeroth law, you can say, is used for the calibration of the thermometers. Okay, is this clear? Not to worry about anything. Now, heat interaction. Sir, heat interaction is the form of energy interaction due to the temperature difference. Heat interaction is the form of energy interaction that occurs due to the driving force, that is the temperature difference given by dq mc dt. Okay, this will be del Q mc dt, where your C is the specific heat, C is the specific heat, and delta T is the temperature difference. C is the specific heat and delta T will be the temperature difference. Okay, sir, what is the specific heat now? Sir, it is the amount of heat which is required to raise the temperature of unit mass by unit degree. C will be given by dq upon m delta T. Amount of heat which is required to raise the temperature of unit mass by unit degree. Okay, so this C will be given by kilojoule per kg Kelvin. We know that very well. For solids and liquid, we are having only one value of specific heat. For solids and liquids, we are having only one value of specific heats, and for gases, it depends upon the process considered, and that's why we are having two values of specific heat, one at constant pressure, that is for Cp for the air is given by 1.005 kilojoule per kg Kelvin, and Cv for the air is given by 0.718 kilojoule per kg Kelvin. Is this clear? But specific heat for water is not written as at constant pressure or volume, because for liquids and solids we are having only one value of specific heat. Okay, sir. Now a very beautiful question. Sir, what is an adiabatic specific heat? Specific heat C is given by dou Q by m delta T. Now for an adiabatic process, your dou Q will be 0. That means always remember the adiabatic specific heat, that is the specific heat for an adiabatic process will be 0, 0, 0. ये किसी को बताना ही. It will be 0, 0, 0. Is this clear? The adiabatic specific heat will be 0, 0, 0. The adiabatic specific heat will be 0, 0, 0. Similarly, sir, isothermal specific heat. Sir, isothermal means delta T will be 0. That means C value divided by 0. That means it will be infinite. So, isothermal specific heat is infinite. Isothermal specific heat is infinite. Okay, isothermal specific heat will be infinite. Is this clear? Isothermal specific heat is infinite. Many times they are asking. Now this we will be discussing. This is, I have written this in the class also. We will discuss after some of the concepts are over. This is pending. This we will discuss after some of the concepts are over, because at present you don't know about the heat supplied at constant pressure. You don't know about the heat supplied at constant volume. So this is slightly pending. Okay. So specific heat is also of two types. So sensible heat, that is occurring due to temperature difference, and latent heat, that is heat transfer during the phase change. The temperature does not decrease but phase change takes place. So this we will be discussing in pure substance, not to worry about anything. This we will be discussing in the, you can say, pure substance. Sir, first law is known as the law of conservation of energy. First law is known as the law of conservation of energy, also known as Joule's law, and it is quantitative law. Also known as Joule's law, and it is quantitative law. Law of conservation of energy, Joule's law, and quantitative law. Joule's law and quantitative law. Okay, sir. Sir, what is first law? Now understand the beauty of the first law. Slowly, slowly, I will give you the beauty of the first law. For a closed system undergoing a cyclic process, net heat interaction is equals to net work interaction. For a closed system undergoing a cyclic process, net heat interaction is equals to the net work interaction. Net heat interaction is equals to the net work interaction, but this is for a cyclic process. For a closed system, that means this is for a cycle. Numericals not in this, it will not be possible. I will have a separate marathon guru for in the special classes for numericals. I promise I will be taking the separate marathon for numericals onto the Unacademy special class, because it will be very difficult to complete the numericals, very difficult at present. Okay, because the concept, you know, thermodynamics is slightly a big subject. Thermodynamics is slightly a big subject. We will end up the class today by 4:30 or 5 only. I don't think we will be able to end it before. And I feel some topics will be left over, but I'll surely do the numericals. You know, I'll be taking the special classes for the numerical portion. Don't worry. We will be taking the special classes for the numerical portion. I promise this. Okay. We are doing maths. We are doing maths in the special classes at 10 p.m. in the night. You can join that also. Many students are coming. Everyone is enjoying. We are starting calculus today. We will start aptitude practice course also, and this will be our third practice course of thermo. Okay, many students are messaging me for fluid mechanics also. Let's hope what I can do for fluid mechanics. Okay, many students are messaging me, sir, anything for fluid mechanics. So I'll try that. Nothing guaranteed at present actually, but I'll do this for sure. You know, these are my course note of ISRO course. These are my personal note, you know, before some months, before 1 or 2 years, I was, you can say, teaching for ISRO scientist / engineer post. So these are the notes of that. Okay, I'm using that notes over here. These are my handwritten notes. These are my handwritten class notes, you know. Many of the students will be aware about my these notes. Okay, I will give you this open only. These were my paid courses note, but at present it's fine. Sab chalta hai. Okay, these are my notes only, so it's fine. We can use this note for the quick revision, because you know what I feel in the ISRO paper and all na, you require a basic understanding, you can say, but on an overall manner. So these are the, you can say, compressed notes for such exams. These are the compressed notes for such exams. Okay, so for a closed system undergoing a cyclic process, net heat interaction is equals to the net work interaction. Net heat interaction is equals to the net work interaction. Okay, sir. Sir, now what are the consequences of first law? You should know about this. You should know about this. You should know about this. Sir, heat transfer is a path function. Heat transfer is the path function. Energy is the property of the system. Energy is the property of the system, and we know that very well. Property of the system is point function. Always remember, energy will be the summation of the kinetic energy plus potential energy plus internal energy. Sir, energy of an isolated system remains constant, because for an isolated system, heat transfer is zero, work transfer is zero. That means delta E for an isolated system is also zero, and perpetual motion machine of first kind is impossible. So these are the four, you can say, consequences of first law. Consequences बोले तो ये first law के ऊपर से derive करे गए हैं. These are the things that we are getting as the end results of first law. Okay, sir. Sir, first law of thermodynamics. Now understand the beauty. First of all, the first law of thermodynamics applied for the process. Can you read this? I think everything is readable. That Q minus W is equals to delta E. First law of thermodynamics for a process. Previously what we were discussing, it was for cycle. For a cycle, net heat interaction is equals to net work interaction, but for a process, Q minus W is equals to delta E. Q minus W is equals to delta E. Now what is W? Sir, W, that is total work interaction, is the summation of the displacement work plus electrical work plus shaft work. Displacement work plus electrical work plus shaft work. Okay, sir. Sir, what is your total change in energy? This is not just internal energy. This is the total change in energy, which is given by summation of kinetic energy plus the summation of the potential energy plus the internal energy of the system. Always be clear with this. So I can say that dou Q minus dou W will be equals to dE, because heat and work are path function. Remember this very well. Heat and work are you can say, exact differential. They are non-exact differentials or path function. So we will have to write them by dou, you can say, always. So this will be dou Q minus dou W will be equals to dE. Okay, sir. Sir, first condition for a stationary system. For a stationary system, that means the system which is having zero change in kinetic energy and zero change in potential energy. So system which is having zero change in kinetic energy and zero change in potential energy, that means the total energy change of the system is equals to the potential energy. That means the total energy change of the system is equals to the potential energy of the system. Is equals to the internal energy of the system. The total change in the energy of the system is equals to the internal energy. So I can say that the first law of thermodynamics for a stationary system can be written by Q minus W is equals to delta U. For a stationary system, the change in kinetic energy and the change in potential energy are zero. So when we apply the first law of thermodynamics, for a stationary system, Q minus W is equals to delta U. Q minus W is equals to delta U, or I can say that del Q minus del W is equals to du. Del Q minus del W is equals to du. Del Q minus del W is equals to du. Is this clear? Del Q minus del W is equals to du. Is this clear? Okay, sir. Sir, now for a simple compressible stationary system. Sir, what is simple compressible system? The system for which the electrical work and shaft work will be zero. The system for which the electrical work and shaft work will be zero. So your electrical work and shaft work will be zero. So the total work will be equals to the displacement work, and stationary system, that means total energy change will be equals to the internal energy change. So we can say that the first law will be given by Q minus WD will be equals to delta U. Q minus WD will be equals to delta U, or you can say that del Q minus del WD will be equals to du. Del Q minus del WD will be equals to du. Okay, sir, very good. And now your favorite equation. For a simple compressible stationary system undergoing an internally reversible process. for the simple compressible stationary system undergoing an internally reversible process. You know that very well. Simple compressible system, that means simple compressible system, that means W will be equals to the displacement work. Stationary system, that means change in energy of the system will be equals to the change in internal energy, and internally reversible means your displacement work will be given by integration of PdV. Remember this, internally reversible, that means your displacement work will be given by integration of PdV. And now I can say that del Q will be equals to du plus PdV. Now this is your favorite equation. That del Q will be given by du plus PdV. Tell me, del Q will be given by du plus PdV. Is this clear, everyone? Boliye. Clear, sir. Sir, now we will be discussing the heat transfer for the different processes. We will be discussing the heat transfer for the different processes. We will be discussing the heat transfer for different processes. For a constant volume process, when we apply the first law of thermodynamics, that is del Q, this is D cross, this is D cross. Don't see this, ये D नहीं है, ये D cross है. So del Q will be equals to du plus PdV. So as your PdV is equals to 0 for a constant volume process, PdV, that is your change in volume, will be equals to 0. Your del Q will be equals to du. Your del Q will be equals to du. So this can be given by mCv delta T. So remember the statement, for any gas undergoing an constant volume process, del Q is equals to mCv delta T. Remember this, for any gas undergoing a constant volume process, del Q will be given by mCv delta T, and for an ideal gas undergoing any process, your heat transfer will be given by mCv delta T. Is this clear? The change in internal energy for an ideal gas undergoing any process will be given by mCv delta T. Is this clear? Is this clear? Is this clear, everyone? Chaliye. Moving ahead, now constant pressure process. Constant pressure process, once again, pressure is equals to constant. Let's apply this equation. Del Q will be equals to du plus PdV. Can I write this as, you can say, we know that very well, your VdP, your differentiation of PV will be written as, PdV plus VdP, will be written as PdV plus VdP. So can I write this as PdV plus VdP? Now here dP will be 0, here dP will be 0, so can I write this as du plus differentiation of PV, because your VdP is 0, so I can write this as PdV equals to dPV. Can I write this? So I can say that your del Q will be equals to D of U plus PV, that is your DH. That means for an ideal gas undergoing any process, you can say constant pressure process, your heat transfer will be given by mCp delta T. For ideal gas, it will be given by mCp delta T. Any doubts with this? बोलिए बच्चा लोग, any doubts with this? चलिए. Now for an isothermal process, directly going on to the formula, your change in internal energy is 0. We have not discussed the work transfer formula. So we will have to discuss first of all the work transfer formulas. So बच्चा लोग, what you feel? We should take a break. Okay, I will be back within some minutes. Okay, so let's take a break. Okay, कितनी देर में मिले? We will be live by what time should I come back? 1:50. We will be live by 1:50. Okay, 1:50 is, I think 1:45, 1:50 I will be back. 1:45, 1:50 I will be back. Is this clear, everyone? Pushpendra, Guru, Nitish, everyone, I want everyone back. Okay, I will be back by 1:40 or 1:50. Okay, is this clear? I will be back on time. So chaliye, let's meet within some minutes, within half an hour nearly. It's already 1:15. We have completed 2 hours, and when we will be completing up to 5, we will be taking the session. If everything is left over, if anything is left over, I'll be taking that on to 15th. I will be taking that on to 15th. Okay, चलिए now चलिए. चलिए बच्चा लोग. So we will be meeting at Okay guys, I hope am I audible? Good afternoon to all the bacha log, and once again I welcome you to this India's largest digital learning platform Unacademy. Hi, this is SHAILESH VAIDYA again, and now we are going to complete thermodynamics in our proper way. Good afternoon bacha log. So before ending the session we were on to this slide where I told you कि अपन लोग इसकी बात करेंगे बट थोड़ी देर बाद. ओके अपन लोग इसकी बात करेंगे बट थोड़ी देर बाद. We'll be having tea also with this. ठंडी बहुत है. So we'll be continuing this now. Work is done by the system if the sole effect onto the surrounding. What is the definition of thermodynamic work? Sole effect onto the surrounding, everything external to the system could be raising of weights. Now the weights can be real or imaginary. work is done by the system if the sole effect on the surrounding, that is everything external to the system, could be raising of the weight. You can say raising of the weight. The weights can be real or imaginary. The weights can be real or imaginary. So this is the definition of thermodynamic work. Now there are some important sign convention. First of all, for you can say work done on the system is considered to be negative. Now compression work is work done onto the system, and expansion work is work done by the system. So work done by the system is taken as positive, and that's why expansion is taken as positive. Work done on the system is, you can say, taken as negative, and that's why the compression system work is taken as negative. Okay, what is heat interaction? Sir, heat and work both are energy in transit or boundary phenomena. Understand this very well. Heat and work are both the energy in transit or the boundary phenomena, but heat interaction occurs due to temperature difference, and work interaction occurs due to, you can say, any of the driving force except the temperature difference. Heat and work are both the energy in transit. Heat and work are both energy in transit. Okay, heat occurs due to the, you can say, heat transfer occurs due to the temperature difference, and work transfer occurs due to any of the driving force except the temperature difference. Okay, sir. Sir, sign convention for the heat interaction. Sir, heat added to the system. Heat that is added to the system is taken as positive, and heat rejected from the system is taken as negative. Always remember, heat added to the system is positive and heat rejected from the system is negative. Okay, sir. Now, first of all, we will be discussing about the closed system work or non-flow work. So, how do we calculate the closed system work? Sir, when you project the process of PV diagram onto the volume axis, the area under the curve of the PV diagram projected onto the volume axis will be giving me the work done. The area under the PV diagram projected onto the volume axis will be giving me work done. Now, the area, this can be written as your displacement work will be integration of PdV. So remember this is the formula for closed system work. ये अपन लोगों ने बात कर चुके हैं. I'm giving you you can say revising the things in a different way, and now actually we are discussing the work done for different systems. Okay, sir. Now, open system work. Sir, open system work is the, you can say, area under the PV diagram projected onto the pressure axis. Open system work is area under the PV diagram projected onto the pressure axis. So it is given by minus of integration VdV. So VdP. Remember this closed system work, or sometimes it is also called non-flow work. It is integration of PdV. Open system work or steady flow work, it is given by minus of integration of VdP. Is this clear, everyone? I hope this is pretty clear. चलिए आगे बढ़ते हैं. Okay, आगे बढ़ते हैं. Let's move ahead. Now, different, you can say, control volume work. Different your non-flow work or closed system work. Different formulas for non-flow work or closed system work. ठीक है सर. फर्स्ट ऑफ ऑल कांस्टेंट वॉल्यूम वर्क. सर, एरिया अंडर द पीवी डायग्राम विल बी जीरो. वी विल बी गेटिंग अ लाइन. Your dV is equals to 0 because volume is constant, and that's why your work done, your displacement work for a constant volume process is 0. Physically, मैंने आप लोगों को पहले बता दिया है that displacement work for rigid container, that means closed volume container, is constant volume container is always 0, and this is the mathematical expression because as dV is 0, so your PdV will also be equals to 0. Is this clear? Constant pressure work, area under the PV diagram. Sir, it will be a rectangle. Rectangle क्या हो जाएगा? Pressure into, you can say, this will be pressure. This will be the value of pressure. See, you can see this. This will be the corresponding value of pressure. This will be the corresponding value of pressure. Let's say I'm telling it P. Pressure upon, you can say, pressure into this area. Means pressure into this portion, this area. So this will be V final minus V initial, or I can say that this will be V2 minus V1. So always remember the displacement work for a constant pressure process is given by P V2 minus V1 for any gas. The displacement work undergone by a constant pressure process by any gas is given by P into V2 minus V1. P into V2 minus V1. But we know that very well for an ideal gas, PV is equals to MRT. So we can say that the displacement work for an ideal gas undergoing a constant pressure process will be given by MR T2 minus T1 और एल्स NR बार T2 minus T1. ये आप लोग कोई भी गैस के लिए अप्लाई कर सकते हो and this one can be applied for the ideal gas only. Understand the difference. This can be applied for ideal gas only and this can be applied for any gas. Is this clear? Is this clear everyone? Is this clear? चलिए. Now isothermal work. Sir, temperature is equals to constant for any gas and PV is equals to constant only for ideal gas. Temperature is equals to constant for any gas and PV is equals to constant for ideal gas. Okay, sir. Sir, the displacement work will be given by integration 1 to 2 PdV. सर यहां से P क्या हो जाएगा? P will be nothing but constant upon volume. अच्छे से सुन लो, P will be nothing but constant upon volume. इंटीग्रेशन करोगे, you will be getting integration of 1 upon V as ln V and you will be getting this as C ln V2 by V1. C ln V2 by V1 and this can be written as C ln P1 by P2. Because we know that for isothermal process, P1 upon P2 is equals to V2 upon V1. So there are two formulas that displacement work for an ideal gas, you can say undergoing an isothermal process. This is for an ideal gas undergoing an isothermal process. It is given by C ln V2 by V1 and C ln P1 by P2. C ln V2 by V1 and C ln P1 by P2. अब C की वैल्यू क्या आ सकती है? सर C is equals to P1 V1. यहाँ पे देख लो, C is also equals to P2 V2. C is also equals to MRT because PV is equals to MRT and C is also equals to NR bar T. So बच्चा लोग ये चारों को you can use with this formula 4 formulas. इन चारों को you can use with this formula 4 formulas. So total there are 8 formula for calculating the displacement work for an isothermal process. Ideal gas undergoing an isothermal process. For an ideal gas undergoing an isothermal process, in total there are, you can say, 8 formulas according to the data given. According to the data given to you. According to the data given to you. Is this clear? Is this clear everyone? I hope everyone is getting this. Okay, so C ln V2 by V1, C ln P1 by P2, C is equals to P1 V1, C is equals to P2 V2, C is equals to MRT, C is equals to NR bar T. Okay, sir. Sir, for an adiabatic process, perfect gas के लिए directly writing this P1 V1 minus P2 V2 upon gamma minus 1. P1 V1 minus P2 V2 upon gamma minus 1 and this is also equals to MR T1 minus T2 upon gamma minus 1. MR T1 minus T2 upon gamma minus 1. So this is the formula. ठीक है सर. सर फॉर अ पॉलीट्रॉपिक प्रोसेस गामा की जगह n आ जाएगा. सो इट इज P1 V1 minus P2 V2 upon n minus 1 and MR T1 minus T2 upon n minus 1. Just give me a minute. Yes, everything is fine. Am I audible? Please confirm if I'm audible. Yes, everything is fine. Am I audible? Please confirm if I'm audible. Yes. Okay, very good. So P1 V1 minus P2 V2 upon n minus 1 upon, and this is also equals to MR T1 minus T2 upon n minus 1. ठीक है sir? This is clear. Now let's discuss about the open system work or steady flow work. Let's discuss about the open system work or steady flow work. Sir, what is open system work or steady flow work? First of all, the displacement work is given by, you can say, integration of minus of VDP projected onto the pressure axis. Integration of minus of VDP projected onto the pressure axis. So first of all, for a constant volume process, your constant volume work in open system, which is also known as steady flow work, will be non-zero. ध्यान से देख लो, for an open system constant volume work will be non-zero. Constant volume work is zero only and only for a closed system. ये चीज बहुतों को पता ही नहीं होती है. How beautifully we can solve this. If a question is coming from this topic, you will be making big blunders. You will be making big blunders. So this will be given by minus of V P final minus P initial. Remember this. This will be given by minus of P minus of V P final minus P initial. Minus of V P final minus P initial. Okay, sir. Sir, constant pressure work for an open system is zero. That means the control volume work for a constant pressure process is zero. Control volume work for a constant pressure process is zero because pressure is constant. The area projected onto the pressure axis will be zero. The area projected onto the pressure axis will be zero. Sir, isothermal process के लिए I have already told you that the displacement work is equals to open system work, that is integration of PdV is equals to minus of integration of VdP. It is equals to minus of integration of VdP. अरे वाह, बच्चा लोग all are there. Very good. Now, for you can say isothermal work, same formula will work. That means same formula will work for the open system also. Same formula will work for the closed system also. Same formula will work for the open system also, and same formula will work for the closed system also. That is C ln V2 by V1, C ln P1 by P2, where C is equals to P1 V1, P2 V2, MRT and NR bar T. Is this clear, everyone? Now, for adiabatic process, understand this very well. Just giving you the final conclusion that your open system work for an adiabatic process is gamma times the closed system work. Open system work for an adiabatic process is gamma times the closed system work. Your open system work for an adiabatic process is gamma times the closed system work. It is the gamma times closed system work. That means I can write gamma into P1 V1 minus P2 V2 upon gamma minus 1. और MR T1 minus T2 upon gamma minus 1. So ये remember करना पड़ेगा. You have to remember this for the examination. That for, you can say, an ideal gas undergoing an adiabatic process, open system work done is gamma times equals to the closed system work done. Open system work done is equals to gamma times the closed system work. Okay, sir. Polytropic work, sir. Polytropic work is also same. Your open system polytropic work is n times the, you can say, closed system polytropic work. Open system work done is equals to n times the, you can say, closed open system work is equals to n times the closed system polytropic work. Is this clear? Is this clear? So these formulas I have already given to you. These formulas I have already given to you. Okay. Now we will move on to the heat interaction. Let's jump on to the heat interaction. So this was the case. Sir, for an isothermal process, I had told you that heat interaction will be equals to the work interaction. For an isothermal process, I had clearly told you that heat interaction will be equals to work interaction. So formulas will repeat. So formulas will repeat because internal energy change for an isothermal process, ideal gas undergoing an isothermal process, is zero. Internal energy change for an ideal gas undergoing an isothermal process is zero. Okay, sir. For an adiabatic process, heat interaction is zero. For an adiabatic process, heat interaction is zero. But for an polytropic process, heat interaction is given by gamma minus n upon gamma minus 1 into the work done by the closed system. Remember this formula. Heat interaction for a polytropic process is given by gamma minus n upon gamma minus 1 into the work done by closed system. Are the formula clear? I hope now you are clear with the difference between the open system work and closed system work. How many of you got the concept very clearly? How many of you got the concept very clearly? Tell me, bachcha log. Open system work and your closed system work. Tell me, how many of you have got this properly? Clearly, sir. समझ में आया? मजा आया? चलिए, I hope you enjoyed this. Now, drawbacks of the first law. So the point is, sir, first law was qualitative. First law was, quantitative. The first law was quantitative. According to the first law, heat transfer can take place from, you can say, high temperature to low temperature, or else from low to high also. Heat transfer can take place from high to low, low to high. First वाले को कुछ नहीं पता था. First law बोले मेरे को फर्क नहीं पड़ता. Heat interaction is taking place from high temperature to low temperature. But it was the second law that was qualitative. The first law was quantitative, and second law is also called directional law because it defined that there is a high grade energy and there is a low grade energy. Very good, thank you very much, Rakesh. There is a high grade energy and there is a low grade energy. Sir, high grade energy means, now what is a high grade energy? Sir, 100% of high grade energy can be converted into the low grade energy. 100% of the high grade energy can be converted into low grade energy, but 100% of low grade energy cannot be converted into high grade energy. But 100% of the low grade energy cannot be converted into high grade energy. Is this clear? So heat is always low grade energy. ऐसा क्यों sir? How to get the PDF? Okay, I will tell you. मैं आपको Google Drive link दे दूंगा राकेश. Otherwise you can connect with me. मैं ग्रुप में आपको पोस्ट कर दूंगा. मैं कोई भी स्पेशल क्लास, आप 10 बजे आज मैथ्स की क्लास में आ जाइए, मैं आपको लिंक प्रोवाइड कर दूंगा जहाँ पे पीडीएफ मिल जाएगी ना. राकेश, आप 10 बजे की स्पेशल क्लास में आ जाइए हमारी. आई विल प्रोवाइड यू द लिंक फॉर, यू कैन से, डाउनलोडिंग दिस पीडीएफ. ओके, जस्ट गिव मी अ मिनट टू सेटल डाउन प्रॉपर्ली. ओके, एम आई ऑडिबल नाउ? राकेश, आप आ जाइए 10 बजे अनअकैडमी लर्निंग ऐप पे. मैं आपको लिंक प्रोवाइड कर दूंगा. यहाँ पे मैं लिंक कमेंट नहीं कर पाऊंगा. गूगल ड्राइव की लिंक ना, आई विल नॉट बी एबल टू कमेंट, तो वो मैं आपको भेज दूंगा. ओके, इज दिस क्लियर राकेश? ओके, चलिए. सो नाउ वी आर वेरी क्लियर that heat is a low grade energy. Sir, low grade energy means heat cannot be converted into work. 100% heat cannot be converted into work. Whenever you are converting heat into work, there is always a loss of heat. There is always a loss of heat, but you can convert 100% of work into heat. But you can convert 100% of work into heat. So work is a high grade energy and heat is a low grade energy. Is this clear? Work is a high grade energy and heat is a low grade energy. This was given by second law of thermodynamics. So second law of thermodynamics may, we have to go with the basic definition. First one, what is a source? Sir, source is a large body of infinite heat capacity which can supply heat without undergoing an appreciable change in temperature. But chalo, we have completed the basics of thermo, means first part. Then we have completed heat and work interaction. Then we have completed the basics of first law, which is connected to heat and work interaction. And now we are in the second law. Everything I am giving you systematically. Okay, and 99% of the questions will be solved with these notes. I can guarantee this. So source is a large body of infinite heat capacity which can supply the heat without undergoing an appreciable change in temperature, because when you are taking the heat from the source, its temperature will not change. So the body is like, you can say, sun, industrial furnace, and you can say constant temperature phase change from vapor to liquid. Why from vapor to liquid? In the condensation you are rejecting the heat. In the condensation you are rejecting the heat, and that's why it is an example of source. Remember the example: sun, industrial furnace, and phase change from vapor to liquid are the examples of source. Sir, what is the sink? Sir, sink is a large body of infinite heat capacity which can absorb the heat without undergoing an appreciable change in temperature. उसमें आप कितनी भी heat supply करते रहो, its temperature will not increase like your atmospheric air. But at present, due to the global warming, some of the temperature of our surrounding air is also increasing, but not at a very, you can say, very large rate. It is not increasing. So we can say that still our temperature of air will not increase. So rivers, sea, lake, ocean are considered to be the sink. These are the bodies which can absorb the heat without the change in temperature. And बच्चा लोग, the heat transfer from the source and sink is generally considered to be internally reversible. Okay, is this clear? Now Kelvin Planck statement. According to second law, we are having two statements. The first one is the Kelvin Planck statement. The second one is the Clausius statement. The first one is the Kelvin Planck statement, which is applicable to the heat engine, and second one is the Clausius statement, which is applicable to the refrigerator and heat pump, which is applicable to the refrigerator and heat pump. So what is the Kelvin Planck statement? Sir, it is impossible to construct a device operating in a cycle that will produce no effect other than the extraction of heat from the single reservoir and convert all of it into work. नहीं समझ में आया? सुनते अच्छे से. It is impossible to construct an engine operating in a cycle that will produce no effect other than extraction of heat from the single reservoir and convert all of it into work. मतलब आप लोग, you cannot remove the heat from the single reservoir and convert it into work because heat is a low grade energy. So obviously you will have to reject some of the heat to the lower temperature sink also. Obviously you will have to reject some of the heat to the sink also. That means basically you should have two reservoir. And बच्चा लोग, once in the interview the students were asked, is this diagram correct? They were given source का third example. Explain sir please. बच्चा, जब फेस चेंज होता है वेपर से लिक्विड पे, तो आप लोग क्या करते हो? कंडेंसेशन होता है ना वेपर से लिक्विड. यू आर रिजेक्टिंग द हीट. कंडेंसेशन में क्या होगा? यू विल रिजेक्ट द हीट. ओके, दैट्स व्हाई सोर्स से अपन लोग हीट को एब्जॉर्ब करते हैं, तो सराउंडिंग उससे हीट को एब्जॉर्ब करेगी. दैट्स व्हाई वी कैन से दैट इट इज एन एग्जांपल ऑफ, यू कैन से फेस चेंज. मींस इट इज एन एग्जांपल ऑफ सोर्स, बिकॉज सोर्स से वी वांट टू एब्जॉर्ब द हीट और वो कांस्टेंट टेंपरेचर पे हो रहा है. Condensation is always at constant temperature, removing the latent heat from the, you can say, given liquid. That's why. Okay, so the point is, bacha, this diagram is correct or not? This was the question. So in the diagram, what you are doing, you are absorbing the heat from this thermal reservoir and you are absorbing the heat from this thermal reservoir also. ये भी गलत है. You cannot absorb the heat from two reservoir. एक में से आपको absorb करनी पड़ेगी और एक में आपको reject करनी पड़ेगी. You should absorb the heat from one of the reservoir and you should reject. That means one should be the source and other should be the sink. Yes, it is totally wrong. That means your sigma W cannot be equals to QH plus QL. Is this clear, bacha? Your sigma W, this arrangement is also impossible. This arrangement is also impossible. And this arrangement is nothing but your perpetual motion machine of second kind. This machine is nothing but your perpetual motion machine of second kind, completely converting heat into work. And we know that very well. Heat is a low grade energy which cannot be converted 100% into work. Yes, sir. Now, the concept of heat engine. Now, the concept of the heat engine. So, bacha log, this is the diagram of heat engine where you are rejecting QH, you are actually absorbing, you are absorbing QH amount of heat from the source at temperature TH and rejecting QL amount of heat to the sink at temperature TL by converting it into some amount of useful work. Is this clear? You are absorbing QH amount of heat from the source, converting it into work and rejecting the, you can say, some amount of heat to the sink. So this is the actual diagram of your heat engine. So what will be your, according to the first law of thermodynamics, to a cycle, this is a cyclic device. So net heat interaction should be equals to net work interaction. Net heat interaction should be equals to the net work interaction. So heat added to the system, this heat engine is our system, will be positive, and heat rejected from the system, this QL will be negative, will be equals to the net work interaction. And thermal efficiency will be given by net heat interaction upon the heat supply, that will be QH minus QL upon QH, and this will be equals to 1 minus QL upon QH. 1 minus QL upon QH. And bacha log, this formula can be applied to reversible and irreversible heat engine both. Is this clear? Rakesh and all other students, Guru, then Pushpendra, then Shravan, everyone, are you clear with the concept of heat engine? पहले मुझे ये बताइए, are you clear with the concept of heat engine? Don't worry, I'll take one more marathon. If the topics are left, don't worry, I'll take one more marathon. But you should understand the things properly. The ultimate goal is you should understand the things properly. Is this clear? Is this formula clear? What was the difference in this diagram and this diagram? Is this clear? Very good, very good, very good, very good, everyone. Chaliye. Moving ahead. Now, this is the question that is asked in the examination when the heat engines are connected in series. What will be the combined efficiency of heat engine connected in series? What will be the combined efficiency of heat engines that are connected in series? See, I'm not going on to the derivation. Derivation आप लोग देख लेना. Combined efficiency of heat engines connected in series. Now, what is the rule for the heat engines connected in series? Sir, the sink for the first engine will be the source for the second engine. Remember this, sir. XC extra topic I will make separately in the special classes. Guru, in the special classes there are questions from molar, specific, volume and all are there. Na? I'll make this with the PYQs. For XC, na, we will have to focus on PYQs, but you can say 80 to 90% topics are there from this class only. There will be some 10 to 20% additional topics. Okay, there will be some 10 to 20% additional topics. I'll be taking that in the special classes because I need to write them more clearly. Okay, don't worry, that will be done. That will be done for sure. Okay, so what is the case? What is the case? Now, what is the combined efficiency of heat engine? Okay, combined efficiencies of heat engine in series. Combined efficiency of heat engine in series. So what is the condition for heat engine in series? Sir, sink for the first heat engine should be the source for the second heat engine. Sink for the first heat engine should be the source for second heat engine. So bachcha log, if eta 1 is the efficiency of the first heat engine and eta 2 is the efficiency of the second heat engine, then the combined efficiency will be given by eta 1 plus eta 2 minus eta 1 dot eta 2. Eta 1 plus eta 2 minus eta 1 dot eta 2. Eta 1 plus eta 2 minus eta 1 dot eta 2. बात समझ में आई? Not going on to the derivation. You can solve this very easily. Now we are jumping on to the Clausius statement. I hope Kelvin Planck statement अच्छे से छप गया होगा. Sir, it is impossible to transfer the heat in a cyclic process from low temperature to high temperature without any work from the external source. Okay. Now this is a my tea mug. ये मेरा चाय का कप है. Okay, if I'm keeping this over here, ये पड़ा है. Let's take this one, ये वाला. Our Unacademy cup, this one. Okay, so let's say if I'm having a coffee in this. Okay, if we are having the coffee in this, coffee. Now I'm keeping this over here. I've kept this over here. And let's say I'm just keeping the milk in it. I'm just pouring the milk in it. Will it get heat energy on its own? Can it get heat energy from its own? One thing is clear. Can it get its heat energy on its own? Can you tell me? Can it get its heat energy on its own? नहीं sir, ये खुद गर्म हो सकता है. No sir. You will have to supply some energy. You will have to supply some energy to it. You will have to supply some energy to it. Yes sir. That means for the heat interaction, one side it is possible. But second thing is, if I am keeping the coffee at a high temperature, it will reject the heat slowly. It will reject the heat slowly, and coffee will come in the temperature equilibrium to the surrounding. And coffee will come in the temperature equilibrium to the surrounding, and that's why you know there is a big confusion among the students. They will be asking you sometimes, maybe in the interviews, maybe in the exams also, they can ask you that which statement is giving the direction of heat transfer. Kelvin Planck statement or Clausius statement? Which statement is giving the direction of heat transfer? Can you tell me which statement is giving the direction of heat transfer? Kelvin Planck statement or Clausius statement? Kelvin Planck statement or Clausius statement? Tell me, Kelvin Planck statement or Clausius statement? Which statement is giving the direction of heat transfer? बोलिए बच्चा लोग, Kelvin Planck or Clausius? Clausius बोलो, कुछ भी बोलो. Kelvin Planck or Clausius? Very good, Shravan, very good, Guru. Clausius statement. So remember this very well. Both are the, you can say, sub statements of second law only, but the direction of heat transfer is given by Clausius statement. Remember this very well. The direction of the heat transfer is given by Clausius statement. So it is impossible to transfer the heat from, you can say, low temperature to higher temperature without the work from any external source. That means for transferring the heat from low temperature to high temperature, you will have to do some work. That means you can say AC cannot run on its own. AC cannot run on its own. This is the statement. So basically, let's discuss the beautiful concept of, your refrigerator and heat pump. Okay, most of the students are confused in the refrigerator and heat pump. Let's discuss this in detail. So first of all, understand the standard cycle of refrigerator and heat pump, and then we will be calculating the COP. Sometimes it is also called the energy performance ratio, EPR. COP को कभी कभी एनर्जी परफॉर्मेंस रेशियो भी कहा जाता है. This we will be discussing this in refri AC. Okay, on plus, बच्चा लोग on plus, I am bringing for you the revision course. Guru, you can attend this. I will be using this notes only on to for thermodynamics, but there we will be doing the problems. There we will do the problems also. Concepts, problem. It is starting from tomorrow 7 to 8. Starting from tomorrow 7 to 8 p.m. Okay, but there will be refri AC there. There will be IC engine. There will be power plant. Okay, so those who want to attend, they can come on plus. Okay, so what is the concept of refrigerator and heat pump? First of all, sir, for a refrigerator or heat pump, once again, it is a cyclic device. Once again, it is a cyclic device, and what you are doing, you are absorbing the heat from the lower temperature source. You are absorbing the heat from the lower temperature source when work is supplied to your refrigerator. When you are supplying the work to your refrigerator, it is absorbing the heat from the lower temperature source and supplying to the heat to higher temperature sink. Can you believe? Supplying the heat to higher temperature sink. Let's repeat my statement. When the work is given to the refrigerator or heat pump, it is absorbing the heat from lower temperature source. Absorbing the heat from lower temperature source and supplying the heat to higher temperature sink. And supplying the heat to higher temperature sink. Are you clear with this? First of all, tell me, are you clear with this? Absorbing the heat from the lower temperature source and supplying the heat to higher temperature sink. Now, what is the point? What is the point? That over here, the low temperature source for the refrigerator and for the AC will be different. The lower temperature will be different. So one thing is very clear, that they can ask you, sir, are lower temperature sources possible and higher temperature sink possible? Yes, sir. ये condition ये बोलती है that source can be a lower temperature source and sink can be a higher temperature sink also. One thing is pretty clear. Okay. Now the point is, just imagine your refrigerator, your fridge. Just imagine your refrigerator, your fridge or your AC. What is your area? Why do we use our AC? I'm sitting in my room. Let's say it is a summer in India. I'm from Gujarat, where the temperature reaches up to 50 degrees centigrade normally, 45 plus on an average in the, you can say, mid of summer. In the mid of summer, the temperature is 45 degrees centigrade. Okay, so what it will be doing? It will be rejecting the heat. The surrounding is at a higher temperature. My system is at comparatively lower temperature. So it will be absorbing the heat from the system. That means it will be absorbing the heat from the room, which is comparatively at the lower temperature to the surrounding, absorbing the heat and throwing the heat outside, throwing the heat to the outside, which is at higher temperature. That is our surrounding. Are you getting this? Our room is at a lower temperature from which we are absorbing the heat and we are supplying the heat to the surrounding which is at the higher temperature. Is this clear? So this is first of all the concept of refrigerator. Okay, sir, don't worry about COP. Let's first understand the concept of heat pump. Now, what is heat pump? I'm going to, you can say, Jammu and Kashmir for vacation. I'm going to, you can say, some countries like Russia, America, where the temperature in the mid of winter goes up to, you can say, 0 or even below 0. 0 or even below 0. So once again, the cycle is same. I will be absorbing the heat from the lower temperature sink. When I supply the work to the heat pump, it will be absorbing the heat from the lower temperature sink and supplying the heat to the higher temperature source. But here, in case of winter, now understand this very well. In case of winter, our room temperature is comparatively higher than the outside temperature. Outside temperature is lower. In the summer, in the winter season, बाहर का टेम्परेचर ठंडा होता है. You go to Jammu and Kashmir, you go to out of India countries like where the temperature is below 0 degree centigrade. At present in our area in Gujarat, the winter is also very high. I am staying in Kutch, the winter is also very heavy. So what is the case? What is the case? That in the midst of winter, the surrounding temperature is low. The surrounding temperature is low. So bachcha log, what we will be doing, we will be rejecting, we will be absorbing the heat from the surrounding. Our heat pump will be absorbing the heat from the surrounding and will be supplying the heat to the room. So here this is our surrounding, the sink is our surrounding, and our source is your source is, sorry, the surrounding, and our sink is the room. Are you clear with the basic difference? The cycle is pretty same. The cycle is pretty same, but only the area of interest changes. The cycle is pretty same, only the area of interest changes. Is this clear? Is this clear, everyone? Okay, sir. Now let's discuss about COP. What is the desired effect in case of refrigerator? So desired effect is the low temperature room or low temperature refrigerating space. The desired effect is low temperature room or refrigerating space. So COP is given by desired effect upon work input. COP is given by which one is source, sir? Let me write this for you. Actually, I disconnected the writing pad. This one is the sink. Actually, sorry, this should be the source. This is a mistake. This should be the source. This is just a writing mistake. This is my source. Okay, this is my source. Are you clear? Always remember, in case of, you can say, refrigerator and heat pumps, lower temperature side will be source. This is just a writing mistake, and this will be your sink. The room will be your sink. High temperature sink. Are you clear now? Actually, I disconnected my writing pad because I had some charging problem with my phone. This is just a small writing mistake. Okay, thank you for noticing this. So what is COP, bacha? The COP of refrigerator or heat pump is given by the desired effect. The desired effect upon work input. Sir, what is the desired effect? In case of refrigerator, the lower temperature room or fridge is our desired effect. So COP of refrigerator is given by QL upon W. COP of refrigerator is given by QL upon W, and COP of heat pump, the area of interest is our room, higher temperature side. Our area of interest is to keep our room warm. मुझे room को गर्म रखना है. क्या करना है? मुझे रूम को गर्म रखना है. यहाँ पे मुझे क्या करना है? सर, बर्फ जमानी है, रूम को ठंडा रखना है. These are my goals. What are our goals of life? I want to crack the GATE examination. So that's why we will be calculating our COP. Okay, so COP of the heat pump will be QH upon W. Is this clear, bacha log? Any doubts in these two concepts? Most of the students are not very clear about these concepts. Anyone having any doubts? Anyone having any doubts? Tell me. Anyone having any doubts? Okay, chaliye. Everyone should comment. By only Guru is commenting. What about others? Don't sleep in the class. After the lunch, I know many of you are sleeping. That's why I did not do the lunch. I just had a tea and then I came. Okay, chaliye. So I hope you are clear. The basic difference between the refrigerator and heat pump is the desired effect. In the refrigerator, our desired effect is the lower temperature source, and in the heat pump, the desired effect is the higher temperature sink. Lower temperature source, that is QL, and you can say in heat pump it is higher temperature sink. No doubt. Kya baat hai? Now, what is the relation between the COP of heat pump and refrigerator? Sir, derivation sabko aata hai. Derivation sabko aata hai. Directly giving you the result. Repeat with me. COP of heat pump is equals to COP of refrigerator plus 1. COP of heat pump is equals to COP of refrigerator plus 1. COP of heat pump is equals to COP of refrigerator plus 1. COP of heat pump is equals to COP of refrigerator plus 1. COP of heat pump is equals to COP of refrigerator plus 1. Now this one is also interesting. So relation between the thermal efficiency and COP. Relation between the thermal efficiency and COP. Sir, COP of heat pump is equals to the 1 upon the efficiency of heat engine. COP of heat pump is equals to 1 upon the efficiency of heat engine, and 1 upon efficiency of heat engine will be equals to COP of refrigerator plus 1. Quite clear. 3 formulas. COP of heat pump is equals to COP of refrigerator plus 1. COP of heat pump is equals to 1 upon the efficiency of heat engine, and 1 upon efficiency of heat engine is equals to COP of refrigerator plus 1. Quite, you can say, easily clear with you. I hope this condition is pretty clear. Okay, can we move ahead now? Chaliye, tell me. Now, Carnot cycle. Okay, we'll be discussing about the processes. First of all, the processes are, always remember, first of all, Process 1 to 2 is isothermal expansion. It is isothermal expansion. Then process 2 to 3 is isentropic expansion. Don't say it heat addition generally. Don't say it heat addition. I'll tell you the reason later on. Okay. Process 3 to 4 is isothermal compression in a Carnot cycle, and process 4 to 1 is your isentropic compression. But bachcha log, what is the correct definition? I think heat pump. हीट पंप्स के डायग्राम में डायरेक्शन मिस्टेक है सर? नहीं है बच्चा? इज देयर एनी मिस्टेक? एनीवन फेसिंग द सेम? गुरु क्या लगता है, मिस्टेक है क्या? गुरु, पुष्पेंद्र देखो तो। हाँ, सोर्स एंड सिंक की वो मेरी लिखने की गलती थी, आई हैड करेक्टेड इट। सोर्स एंड सिंक की थी। दोनों का डायग्राम सेम होता है बच्चा, ऑलवेज रिमेंबर। रेफ्रिजरेटर और हीट पंप का डायग्राम एकदम सेम होता है। देयर वर्किंग साइकिल इज सेम, बट ओनली द डिजायर्ड इफेक्ट इज डिफरेंट। Their working you can say cycle is same. Okay, I'm reading your comments from this side. My phone is kept over here, so I'm not regularly seeing your comments. Okay राकेश, कोई गड़बड़ नहीं है, चिंता मत करो। Okay राकेश, कोई गड़बड़ नहीं है, चिंता मत करो। Okay, is this clear? हाँ, it's correct, pretty correct. Okay, the only change is बच्चा the desired effect. ठीक है राकेश, the only change, हाँ, source and sink was by mistake. I had written sink over here, which is wrong, so I corrected it. By mistake I had written sink over here. Okay, that's just a writing mistake. Sometimes happen with me. I do some silly mistakes always. Habitual of doing silly mistakes. Okay, Rakesh, is this clear? दोनों की साइकिल सेम है, मैंने इसलिए बोला हीट पंप और रेफ्रिजरेटर की साइकिल सेम है, द डिजायर्ड इफेक्ट इज ओनली डिफरेंट। Can you hear the song in the background? Should I close the door? Please confirm. Can you hear the song in the background? Can you hear the song in the background? Should I close the door? Please confirm. Can you hear the song in the background? Can you hear the song in the background? Should I? Okay, then good. Sometimes it's difficult to say no song. Acha. Someone is playing the song in the neighborhood. That's why I thought. Okay, actually, that's why I sit on the first floor. No song is being heard, then very good. Okay, that's what I wanted. I can hear actually the voice you can say control is there in these softwares now, but it's very good to check once. Okay, so Carnot cycle, what will I say? Sir, process 1 to 2 is reversible, internally reversible isothermal. This is heat addition. Internally reversible isothermal heat addition. Then it will be internally reversible adiabatic expansion, internally reversible isothermal heat rejection, and internally reversible adiabatic compression. Is this clear? These are the 4 processes of Carnot cycle. Now, why Carnot cycle is not practical? You know, the point is isothermal process need to be very slow. Isothermal process need to be very slow and adiabatic process need to be very fast. Now, how can you have both the processes together? Like your piston should have speed modulation, speed, slow. Speed, slow, not possible. That can create an infinite jerk in your piston cylinder assembly, and that's why Carnot cycle is not practical. That's why Carnot cycle is not practical. Is this clear? Carnot cycle is not practical. So what are our important points from the Carnot cycle? First of all, the efficiency of the Carnot cycle only for the reversible engines. This I will tell you why this is for reversible engine. बच्चा, this is given by 1 minus TL upon TH. ये formula with the temperature limits is only and only for the reversible engine. Don't apply this everywhere. So the efficiency of the Carnot engine is given by 1 minus TL upon TH. The efficiency of the Carnot engine is given by 1 minus TL upon TH. Okay, sir. The efficiency of, you can say, reversible and irreversible, both the engines are given by 1 minus QL upon QH. 1 minus QL upon QH. Okay. One thing is, this is your expansion ratio. This is your expansion ratio. I'll be telling this in detail. You can say in the discussion of, you can say, application parts like IC engine, I'll be telling you. So this is another form of, you can say, efficiency of Carnot engine. You can remember this. TL upon TH is given by 1 upon e raised to the power gamma minus 1. Just remember this. कभी कभी पूछ लेते. You know, GATE is habitual of twisting the question onto the words. वो words में थोड़ा तोड़ मरोड़ के दे देगा. So in place of TL upon TH, you can put this. So the efficiency formula will be 1 minus 1 upon e raised to the power gamma minus 1. In special class? Yeah, application will be completed in plus only. Guru, application part will be completed in plus and we'll be doing the questions in special classes. Okay, application part will be completed in plus, and if possible, I'll take the, you can say, marathon on YouTube also. If possible, I'll take the marathon on YouTube also for referee AC, IC engine and power plant. HMT not planned at present, HMT not planned at present, but I'll plan that on. Okay, actually the point is, I'm first of all focusing on to the subjects which I have already taught on plus or somewhere, so I'm having the notes ready, because now making the short notes is slightly time consuming. To be honest, I've completed the revision of strength of material, I've completed the revision of casting, I've completed the revision of welding, thermodynamics, then I completed referee AC, psychometry is left in the special classes. I completed so many topics on plus and special classes, I completed on plus casting, mechanics, strength of material, theory of machine, vibration separately. Then I completed metal forming. After that, I completed practice course on for theory of machine, practice course on for strength of material. These on plus. On special classes, I have taught casting, welding, metal cutting, metal cutting and metrology. 4 subjects in special classes. On YouTube also, I have taught casting, welding, and metal cutting. Thermo not completed. Thermo, these are my ISRO course notes. Okay, thermo I have not taken. Actually, in the special classes, before May, I had completed up to second law. Through the special classes, I had completed up to second law. But these notes are of my, you can say, ISRO course. They were available with me. I have these notes, so I am using these notes over here. These notes are all ready, so it is easier for me. Okay, chalo, let's move ahead. We'll be discussing everything in the end. We need to target everything up to 5 p.m. today. If we are not completing the topic, if we are not completing the thermo completely, we'll have another marathon also within 2-3 days. Not tomorrow and on 14th, not tomorrow and on 14th, but we'll be having that after, you can say, 15th or 16th. Okay, I hope this is clear. Now, Carnot theorem. Now, important portions are coming. You can surely expect 1 or 2 questions from these topics. First of all, what is the Carnot theorem? So, Carnot theorem says that within the same temperature limits, the efficiency of reversible engine is always more than the efficiency of the irreversible engine. The efficiency of reversible engine is always more than the efficiency of irreversible engine. First point. So second point is the reversible engines between the same temperature limits will be having same efficiency. The reversible engines between the same temperature limits will be having same efficiency, like Carnot, Stirling and Ericsson engine operating between the same temperature limits, their efficiency will be same. Carnot, Stirling and Ericsson engine operating between the same temperature limits, their efficiency will be same. Their efficiency will be same. So always remember, the efficiency of irreversible engine will always be more than the efficiency of the irreversible engine operating between the same temperature limits. Now from this I can say that your efficiency is work output upon heat supplied. So heat supplied is, let's say, same for both the engines, whether it is a reversible engine or irreversible engine. So I can say that the work output of the reversible engine will also be more than the work output for the irreversible engine operating between the same temperature limits, and you can say same heat supplied. Operating between the same temperature limits and same heat is supplied. See, condition is very important. So let me repeat this for you. Sir, according to the Carnot theorem, efficiency of the reversible engine is always more than the efficiency of the irreversible engine operating between the same temperature limits. Efficiency of the reversible engine is more than the efficiency of the irreversible engine operating between the same temperature limits. Okay, sir, very good. Sir, your work output for the reversible engine is more than the work output of the irreversible engine when the heat supplied to both the engines is same, and reversible engines operating between the same temperature limits will have same efficiency. 3 statements from this. Okay, now thermodynamic temperature scale. Lord Kelvin was the pioneer on giving this. Lord Kelvin was the one who worked on to this, and he gave the thermodynamic temperature scale that QH upon TH is equals to QL upon TL. QH upon TH is equals to QL upon TL. QH upon TH is equals to QL upon TL. Is this clear first of all? QH upon TH will be equals to QL upon TL. Okay, sir. Here the temperature should be in Kelvin. So now using the thermodynamic temperature scale, can I say that first of all, the efficiency of heat engine is given by 1 minus QL upon QH. This formula is applicable to reversible. What does it mean, sir? That means we are the heat transfer. You can say the ratio of heat supplied upon heat reject is always proportional to the temperature at which the heat transfer is taking place. The ratio of, you can say, you can say heat supplied to the heat rejected will always be, you can say, in relation with the temperature at which the heat transfer is taking place. Are you getting my point? The ratio of, you can say, heat supplied upon heat rejected will always be in proportion to the temperature at which this heat transfer is taking place. Okay, is this clear? And this is for the reversible process only. This is for the reversible processes only. Now is this clear, Guru? Is this point clear now? Is this point clear, bacha? Now clear, sir. Okay. See, there are some doubts I know in this thermodynamics. Everyone is having some slight glimpse of doubt. So first of all, we know that the efficiency of the heat engine is given by 1 minus QL upon QH, and this formula is valid for reversible and irreversible engine both. This formula is valid for reversible and irreversible engine both. Now the point is, if your engine is reversible, so I can directly put the thermodynamic temperature scale relation QL upon TH. Sorry, QL upon QH will be equals to TL upon TH, and this formula is valid for reversible heat engine only. This formula is valid for reversible heat engine only. This formula is valid for reversible heat engine only. Is this clear? Is this clear? And this was the question. It is impossible to achieve the absolute zero temperature. Sir, absolute zero temperature means your TL will be zero. Understand this very well. For a reversible engine, the absolute zero temperature means that your TL will be zero. And TL0, that means your efficiency is 100%, and efficiency 100% is impossible. Efficiency 100% is impossible. This is the violation of the, you can say, Kelvin-Planck statement. This is the violation of Kelvin-Planck statement. This is the violation of Kelvin-Planck statement. Is this clear? Is this clear? So this is the way you can say that achieving the absolute zero temperature is impossible. Achieving the absolute zero temperature is impossible. Is this clear? Okay, chaliye. Now this is the relation that I already gave you, that for a reversible heat engine, QL upon QH will be equals to TL upon TH. So you can write the efficiency of the reversible heat engine in the terms of temperature limit. You know, once in GATE, they gave you the temperature limits, they gave you the heat supplied, and they asked the efficiency of heat engine, and they did not mention whether the engine was the reversible heat engine or irreversible heat engine. You know, 50% of the student used this formula to find out the efficiency of irreversible heat engine because they were not aware about these things. Now this formula is applicable to both reversible and irreversible engines, but this formula is applicable only and only to reversible heat engines. So until and unless they are not mentioning in the question that the engine is reversible heat engine, you cannot use the formula. Please don't do these silly mistakes. You cannot use this formula until and unless they mention. You will have to use this formula only. आई होप दिस पॉइंट इज प्रीटी क्लियर. अगर आप लोगों को नहीं बोलता है कि सर रिवर्सिबल हीट इंजन है एंड दे आर गिविंग यू हीट सप्लाइड, यूज दिस फॉर्मूला. सी, दिस वाज द क्वेश्चन वेयर द स्टूडेंट मेड मिस्टेक. आई होप आफ्टर दिस वीडियो यू विल नॉट मेक दिस मिस्टेक. I hope after this video you will not make this mistake. Okay, sir. Sir, similarly, now this is a very important, you can say, concept. This is a very important concept. You can solve the many of the question. You know, they will be asking you heat engines in series. They will be asking you heat engine in series, and they will be asking you the heat supplied, heat rejected for the different you can say thermal reservoirs. Heat supplied and heat rejected to the thermal reservoirs, different thermal reservoirs. See, you watch this class. You watch this class. If possible, I will be bringing a marathon for the PYQs also. I will be bringing a marathon of PYQs also, either on this YouTube platform or in the special classes. So you will be clear about this. You will be clear about this, how the questions are coming. So what is the case? You can apply the thermodynamic temperature scale, and we can say that QH upon TH for the high temperature source will be equals to the medium temperature thermal reservoir. QM upon TM will be equals to QL upon TL. So बच्चा लोग, if they are giving you any temperature, any heat transfer value, you can calculate the unknown value without calculating the efficiency. आप लोगों को ये efficiency calculate करे बिना ये काम कर सकते हो. How quickly you can solve this? Are you getting the use of this? Are you getting the use of this, बच्चा? इसका use कैसे हो सकता है? I hope you are feeling the funda. How can you use this thing? इसको कैसे use कर सकते हो आप लोग? Yes or no? Tell me. Okay, so can we move ahead? Chaliye. Can we move ahead? Okay, now this is a very interesting question. This one is a very interesting question, sir. What they have asked? What they have asked, sir, your heat engine in series. Heat engine in series. So आप लोगों को ये तो पता है what is the heat engine in series? What is the heat engine in series? Now heat engine in series, you can say having same thermal efficiency. Heat engine in series having same thermal efficiency. So what will be the temperature of your, you can say, this reservoir, your middle reservoir? What will be the temperature of the middle reservoir? So when you are having same thermal efficiency, your temperature Tm is given by root of Th into Tl. Direct formula based question. Root of Th into Tl. Condition is heat engines should be in series. Reversible heat engine should be in series. Mark my words. Reversible heat engine connected in series and having same thermal efficiency. So Tm is given by root of Th dot Tl. Your Tm is given by root of Th dot Tl. Your Tm is given by root of Th dot Tl. Your Tm is given by root of Th dot Tl. Is this clear? Is this clear? Okay, sir. So second condition is same work output. Second condition is same work output. So when you are having same work output for the engines in series, your Tm will be given by Th plus Tl upon 2. Derivation is not important. Just remember the formula at present. Derivation is important, but not at present. And derivation is quite easy. But you should know two things. First of all, heat engines connected in series. Second thing is, first thing is reversible heat engine connected in series. I have mentioned this very clearly. Reversible heat engine connected in series. Same work output. This formula. Direct formula based question. Same thermal efficiency. This formula. I am making my words pretty clear. Direct questions will come from this topic. Now applying this for, you can say, reversible refrigerator. You know that for reversible, irreversible and reversible refrigerator, we can say that COP of the refrigerator is QL upon QH minus QL. But if I write the condition reversible refrigerator, then it will be given by TL upon TH minus TL. TL upon TH minus TL. TL upon TH minus TL. Is this clear? Is this clear? Okay, very good. Sir, reversible heat pump, sir, TH upon TH minus TL. I hope no doubts in this. Clear, sir, clear. Okay, so this is the difference between reversible and irreversible. So completed one more part, and now we are jumping on to Clausius inequality. Acha, entropy, I will be taking the important cases and formulas. But I will be discussing about the entropy in detail in one of the, you can say, sessions separately, because entropy requires around 2 to 3 hours for discussing it completely. Entropy requires 2 to 3 hours for discussing it separately. So I'll try my level best to cover up everything related to entropy. I'll cover up all the concept. Sir, what is X? Which X? It is any value. I had taken any constant. When you are doing mathematical relation, so you can take this as K, which will be cancelled out by taking common. It is any K, or you can say X value or something like that. Okay, any constant value which will be cancelled out later on. Just proving this, that your QH will be equals to XTH, not directly the temperature. Understand this very well. Whenever you are writing QH upon TH, let me write this for you. Whenever you are writing this as QH upon, you can say, I cannot write with the writing pad. Okay, just let me type this. I can type this. QH upon, got it? QL. Now this will, QH can never be equals to directly TH. It can never be written as equals to TH. Are you getting my point? This can never be written as equals to TH. It can never be written. Okay, this will not be directly equals to TH. It will be having some proportionate value. Okay, that is the only. Okay, I hope this is pretty clear. Okay, Clauses inequality, very important, very important, very important, बहुत important. What is clauses inequality? We have completed, I think, 3+ hours. We have completed 3+ hours, and I hope I am enjoying the session. I'm pretty enjoying the session. So cyclic integral of, you can say cyclic integral of del q by t greater than 0, then the, you can say, cycle is impossible. So cyclic integral of del q by t is equals to 0, then cycle is possible and it is an internally reversible cycle. Cyclic integral of del q by t is less than 0, then the cycle is possible and it is an internally irreversible cycle. Remember this: cyclic integral of del q by t greater than 0, impossible. Cyclic integral of del q by t equal to 0, cycle is possible, internally reversible. And cyclic integral of del q by t less than 0, cycle is possible, internally irreversible cycle. Enjoying the same? Okay, so now these questions are coming in the examination. These questions are coming. You can see the same diagram many times in the examination. Same diagram. They will be giving you a cyclic device which will be having generally more than 2 reservoirs. Generally having more than 2 reservoirs. It can be source, it can be sink, anything. But whenever you are having more than 2 reservoirs, please apply the Clauses inequality. Please apply the Clauses inequality. Remember this, to apply the Clauses inequality. Remember to apply the Clauses inequality. Okay, sir. Now you can see this. Now this is a cyclic device. Here, what we are having now, our system is taking heat from reservoir at temperature T2, and you can say taking heat from the Q1 amount of heat from the temperature T1 and rejecting heat to the reservoir 3 at temperature T3. So our cyclic device is absorbing Q1 amount of heat from the reservoir at temperature T1, Q2 amount of heat from the reservoir at temperature T2, and rejecting Q3 amount of heat to the reservoir at temperature T3. That means these two are source and this one is sink. So we cannot apply the normal efficiencies formula. This will be solved only and only by Clauses inequality. अच्छे से बैठ लो दिमाग में. अच्छे से बिठा लो दिमाग में. This will be solved by Clauses inequality only. This will be solved by Clauses inequality only. This will be solved by Clauses inequality only. Okay, sir. Sir, what is the case now? See this. Here, what will be the net heat interaction? So net heat interaction will be heat added to the system positive, heat rejected to the system negative. So this will be Q1 plus Q2 minus Q3. Q1 plus Q2 minus Q3. Q1 plus Q2 minus Q3. Is this clear? Q1 plus Q2 minus Q3. Okay, sir. Pretty clear. Q1 plus Q2 minus Q3. Just give me a minute. Okay, now case 1. Now let's say if you are having your net heat interaction as positive, अगर आप लोगों का ये sigma q की value positive आती है, now understand this very well, then obviously this is a heat engine. Obviously this is a heat engine. Sir, second case, if we are having the net heat interaction as negative, then obviously either it is refrigerator or heat pump. Remember this very well. If your sigma q is positive, then it is a heat engine. It is a heat engine. And if your sigma q is negative, then it is a refrigerator or heat pump. Then it is a refrigerator or heat pump. Let's understand this in detail. Let's understand this in detail. Okay, now there are two things. First of all, you will have to check the sigma q. If it is positive, heat engine. If it is negative, refrigerator. Now they will ask you the, you can say, type of device. The question that they will ask you, there are two possibilities. Either they will ask you the value of Q1, Q2, Q3, T1, T2, T3, anything. And secondly, they can ask you the type of device. So how you can find the Q1, Q2, Q3 or your temperature or your work interaction? They will be giving you your Q1, Q2 and Q3, and you have to use the relation. I will be doing the problems also, that your net heat interaction is equals to net work interaction. You can use this formula. But if they are asking the type of device, if they are asking the type of device, so case 1, let's say your heat interaction is positive, and cyclic integral of del q by t, your summation of heat interaction is positive and cyclic integral of del q by t is less than 0. That means it is an heat engine, but internally irreversible heat engine. Your net heat interaction is positive, but cyclic integral of del q by t is less than 0. So it is an internally irreversible heat engine. Can you understand this, bacha? Can you understand this? Second thing, if your net heat interaction is negative, but cyclic integral of del q by t is equals to 0. Negative means negative means refrigerator or heat pump, and equal to 0 means internally reversible refrigerator or heat pump. And the third case is your net heat interaction is positive and cyclic integral of del q by t is equals to 0, then it is heat engine, that is an internally reversible heat engine. I hope these cases are clear. Tell me, I hope these cases are clear. बोलिए बच्चा लोग. I hope these cases are clear. So this was the question that was asked in GATE 2016 for 2 marks. See this. This was a question that was asked in GATE 2016 for 2 marks. A reversible cycle. They have clearly mentioned a reversible cycle receives 40 kilojoule of heat from one heat source, okay, at temperature of 127 degrees centigrade, and 37 kilojoule of heat from another heat source at 97 degrees centigrade. So you can take any T1 or T2 at, you can say, any temperature and heat. The heat rejected, they are asking Q3 at 47 degrees centigrade. So you can directly use the formula that Q1 upon T1 plus Q2 upon T2 minus Q3 upon T3 is equals to 0. Are you getting my point? ये direct formula use करो. See, cyclic integral of del q by t will be nothing but q1 upon t1 plus q2 upon q2 minus q3 upon t3. 2 marks में ऐसा question. Can you believe? 2 marks में ऐसा question. बस ढूंढ लो. Calculation you will do, I will not do. Calculation you will do, I will not do. Okay, चलिए. So once again, Clausius inequality. You can say cyclic integral of del q by t equal to 0, internally reversible and possible. Cyclic integral of del q by t less than 0, internally irreversible, possible, and cyclic integral of del q by t greater than 0. It is impossible. ठीक है, चलिए आगे बढ़े. Okay, चलिए. Let's start. Now, let's leave that slide. यहाँ पे देखते हैं. Now understand this very well. Now slowly we are jumping on to the topic of entropy. With the Clausius inequality, entropy comes. With the Clausius inequality, we can understand the funda of entropy. Okay, so what is the case? Let's say we are having, you can say, 2 internally reversible cycles. Let's say you are moving from state 1 to 2 by path 1A2 and returning back by path 2B1 and 2C1. Understand? I'll take some time to explain you this in detail. We are moving from, you can say, state 1 to state 2 by path 1A2 and returning back from path, you can say, 2B1 and 2C1. All the processes are internally reversible because I have drawn them by solid line. As they are internally reversible, your cyclic integral of del q by t will be equals to 0. For, you can say, complete cycle 1A2B1 and 1A2C1, it will be cyclic integral of del q by t will be 0. That means cyclic integral ki jagah now integral of del q by t for process 1A2 plus integral of del q by t for process 2B1 will be equals to 0. Similarly, integral of del q by t for process 1A2 plus integral of del q by t for process 2C1 will be equals to 0. First of all, is this clear? Can I compare these two? When I compare these two, I get to know that your integral of del q by t integral of del q by t is same for the process 2b1 and 2c1. Sir, what is the conclusion? This integral of del q by t is known by the change in entropy. Remember, this delta S is given by integral of del q by t, entropy change. You know the formula that ds is equals to del q by t. This is for an internally reversible process undergone by a closed system. Why 0, sir? Why 0? Just now we told na, for internally reversible process, your integral of del q by t, cyclic integral of del q by t will be equals to 0. Okay, cyclic integral of del q by t equals to 0 according to the Clausius inequality. Net heat interaction change with the, you can say, temperature will be 0. Are you clear? I'm using this relation only because all these processes are internally reversible. All these processes are internally reversible. Are you clear now, Guru? Okay, chaliye. Now, this we have discussed. Now, case number two, I'm having one internally irreversible process. Okay. Now, case number two, I'm having internally irreversible process. Understand this very well. Internal, see, 1A2 is internally reversible. 2B1 is also internally reversible, but 2C1 is internally irreversible. Now, for an internally irreversible cycle, cyclic integral of del q by t is less than 0. Cyclic integral of del q by t is less than 0. So, integral of del q by t for process 1A2 plus integral of del q by t for process 2B1 is equals to 0. And cyclic integral of del q by t for process 1A2 plus integral of del q by t for process 2C1 is less than 0 because it is internally reversible. Sir, if any of the process of a cycle is internally irreversible, then complete cycle becomes internally irreversible, and we know that very well. For an internally irreversible cycle, cyclic integral of del q by t is less than 0. Cyclic integral of del q by t is less than 0. Is this condition clear? So can I say that integral of del q by t for process 1A2 plus integral of del q by t for process 2C1, that is your irreversible, will be less than reversible. This is your irreversible. This is your reversible. This will be less than irreversible. Yes or no, बच्चा? Can I say this? समझ में आ रहा है? I am giving you a very very interesting conclusion. Everyone, just pay attention to this. This is quite, you can say, interesting. This is quite interesting. Tell me, are you getting this, बच्चा? When I give you the conclusion, na, things will be more clear. Things will be more clear. When I give you the conclusion, na, things will be more clear. Tell me, is this clear? Okay, is this clear? Bolo bolo re. Very good. So when you compare this, ये तो cancel हो जाएगा. This will be getting cancelled out. So what will be left over with? Integral of del q by t for a internally irreversible process will be less than integral of del q by t for internally reversible process. And bacha, that means your delta S, that is the entropy change, is greater than integral of del q by t for internally irreversible process. Remember this. Remember this statement. I will be giving you the beauty of this statement. Just wait for 5 minutes. Your doubts will be clear. Everyone, if is having any doubts, just wait for 5 minutes. I'll clear everything. So delta S is greater than integral of del q by t for an internally irreversible process. So final conclusion is delta S is equals to integral of del q by t for an internally reversible process, and delta S is greater than integral of del q by t for internally irreversible process. Well done, sir. Pretty clear now. So that means for an internally irreversible process, this will be equals to integral of del q by t plus any constant this will be equals to integral of del q by d. I want to make it equal, so यहाँ पे मुझे कुछ ऐड करना पड़ेगा. I want to make it equal, so I will have to add something over here, that is any constant. Yes or no बच्चा? That will be any constant, and that constant is nothing but your entropy generation. That constant is nothing but your entropy generation. Tell me, that constant is nothing but your entropy generation. Are you getting this? Those who have studied thermodynamics previously will enjoy this. Those who have studied, I am slowly giving you the beautiful concepts of entropy. Is this clear, bachcha log? Now tell me, is this clear? Rakesh, Guru, Pushpendra, Shravan, Sriridhi, Bhumit, everyone. Is this clear? Tell me. Okay. So that means your delta S, always remember. Now let me give you the statement. Always remember, the entropy change for a given process is always equals to the entropy transfer due to heat transfer. This is nothing but entropy transfer due to the heat transfer plus the entropy generation. Repeat with me, the entropy change for a given process is equals to the entropy transfer due to the heat transfer plus entropy generation. Entropy transfer due to heat transfer plus the entropy generation. Entropy transfer due to the heat transfer plus the entropy generation. But sir, entropy generation will be zero in the internally reversible process. Entropy generation will be zero in case of internally reversible process. That means this is the equation for internally irreversible process, and entropy generation will be zero. So we can say that this will be equals to integral of del q by t. I hope everyone will be clear with this now. That means for an internally reversible process, entropy generation is zero. 100 times asked question. 100 times asked question. Entropy generation is zero for an internally reversible process. Entropy generation is zero for an internally reversible process. So now let's understand entropy changes for closed system undergoing an internally reversible heat interaction. Understand this. This is internally reversible. This is internally reversible. Okay, sir. Sir, case number one. Case number one. We are supplying the heat. We are adding the heat. Heat addition is taking place. Heat addition is taking place. That means your del Q will be positive and absolute temperature is always positive. It's entropy. Entropy is extensive or intensive? I don't know at present. I have not taken this. I'll tell you. Don't worry. I'll tell you. I'll tell you what is it. Okay. Just wait for a while. I'll tell you. Okay. Just wait for a while. It is there somewhere in this slide only. It will be there somewhere in this slide only. Okay. Okay. It will be there somewhere over here only. Just wait for few slides only. Okay. Chaliye. Let's focus on to this. It is an internally reversible heat addition. It is an internally reversible heat addition. Internally reversible heat addition. That means your del Q is positive. Del Q is positive. Absolute temperature change is always positive. Absolute temperature change is always positive. Absolute temperature change. Absolute temperature not change. Sorry. Absolute temperature is always positive. That means positive upon positive. That means delta S, that is S2 minus S1, will be positive. That means entropy increases. That means whenever heat is supplied for an internally reversible heat interaction process, whenever a heat is added to an internally reversible process, entropy of the system increases. Whenever the heat is supplied to an internally reversible process, entropy of the system increases. Whenever the heat is supplied to an internally reversible process, entropy of the system increases. Okay, sir. Case number 2. Sir, heat rejection in an internally reversible process. Heat rejection in an internally reversible process. That means your del Q will be negative, but absolute temperature is always positive. So negative upon positive will be negative. That means S2 minus S1 will be negative. That means your entropy will decrease. That means for an internally reversible process, if heat is rejected from the system, entropy of the system decreases. If the heat is rejected from the system, entropy of the system decreases. Are you getting my point? Heat is rejected from the system, then the entropy of the system decreases. Entropy of the system decreases. Is this clear? Is this clear बच्चा लोग? Heat is added to the system, entropy of the system increases. Heat is rejected from the system, entropy of the system decreases. I hope this is pretty clear. I hope this is pretty clear. I hope this is pretty clear. Tell me. Sir, third case. Sir, third case, entropy change for a, you can say, closed system undergoing, you can say, internally heat, reversible heat interaction for an adiabatic process. For an adiabatic process, that means del Q is 0. That means del Q is 0. Del Q is 0, but temperature is still positive. Del Q is 0, but temperature is still positive. As del Q is 0, so entropy change will be 0. That means entropy is constant. So always remember, internally reversible adiabatic process is called isentropic process. Understand the word. Internally reversible adiabatic process is called isentropic process because entropy remains constant. Entropy remains constant. Internally reversible adiabatic process is called isentropic process. So three cases for internally reversible heat interaction: heat added to the system, entropy increases; heat rejected from the system, sir, entropy decreases; and adiabatic process, entropy remains constant, isentropic process. But now let's discuss about internally irreversible heat interaction. Internally irreversible heat interaction. So with the internally irreversible heat interaction, the point is, first of all, the formula will be entropy change due to the heat temperature change, that is your del Q by T plus entropy generation. This will be entropy change due to the temperature change, del Q by T plus entropy generation. First thing is pretty clear. Now we are adding heat. Heat is added to the system. Now always remember, entropy generation is always positive. Entropy generation is always positive. We are adding the heat to the system, so del Q will be positive, and absolute temperature is always positive. Absolute temperature is always positive. Absolute temperature is always positive. So bachcha log, here the entropy will increase because this right hand side is completely positive. So for an internally irreversible heat addition process, entropy of the system increases. For an internally irreversible heat addition process, entropy of the system increases. For an internally irreversible heat addition process, entropy of the system increases. Entropy of the system increases. Entropy of the system increases. Is this clear? Quite clear, sir. Now second case, adiabatic process. Acha, can you tell me this adiabatic process will be isentropic? If I write adiabatic process for an internally irreversible heat interaction, will it be isentropic? Heat transfer, you can say adiabatic process, internally irreversible adiabatic process, will it be isentropic? Are you getting my question? Internally irreversible adiabatic process, will it be isentropic? Will it be isentropic? Tell me, will it be isentropic? Will it be isentropic? Are you getting my question? Rakesh is telling no. Rakesh is telling no. Guru is telling no. The point is, bachcha log, when you are having adiabatic process, your del Q is 0. Your del Q is 0. But in an irreversible process, there is an entropy generation. In an irreversible process, yes, due to the entropy generation, your entropy change will be positive. Due to the entropy generation, your entropy change will be positive, and that's why bachcha log, the entropy of the system will increase. That means for an internally irreversible adiabatic process cannot be isentropic. Internally irreversible adiabatic process is not isentropic because of entropy generation. Internally irreversible adiabatic process is not isentropic process because of you can say entropy generation. Is this clear? Third case, sir, heat rejection. Internally irreversible process undergoing heat rejection. Now there are possibility, your del Q will be negative, your absolute temperature is always positive, and entropy generation is always positive. So there are three possible cases. Sir, first case, if your del Q by T, this negative value is less than the entropy generation, so the entropy of the system will increase. Second case, sir, if this del Q upon T is more than the entropy generation, so this value will be negative, so the entropy of the system will decrease. And the third case, the third possibility is that your del Q by T is equals to the entropy generation. Both will be getting cancelled out, then the entropy of the system will remain constant. That means whenever we are having the internally irreversible heat rejection process, the entropy of the system may increase, the entropy of the system may decrease, the entropy of the system may remain constant depending upon the, you can say, entropy transfer due to the temperature difference, depending upon the entropy transfer due to the temperature difference. Is this clear? Is this clear, bachcha log? Is this clear? Is this clear, bachcha log? Okay, due to an urgent emergency, I'll have to take a 20 minutes break. Okay, I'll be back at the earliest, bachcha. I will be back at the earliest. There is a small emergency. I'll be back at the earliest. Okay, let's meet at, you can say, within 20 minutes, within 15 or 20 minutes. Let's meet. Okay, most probably I'll be live at 3:30 or 3:45. 3:35, not 3:45. I will be live at 3:30 or 3:35. Okay, just 15 or 20 minutes break I'm taking. I'll come at the earliest. I'll come back at the earliest. Can it be called isentropic? Yes, it can be called isentropic. I've clearly mentioned when your entropy transfer due to the heat transfer is equals to entropy generation. The entropy transfer due to the, you can say, heat transfer is equals to entropy generation, then it will be called an isentropic process. So they are asking you that in the, you can say, heat rejection process, can we have an isentropic process? So this is the case. Is this clear, bacha? Within 15 minutes I'll be back. I'll be back within the 15 minutes. Chaliye, very sorry. Hey guys, am I audible again? I'm back. Sorry, I'm late. Sorry, I'm late. Okay, so bacha log, I'll be starting the session. So last case we were discussing about the internally irreversible heat rejection. So we know that very well. Internally reversible heat rejection, the entropy of the system may increase, the entropy of the system may decrease, and the entropy of the system may remain constant depending upon the you can say, entropy change, depending upon the entropy transfer due to the heat transfer and entropy generation. Depending upon the entropy transfer due to the heat transfer and entropy generation. Is this clear, everyone? I hope this is pretty clear to all. I hope this is pretty clear to all. I'm very sorry. I got slightly late. Okay. I hope now I'm audible and clearly visible to all. I hope everything is pretty clear. So moving ahead now, as you were asking, entropy change is an exact differential. Entropy change is an exact differential, but your del q by t is your del q is an inexact differential. Not del q by t, but del q is an inexact differential. So always remember, exact differential is always equals to the integrating factor into inexact differential. Exact differential is always equals to the integrating factor into inexact differential. So always remember, ds is an exact differential, del q is an inexact differential, and 1 upon t is an integrating factor. This you were asking Guru. I think Guru was asking this question. Okay, I hope this is pretty clear with all. I hope this is pretty clear with all. Okay, chaliye. So let's start the session with the bang once again. Now, entropy transfer for closed system undergoing constant temperature heat interaction. Some direct formulas. So what are some direct formulas? First of all, let's say heat is added to the system. Okay, heat is added to the system. So this can be written as, you can say, heat transfer from process 1 to 2 upon the temperature at which the heat transfer can be taken place. So direct shortcut formula is, you can remember this, that when heat is added to the system, the entropy transfer can be written by heat transfer upon the temperature at which the heat transfer is taking place. And as heat is added to the system, so this will be positive, and when the heat is rejected from the system, this will be negative. Remember this, entropy transfer for a closed system undergoing a constant temperature heat interaction, so it will be given by plus minus q upon t. Okay sir, from the source we are constantly removing the heat, we are absorbing the heat. From the source we are constantly absorbing the heat, so this will be given by minus of QH upon TH. At constant temperature we are absorbing the heat, so this will be given by minus of QH upon TH. This will be given by minus of QH upon TH. From the sink, in the sink we are supplying the heat, so this will be given by plus of QL upon TL. Plus of QL upon TL. So bacha log, there is a very regularly. Now this was the case 1 for the source, minus of QH upon TH. For the sink, plus of QL upon TL, entropy transfer. And third case, the entropy transfer through a plane wall, where on one side we are having high temperature and on to the other side we are having low temperature. Means you can say here it's like a furnace wall. Yahan pe we are having high temperature gases, here we are having low temperature, you can say, environment. So what will be the case? Sir, the entropy added, that means your entropy in will be given by heat is added to the system. So from this side, this will be Q dot upon TH. Sir, entropy transfer outside from, you can say, to the surrounding, this will be given by minus of Q dot upon TL. So बच्चा लोग, as the entropy is rejected from the system, ये system में से reject हो रही है, so this will be given by Q dot minus of Q dot upon TL. I hope these things are pretty clear. I hope these things are pretty clear. Okay sir, pretty clear. So what will be the net entropy transfer? Sir, Q dot upon TH minus Q dot upon TL. Q dot upon TH minus of Q dot upon TL. Is this clear? Is this clear everyone? Q dot upon TH minus of Q dot upon TL. I hope this point is pretty clear everyone. Okay. Sir, now entropy transfer is Q dot upon TH minus Q dot upon TL. So always remember, in such cases, I'll be telling you this later on, the entropy generation will be negative of this. The entropy generation will be negative of this. So you can directly remember that entropy transfer will be given by Q dot upon TL minus Q dot upon TH. This will be positive. Entropy transfer will be negative. Entropy generation will be positive. Direct formula hai, rat lo, direct formula based questions are coming in the examination. Direct formula based questions are coming in the examination. I hope this point is pretty clear with you all. Okay sir. Next is your entropy transfer for a closed system undergoing reversible constant temperature heat interaction. Reversible constant temperature heat interaction. Now see this. Okay, so now the point is, first of all, we are having reversible heat engine. The point is we are having the reversible heat engine. Okay, what we are having? We are having the reversible heat engine. Okay, sir. Sir, what is the reversible heat engine? Sir, in case of reversible heat engine, what you will be doing? You will be rejecting the heat from the source. You will be you will be absorbing the heat from the source. आप लोग सोर्स में से हीट को एब्जॉर्ब करोगे एंड यू विल बी सप्लाइंग द हीट टू द सिंक एंड यू विल बी सप्लाइंग द हीट टू द सिंक. Okay, sir. Now, the point is, what will be the entropy change for a reversible heat engine? Your entropy change for the reversible heat engine is always zero. The entropy change for a cyclic device is always zero. The entropy change for a cyclic device is always zero. That means the entropy change of surrounding is also zero. Entropy change for the surrounding is also zero. That means your net entropy change for the system will be given by, you can say, minus of QH upon TH plus QL upon TL. This will be for the system. This will be for the system, and entropy change for the surrounding will be zero. Are you getting my point, बच्चा? ये point clear हुआ? Direct formula based question are coming from the source. You are absorbing the heat, so this will be minus of QH upon TL, and from the sink, at the sink you are supplying this, so this will be QL upon TL. Ultimately, the net heat interaction will be, you can say, zero, because this is a reversible heat engine. Ultimately, this will be zero. I hope these points are pretty clear, everyone. I hope these points are pretty clear. Moving ahead, now heat transfer between the source and the sink. So the point is, now we are not having the heat engines. Okay, now we are not having the heat engines. We are having a wires or strip through which the heat transfer will be taking place. अपने पास ऐसे wire या strip है from which the heat transfer will be taking place. See, I'll be discussing entropy later on in detail. Don't worry about this. I think you will be getting confused. Okay. So the point is heat transfer between the source and the sink. So the total entropy change of the system will be given by the entropy change of the source plus the entropy change of the sink plus the entropy change of this wire or strip. Now the point is we are having the steady state, you can say, heat transfer. So the entropy change of the strip will be zero. The entropy change for the strip will be zero because of the steady state heat transfer. There will be no entropy change from this strip. यहाँ से कोई भी entropy transfer due to heat transfer is not going to taking place. So what is the entropy change of the source? Sir, minus of Q dot upon TH. What is the entropy change of the sink? Sir, plus of Q dot upon TL. So this is your final formula. Direct formula based question are coming in GATE. Direct formula based questions are coming in GATE. Tell me, is this clear? I hope you are getting this. Guru and all other students, I hope you are getting this. Tell me. Now, this is now heat transfer between the source and sink. See, previously it was the heat transfer through source and sink. Acha, this is the case for the closed system. So this is also same. At present, this is also same. Don't worry about this. So these are the cases of entropy. But chalo, I promise entropy, I will be taking it, you can say, later on in detail in the special classes also. Okay, in the special classes also. Okay, I will be updating you the link. I will upload with the short videos for you कि अपन लोग entropy को around in 3-4 hours will be discussing that in detail. We will be discussing that in detail. Is this clear, everyone? Okay, we will be discussing that in detail. So now we are jumping on to the equations that are your, you can say, entropy transfer equation. So first of all, we need to understand what is the first TDS equation. First TDS equation क्या है? थोड़ा you have to be very careful. थोड़ा you should, you can say, be taking care of the things. You should take care of the things. Okay. The point is, first of all, we know that very well. Del Q is equals to du plus PdV. Del Q is equals to du plus PdV. Okay, sir. Sir, we know that very well that entropy transfer ds is given by del Q upon T. Yes or no? Entropy transfer ds is given by del Q upon T. So can I say that del Q will be equals to TDS will be equals to du plus PdV. So this is the first TDS equation. TDS is equals to du plus PdV. TDS is equals to du plus PdV. Bacha, don't worry, entropy change I will be discussing separately in the special classes for you. Entropy change we will be discussing separately in the special classes for you. Okay, I think this will be a slight, you can say, portion that you require more proper understanding. We cannot discuss entropy in within half an hour or so. So we will be discussing all the cases through the special classes for sure. Okay, is this point clear, everyone? So the first TDS equation is given by, you can say, TDS is equals to du plus PdV. Okay, sir. Sir, second TDS equation. Sir, second TDS equation, we know that very well. First of all, H is equals to U plus PV. Yeah, that will be coming on. जी आगे जाते हुए this will be very useful. That all are there in the today's relation session. That are there in the thermodynamic relation. But we want some, you can say, clarity of entropy also for, you can say, understanding the entropy. Now, this formula based portion I have given you everything. But you should understand the entropy transfer in detail. We have discussed many of the things, but you should still understand this detail. Okay, is this clear? So the point is, the second TDS equation is TDS is equals to DH minus VDP. Okay, first relation is TDS is equals to du plus PdV, and second relation is, you can say, DH minus VDP. du plus PdV and DH minus VDP. Is this clear? Is this clear? Okay, sir. This is very clear. Okay, sir. Sir, now entropy change for the perfect gas. Entropy change for the perfect gas. What is the entropy change for the perfect gas? Sir, now understand the relation. The first formula is, from the first TDS equation, you will be getting the first relation. See, derivation is there onto your screen, but we need to remember the relation directly. So the first relation is CV ln T2 upon T1 plus R ln V2 upon V1. CV ln T2 upon T1 plus R ln V2 upon V1. I will be telling you how to remember this. Sir, the second relation is CP ln T2 by T1 minus R ln P2 by P1. CP ln T2 by T1 minus R ln P2 by P1. Is this clear? CP ln T2 by T1 minus R ln P2 by P1. Okay, sir. Sir, third equation is, you can say, CV ln P2 by P1 plus CP ln V2 by V1. So these are the three equations for entropy change undergone by a perfect gas. First condition is, these equations are valid for the perfect gas only. So how to remember these three equations? How to remember these three equations? Okay, these three equations are there onto your screen. How to remember them? I will be telling you how to remember them. First of all, you write your entropy change, and you write, first of all, ln T2 upon T1. You can say, first of all, you can write CV and R. What you can write? CV and R. Let me write this for you. Let me connect my pad. Let me write this for you. Let me write this for you. Actually, no, my link got broke. My link got broke when I was going there for the urgent emergency. Na? Okay, so okay, now understand this very well, how to remember this equation. First of all, 1, 2, 3. कैसे याद रखना है? What should be the case? Direct formula based question. First of all, write CV R. Sir, CP R and CV CP. CV R, CP R, CV CP. Okay. Now here, as we are having CV, so here it will come ln V2 by V1. Remember this, it will come ln V2 by V1 as we are having CV. CV ln V2 by V1. Sir, CP ln P2 by P1. You can confirm. Here we are having CV ln V2 by V1. And here, as we are having CP, so here we will have ln P2 by P1. Okay, whenever we are having R, so we will have temperature with respect to R. So this will be ln T2 by T1. ln T2 by T1. Okay, in CV and R we will be having plus, in CV CP we will be having plus, only in CP and R we will be having minus. Is this clear? Is this clear? Is the formula writing steps clear to all? How to write this formula? Is this clear to all? बोलिए बच्चा लोग, is this clear? I hope this point is pretty clear. Okay, I hope these points are pretty clear with all. Clear? So direct formula based questions are coming. चलिए. Now, nice trick. Okay, now this is one more formula which is there for the entropy change for solids or liquid. The entropy change for the solids or liquids. Entropy change for, you can say, solids or liquids. Okay. Entropy change for the solids or liquids. So whenever we are having solids or liquid, what is the entropy change? So remember this, bacha, it is given by C ln T final upon T initial. C ln T final upon T initial. Directly this formula, C ln T final upon T initial. Entropy change for the solids or liquid is given by C ln T final upon T initial. T final upon T initial. Is this point clear? Okay, so these are the formulas that you need to remember. These are the only cases in the entropies that you need to remember. Three formulas I had given you. This is for solid. I think in GATE 2020 or GATE 2021, there was the direct question of entropy change for the solids. There was a direct question of entropy change for the solids. So that will be very important for you. Now, direct formulas will be very important for you. And now we are jumping on to a very interesting portion, that is your exergy. Okay, now we are jumping on to the very interesting portion of your course, that is your exergy. Sir, what is exergy? Sir, exergy is the maximum possible useful work that can be obtained from the system. The maximum possible useful work that can be obtained from the system is called exergy. Okay, sir. Sir, if the system is working in the cycle, then exergy is known as the available energy. And if the system is working in the process, then exergy is known as the availability. Two things: working in a cycle, available energy; working in the process, known as availability. Is this point clear, bachalo? I hope these points are pretty clear. Yes, sir, pretty clear. Now, what is available energy? Sir, available energy is the maximum possible useful work. It is the maximum possible useful work output that is obtained from the given heat input at a given temperature. One question will come from this topic of available energy. Available energy is the maximum possible useful work output obtained from the given heat input at a given temperature. आप लोगों के इस given temperature पे आप लोग कितना useful work पा सकते हो, that is the definition of the available energy in the simple form. Any example of what, बच्चा? Any example of what? Means I did not get your point. Any example of what, bacha? I did not get your point. Exergy, we will apply to heat engine only. Wait a minute. We'll apply to the heat engine only. We will apply to the heat engine only and then we will check. We'll apply to the heat engine only and then we will check. Then we will check. Okay, we will apply to the heat engine only. Okay, is this clear? We'll apply to the heat engine only. Okay, let's wait and watch how we will apply. So first of all, we should understand the direct numerical, applying the concept of exergy. So what we are doing, sir, we are calculating the condition for obtaining the maximum possible work output. We are calculating the condition for obtaining the maximum possible work output. Maximum possible work output. Okay, sir. Sir, this is your reversible heat engine. This is your reversible heat engine. Okay, sir. Sir, efficiency of the reversible heat engine is given by your work output of the reversible heat engine upon the heat supplied. Your work output of the reversible heat engine upon the heat supplied. Work output from the reversible heat engine upon the heat supplied, work output from the reversible heat engine upon new to this topic, sir. Okay, no problem, no problem. We'll go very slowly because direct one question formula based can come from this topic. Okay, so this is the formula for efficiency. So can I say that work output from the reversible heat engine will be given by the efficiency of the reversible heat engine into the heat supplied. This will be equals to the efficiency of the reversible heat engine to the heat supplied. Now, generally the heat supplied is fixed. Generally the heat supplied is fixed. In our engines, the heat supply is fixed onto the number of things. This we cannot change. Okay, this we cannot change. But what we can change is the calculation of efficiency. What we can focus on, we can focus on to the, you can say, calculation of efficiency, because the heat that will be absorbed, the heat that will be rejected generally is fixed. Okay, the heat that will be absorbed, that will be, you can say, fixed. So this will be fixed. So the efficiency of the reversible heat engine is nothing but, you can say, let me write this for you. The work done by the reversible heat engine is given by TH minus TL upon TH into the heat supplied QH. Okay, just keep this formula. Just keep this formula in your mind. This is your reversible work done. Don't worry about anything. This is your reversible work done. Just understand this very well. Now I want the maximum possible work output. So maximum possible work output is only possible. Understand the condition, sir. Maximum possible work output is only possible when your lower temperature side, that means the temperature at which the heat is rejected, is in equilibrium with the temperature of the surrounding, or else you can say that as T naught. Remember this, we will get the maximum possible efficiency from the heat engine only and only when we will be having the lower temperature side, the temperature at which the heat is rejected, you can say, into equilibrium with the surrounding, because higher temperature is always fixed according to the metallurgical conditions and other factors, and lower temperature side is fixed according to the environmental condition, because we cannot reject the heat at the temperature below the atmospheric temperature. Are you getting my point, bacha? Are you getting my point? So to obtain the maximum possible work, your TL will be T naught, that is your environmental temperature. So whenever the heat transfer is taking place up to the temperature of the surrounding, we will be getting the maximum possible reversible work output from the system. This is the maximum possible reversible work output from the system, and this maximum possible work output from the system is nothing but the available energy of the system. The maximum possible work output from the system is nothing but the available energy of the system. Just read the definition, sir. Maximum possible useful work output obtained, you can say, from the given heat input. That means our heat input is also constant, our temperature at which the heat supplied is also constant, and the temperature at which the heat is rejected is in equilibrium with the environmental temperature. So this is the available energy. This is the formula of the available energy of the system. Are you clear with this? Tell me. Are you clear with this, bacha log? Tell me. Now I think, Guru, you will be getting some glimpse of this topic. Now you will be getting some glimpse of this topic. Yes or no? What about others, bacha? I hope you are getting the glimpse of this topic properly. Very good, Pushpendra. Okay, so many a times they are asking you directly that what is the available energy for a given process? What is the available energy for a given process? Okay, now what are the conditions for obtaining the maximum possible work output? That means your maximum possible available energy. Sir, first thing is the heat engine should be the reversible heat engine. The heat engine must be reversible heat engine, because we are applying the formulas for reversible heat engine, because only reversible heat engine can give you maximum possible work output. And second thing is temperature of heat rejection must be the environmental temperature. They will ask you in the examination, what are the conditions for maximum possible work output? So remember this, heat engine must be the reversible heat engine, and the temperature of the heat rejection must be the environmental temperature. The temperature of the heat rejection must be the environmental temperature. Is this clear? Is this clear? So first of all, remember this formula, TH minus T naught upon TH into QH, and remember these two conditions. So now, this is the graph for this chapter, direct formula always remember the total heat supplied to any engine. The total heat supplied QH to any engine is always equals to the available energy that is converted into work and unavailable energy that is rejected to the sink. Remember this, available energy that is converted into work and unavailable energy that is rejected to the sink. So our ultimate goal is to increase the available energy and decrease the unavailable energy. This is our ultimate goal. So available energy of the system is given by TH minus T naught upon TH into QH. TH minus T naught upon TH into QH. Is this clear? It is given by TH minus T naught upon TH into QH. This is one formula that I give you. Sir, second formula, according to the thermodynamic temperature scale, because our total study is onto the reversible heat engine only, I can say that QH upon TH. QH upon TH will be equals to QL, but here QL is your unavailable energy upon the temperature of heat rejection is T naught. So our second formula is QH upon TH is equals to the unavailable energy upon T naught, and QH is equals to the available energy plus unavailable energy. Many times from these three formulas, direct formula based questions are coming in examination, whether it is GATE examination, whether it is engineering services, ISRO or BARC examination. Tell me, are you clear with this? Are you clear with this? These are the three formulas. I'm bringing the basics from the very beginning for you. Okay. Chaliye. Now, this is, I have given you a numerical. They will be asking you such numericals that they will be giving you the temperature of source. They will be giving you the heat transfer. That is your QH. They will be giving you, you can say the temperatures, and they will ask you the available and unavailable energy of the system. So this way you can calculate. This green color one is I have calculated. This black color one was given to us. Okay, is this clear? We'll discuss the problems. Don't worry. Now, what is unavailable energy? Sir, the minimum energy that must be rejected to the environment is known as the unavailable energy, and generally remember this, unavailable energy is never zero. But our goal is to minimize the unavailable energy. Our goal is to anyway minimize the unavailable energy. Okay, sir. This we will be discussing later on, why our, you can say, second law is called qualitative and first law is called quantitative. Okay. Okay, so we'll discuss this later on. Now we are discussing the topic of, you can say, exergy, you can say potential. Exergy potential, it's like work potential that is associated with the kinetic energy and potential energy. Let's see this. We know that very well. Our kinetic energy is 1 half mv square. Our potential energy is mgz, mgh या mgz. Okay, sir. Sir, exergy transfer for a closed system. Now, slowly understand this. This is a very interesting topic, and they can ask you one question from this. Okay. We know that very well. For a closed system, your del Q is equals to del du plus del W. Okay. So del W will be nothing but del Q of the system minus entropy change of the system, and this can be written as del Q of the surrounding minus entropy change of the surrounding. Yes or no? This can be written as entropy change. Now del Q of the surrounding can be written as, sir, we have to reject the heat to, you can say, T naught, the temperature of the surrounding. So this will be T naught ds. This will be T naught ds. Okay, slowly try to understand this. So this will be given by minus of T naught ds. See the point is, yes, actually it is a loss only. Yes, Pushpendra, it is a, you can say, energy that is, you can say, we are not able to convert it into the useful form. So this is a, you can say, loss of energy only. This is the loss of energy only. See, the point is here, the formula was dq of the system minus the, you can say, no, I'm telling you, this is du of the system. Now we know that very well. Let's say our system is, you can say, we know that very well, the heat transfer for an isolated system is zero. Heat transfer for an isolated system is zero. So when the isolated system is having zero heat transfer, so it can be written as, you can say, del Q of system plus del Q of the surrounding to be zero. So can I say that del Q of the system will be equals to, you can say, minus of del Q of the surrounding. Now in the closed system, the heat transfer is not taking place. Your heat transfer is taking place, but mass transfer is not taking place. But at present, what we are doing, we are assuming this to be an isolated system, and then we will apply the condition. So can I say that Can I say that this can be written as minus of del Q of the surrounding? Minus of del Q of the surrounding, because we want to calculate the, you can say, total maximum useful work. So what we will be doing now, this del Q of the surrounding can be written as T naught ds. So putting this T naught ds minus del U of the surrounding, so this will be minus of T naught S2 minus S1, and this entropy, internal energy change, sorry, this will be U2 minus U1. So when you combine this, what is the maximum work obtained for the closed system? It is given by U minus T naught S for state 1 minus U minus T naught S for state 2. See, remember this formula. Remember this formula. Your maximum work obtained will be given by U minus T naught S for state 1 minus U in bracket U minus T naught S for the state 2. So you can calculate the maximum work done. You can calculate the maximum work available. Okay. Chaliye. Okay. This is for the closed system. This is for the closed system. Are you clear with this by the ultimate formula? Are you clear with this for the ultimate formula? This is the maximum work because we can obtain the maximum work. First of all, this is the maximum possible work. Okay. Now, second point is now understand this very well. This is your maximum possible work. Maximum possible work. This is not useful. This is theoretical. ये जो है पूरी की पूरी चीज, this is theoretical. And now I want to find the useful work from this. Now I want to find the useful work from this. Sir, what will be the useful work? So always remember, whenever you are having closed system, so you will have to do some work onto the expense of surrounding also. Expense of surrounding means you will have to do the work that will be lost slightly to the surrounding also. Work done against the atmospheric pressure. You know, when you want to push the piston towards the, you can say, ODC, you can say towards the top dead center, you can say. So what is the case? You will have to do the work against the atmosphere, and work done against the atmosphere will be the displacement work only, which can be given by PdV. Work done against the atmosphere will be PdV. So this can be called as P naught V2 minus V1. So always remember, this is the work done against the atmosphere. P naught, that is the atmospheric pressure, into V2 minus V1. Okay, sir. So can I say that the useful work that is obtained from any of the process will be given by maximum possible work minus the atmospheric work. Maximum possible work minus the atmospheric work. So maximum possible work is nothing but U minus T naught S for state 1 minus of, in bracket, U minus T naught S for the state 2 minus of P naught V2 minus V1. So this will be the final formula, U minus T naught S plus P naught V for the state 1 minus U minus T naught S plus P naught V for the state 2. This is for closed system. This is for closed system. But chalo, they will be asking you direct question for useful work for the closed system. Useful work for the closed system. If they are asking maximum possible work, this formula. If they are asking the useful work, then this formula. But now there is a slight interesting concept for the open system. You know, for the open system, we will have to apply the steady flow energy equation. For the steady flow, Okay, am I audible? Please confirm. Please confirm, am I audible? Am I audible? Am I audible? Yes, 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 yes. Okay, 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 okay. Everything is fine. Things are coming together, you know. Many things are coming together today only. Okay, so now we were discussing this for the open system. Okay, sir, open system, when you apply the steady flow energy equation, the point is, okay, the heat transfer del Q will be given by, from the steady flow energy equation, dH upon del W. Understand this very well, dH upon del W. Okay, dH upon del W. Okay, sir. Once again, I can write your del Q as T naught into S. Del Q as T naught into S. So, the maximum possible work will be given by del Q minus dH. Del Q minus dH for an open system. Understand this very well. For an open system, this will be del Q minus dH. For the closed system, we were having del Q minus internal energy. Just remember, I am giving you the tricks to remember the end formula. Here we were having internal energy for closed system. For open system, we are having enthalpy. So the final formula, sir, what is the SFEE concept, steady flow energy equation, that we are applying for open system? I'll discuss this in the open system analysis. Don't worry. I'll discuss this in the open system analysis. You can say energy transfer, we will be doing this you can say in the inlet to the outlet. So don't worry about this. We'll discuss that. Okay. So this is given by the maximum possible work, that is H minus T naught into S for state 1 minus in bracket H minus T naught into S for state 2. Now understand this very well. In the open system, we are not having any work against the atmosphere, because work is done with the atmospheric equilibrium only. What we are doing the work, we don't have to push anything against the atmosphere, so there is no need to do the work against the atmosphere in case of open system. Can you feel this? For the open system, the maximum possible work is equals to the useful work. The maximum possible work is equals to the useful work only. How many of you can feel this condition? The maximum possible work is equals to the useful work only. How many of you can feel this condition? The maximum possible work is equals to the useful work. Yes, sir. But for the closed system, this is not true. But for the closed system, this is not true. Tell me, how many of you can feel this? How many of you can feel this condition? Yes, atmosphere is not working. We are working with the atmospheric equilibrium only. That's why. So here no need to do the work against the atmosphere. So that will be 0. So your maximum possible work. So environmental loss is already added in useful work. No, actually environmental loss कब आता है पुष्पेंद्र? Whenever you are having the closed system, आप environment को push करो. The point is, what you are having in the open system, pipe flow. Just imagine this, you are having a pipe flow. Okay, in the pipe flow, are you doing any work that is having a, you can say, work done against the atmosphere? Any work that will be work done against the atmosphere? Can you feel this? Okay, here there is a loss of energy. There is a loss of energy, I agree, but we will not be having any, you can say, work done against the atmosphere, because our open system, the mass flow rate is taking place, you can say, in the atmospheric presence only. तो आप लोग ये समझ सकते हो, there will be no work done against the atmosphere. वहां पे क्या था, as you were doing the work against the atmosphere, you are pushing the atmosphere. आप लोगों को expansion करना है. Your system is doing the work on the surrounding. Here in any cases, your system will not do the work against the surrounding. Are you clear with this? Got it? Okay, so that is the point. Okay, for the open system work. So there are 3 possible questions. First numerical, they will be asking you the maximum possible work for the closed system. Maximum possible work for the closed system. Sir, useful work for the closed system. useful work for the closed system. Third one is maximum possible work of the open system, which is also equals to the useful work for the open system. So remember this very well. For an open system, the maximum possible work is already equals to the useful work. The maximum possible work is already equals to the useful work. But I will be giving you the formula sheets also very soon. Okay. Now next is your, you can say, irreversibility and Gauss-Stodola theorem. Irreversibility and Gauss-Stodola theorem. What is irreversibility? Sir, the reversible work minus the useful work. The reversible work minus the useful work, that means the amount of work that cannot be converted into the useful work is called the irreversibility of the system. The irreversibility is given by the reversible work, which is also the maximum possible work minus the useful work. The irreversibility is given by the maximum possible work minus useful work. Okay, sir. Sir, Gauss-Stodola theorem says that the irreversibility is directly proportional to the entropy generation of the universe. Irreversibility is directly proportional to the entropy generation of universe. Now always remember, entropy generation of the universe is also equals to the entropy change of the universe. Entropy generation of the universe is equals to the entropy change of the universe, because universe is not having any surrounding. So totally the entropy change of the system plus entropy change of the surrounding will be the entropy change of universe. So according to the Gauss-Stodola theorem, irreversibility is nothing but T naught into delta S of the system plus delta S of the surrounding. Delta S of the system plus the delta S of the surrounding. Is this clear, bacha? Is this clear? Gauss-Stodola theorem statement also they are asking, and they are asking the numerical also onto this concept. Okay, chaliye. Now one more formula based question that can come from exergy. Irreversibility, as I told you, is nothing but, you can say, T naught into delta S of the system plus delta S of the surrounding. T naught into delta S of the system plus delta S of the surrounding. So you should know this very well, that the delta S of the system is given by MC ln T2 by T1. We were having this for the entropy transfer of the system. We had derived this formula MC ln T2 by T1. MC ln T2 by T1 plus the entropy change of the surrounding will be Q by T naught, and Q can be written as MC delta T. Q can be written as MC delta T. So this is the formula you can remember directly for the numericals. Okay, is this clear? Chaliye. Now we are jumping on to the new chapter. That is your pure substance. Okay, we will complete the pure substance. Very beautifully. We will complete the pure substance. Okay. My total link got broke. Link टूट गया यार पूरा का पूरा, मजा। Okay. What is a pure substance? What is the pure substance? Now understand this. Now this is a very interesting topic. Sir, a substance that has a fixed chemical composition throughout is called pure substance. We can identify the pure substance in two ways. The first one is the chemical composition. Second one is the chemical aggregation, that is bonding. Okay, sir. So these are the examples from which we will identify whether it is a pure substance or not. So case number one. Let's say we are having nitrogen in the container. आप लोगों को क्या करना है? Take the sample at different places. Here also it is N2, here also it is N2, here also it is N2. So what were the two things important for pure substance? Sir, first one was chemical composition should be uniform throughout, and chemical aggregation, that is bonding, also should be uniform throughout. So this will be the case that as we are having chemical, you can say, composition uniform throughout and chemical aggregation, that is bonding. Bonding is not needed only. This is a single phase substance only. So that's why you can say this will be pure substance. Single phase substance are generally pure substance. Okay. Sir, H2O, water. Chemical composition is uniform throughout. I am taking the sample at different places. Sir, chemical composition is H2O, H2O, H2O only. Yes, sir. What about bonding? What about bonding? Sir, bonding between H2O is also uniform. We are not having hydrogen and oxygen molecules, not having proper bonding anywhere. So that's why this is also a pure substance. That's why this is also a pure substance. Acha, how many of you can tell me about air? Is air a pure substance or not? I want to know about this. Is air a pure substance or not? Tell me. Is air a pure substance? Very good. Guru has given a very interesting answer. Sir, dry air is a pure substance. Okay, dry air is a pure substance. Very good. See, the point is moist air, not pure. See, the point is now this is the air without any moisture content. Without any moisture content. What are we having? Sir, general constituents of air are nitrogen, oxygen, carbon dioxide. Okay, so when I take the samples at different places, the nitrogen, oxygen and carbon dioxide are obviously in the fixed proportion and they are not having any chemical incongruency and no problem with the bonding also. We are having, you can say, the same content generally throughout. The same content generally throughout, and that's why dry air can be considered as pure substance. Dry air can be considered as pure substance. But when you talk about the, you can say, liquid air plus gaseous air, when you talk about liquid air plus gaseous air, after the condensation, you can see the particles of nitrogen, oxygen, carbon dioxide are gone. They will not be having the uniform bonding. They will not be having bonding with each other, and that's why it will be called the impure substance. That's why it will be called the impure substance. Is this clear? That's why it will be called the impure substance. Are you clear with this, bacha? Are you clear with this? Tell me. Okay, tell me, are you clear with this? So dry air is a pure substance, but moist air is not a pure substance. Moist air is not a pure substance. Okay, sir. Chaliye, moving ahead. Now Gibbs phase rule. Acha, what is the Gibbs phase rule that we are using in material science? I am a material science teacher also. I have taught material science also. In the special classes, I have taught material science also. What is the Gibbs phase rule in material science? Can anyone tell me what is the Gibbs phase rule in material science? P plus F is equals to C plus 1. Very good. P plus F is equals to C plus 1. ऐसा क्यों? Rakesh has given a very correct answer. Sir, why is such confusion? Here I have written P plus F is equals to C plus 2. Sir, is it wrong? Sir, is it wrong? Is it wrong? No, it's not wrong. I have written it's not wrong. I have written it's not wrong. For sure, it is not wrong. For sure, it is not wrong. Okay. Then, sir, what's the problem? What's the problem? Generally, when we are talking about material science, whenever we are talking about material science, always remember that we are considering the change of only and only temperature. The pressure is constant throughout. The pressure is atmospheric pressure. Your all heat transfer processes, heat treatment processes, sorry, are taking place at the atmospheric pressure only, and that's why atmospheric pressure is not independent to change, and that's why we are using that only single variable, that is temperature dependent formula. But when you talk about thermodynamics, here we study the change of temperature, here we study the change of pressure. So Gibbs phase rule describes the number of degree of freedom, that is the number of independent intensive variables required to specify the state of the system. Number of independent intensive variables required to specify the state of the system. So that's why the Gibbs phase rule for thermodynamics is P plus F is equals to C plus 2. Where F is your degree of freedom, C is the number of components, and P is the number of phases like solid, liquid and gases. I hope this is pretty clear. So let's understand. First of all, subcooled liquid. Sir, what is the subcooled liquid? The liquid that is below the saturation temperature corresponding to the given pressure is called the subcooled liquid. The liquid which is at the temperature below the saturation temperature corresponding to the pressure is called subcooled liquid. Okay, sir. That means it is water. H2O we are taking. So how many components are there? Sir, C is equals to 1. Phase, sir, single phase. So what will be the degree of freedom? C minus P plus 2. So this is coming out to be 2. That means the degree of freedom for a subcooled liquid is 2. That means you require pressure and temperature both to completely specify the condition of the subcooled liquid. What did I tell you? What did I tell you? The subcooled liquid is the liquid at a temperature below the saturation temperature corresponding to the given pressure. Corresponding to the given pressure. That's why you require the values of pressure and temperature both to completely specify the state of the subcooled liquid. Are you clear? To completely specify the state of the subcooled liquid. I hope this point is pretty clear with all. I hope this point is pretty clear with all. Tell me, bacha log, I hope this point is pretty clear. Okay, sir. Sir, what is the, you can say, degree of freedom for superheated vapor? Superheated vapor, that means completely dry and saturated. Superheated vapor, obviously H2O, which will be in the gaseous state. So component is 1, phase is 1. Once again, degree of freedom is 2. That means to completely specify the state of superheated vapor, you require the pressure and temperature both. You require the pressure and temperature both. Okay, sir. Wet vapor. Wet vapor, sir, the vapor which is at the saturation temperature corresponding to that pressure. Okay. So what is the point? Sir, how many components are there? Only water. So component is 1 but phase are 2. Component is 1 but phase are 2. So when you write the degree of freedom will come out to be 1. That means for the wet vapor, if I tell you the pressure, the temperature will be saturation only. That means it will be constant. If I tell you the temperature, the pressure will be saturation, it will be constant. That means you can specify the wet vapor with either telling the pressure or temperature, any one of them. But here the pressure and the temperature are independent. Here they are dependent. Is this clear? Is this clear, bacha log? Now phase change. Let's understand this. What is the latent heat? What is the sensible heat? Thoda maza aayega. What is the latent heat? What is the sensible heat? Bacha log, thanks for being with me from the beginning to the end. I'm very happy. I hope we will complete the pure substance. After pure substance, I will wind up the today's session. After pure substance, we will wind up today's session because I will have another session also in the evening. I have the another session also. Okay, so after this, we will wind up the session, but there are 2-3 topics left. Only open system analysis is left. Only open system analysis is left, which I will be taking through the, you can say, special classes on Unacademy platform. Okay, I will be updating you when I'm taking the special classes of open system analysis. Thank you very much, Guru. Thank you very much. And practice session with this will be the complete package. Okay, so how does the phase change take place? Sir, for a pure substance, let's say we are having the water at 20 degrees centigrade and you are supplying the heat. You are supplying the heat. Relations are there after this only. I have kept them after this only. I think I have kept them after this. Yes, they are over here. They are over here. Okay, so open system analysis and thermodynamic relation. Open system analysis and thermodynamic. I'll share the drive link for sure. Rakesh, just give me a day. You attend the session at night now, I'll update there over the link. Okay, because on YouTube I'm not possible how to share the link. I am not pretty sure because on YouTube I'm not unable to share the link. Okay, so I'll update there over there. Okay, for sure these notes are for you. For sure these notes are for you. So bacha log, let's understand this topic. Okay, 2 things are left: thermodynamic relations and open system analysis. We'll solve that very easily in the special classes. Okay. Sir, sensible heat. You are supplying the heat to water at 20 degrees centigrade at atmospheric pressure and it is reaching to 100 degrees centigrade because at the atmospheric pressure the saturation temperature is 100 degrees centigrade. So heat supplied from, you can say, 20 degrees centigrade to 100 degrees centigrade is called the sensible heat. This is called the sensible heat because the temperature change is taking place. Temperature change is taking place. Okay, sir. Sir, now at 100 degrees centigrade, I am having saturated liquid. 100 degrees centigrade, I am having saturated liquid. On further application of heat, अगर मैं और हीट सप्लाई करता हूं, सो एट 100 डिग्री सेंटीग्रेड ओनली आई विल बी गेटिंग द सैचुरेटेड वेपर. That means this is the supply of latent heat. That means the heat that is associated with the phase change but not the temperature change. The heat transfer that is associated with the phase change but not with the temperature change is called the latent heat. This is your latent heat. This is your latent heat. Okay, sir. And now on further application of heat, the saturated vapor, the dry and saturated vapor will have an increase of temperature from, let's say, 100 degree centigrade to 120 degree centigrade. So this is an example of sensible heat. This is an example of sensible heat. So I hope you are clear. First of all, with the definition of sensible heat, latent heat in detail. So first of all, what is sensible heating? Sir, the addition of heat which is utilized to increase the temperature is known as the sensible heating. The addition of heat which is utilized to the temperature to increase the temperature is called sensible heating, given by C delta T. That means here we are not interested with the phase change, but we are interested with the increase in temperature. Okay, sir. Sir, what is latent heat? The addition of heat which is utilized for the phase change is called the latent heating. The addition of heat which is utilized for the phase change is called latent heat, and latent heat of fusion is given as 334 kilojoule. Remember, this latent heat of vaporization is 2257 kilojoule. Sometimes they are not giving this in the, you can say, given problem, so you should remember this. ये आप लोगों को याद रखनी चाहिए. Now saturation temperature, some basic difference, some basic definitions. Sir, what is saturation temperature? Sir, the temperature at which the phase change starts at a particular pressure is called the saturation temperature. The temperature at which the phase change starts at a particular pressure. So temperature at which the water starts boiling is always dependent on pressure. I will be giving you an example. At the atmospheric pressure, the water starts boiling at 100 degrees centigrade. At the atmosphere, the water starts boiling at 100 degrees centigrade. But when you are going at mountains, let's say we are going at mountains, we are going in the mountains for trekking. Okay, we are going on to a very, very high mountain ranges. So what will be the case? As we are moving above the ground level, the pressure is decreasing. The pressure will be decreasing and the corresponding saturation temperature will also decrease. Can you feel this? The corresponding saturation temperature will also decrease. So previously you can say that at 1 atmospheric pressure, your water was boiling at 100 degrees centigrade. Let's say I'm taking just an example that at the given pressure on the mountain, the water is boiling at 80 degrees centigrade. The water is boiling at 80 degrees centigrade. Now answer a question. I am sending Guru to a mountain range and asking him to calculate. Yes, asking him to calculate the time required for making the Maggi. The time required for making the Maggi. He will say, sir, 2 minutes mein nahi banti. Not able to make this in 2 minutes. Not able to. No. Saturation temperature will not increase, bacha. Saturation temperature will not increase. I'll be telling you. As you are increasing the pressure, pressure and temperature are having direct relation. Don't confuse with that. Don't confuse with that. The saturation temperature is decreasing. Now, why it is decreasing? What will happen? The water boils, let's say, at 80 degrees centigrade. Okay, so water will start boiling at 80 degrees centigrade. Water will start boiling at 80 degrees centigrade. So now Guru is making Maggi. Okay, Guru is making Maggi. Sir, he will say that, sir, my water is boiling and that's why the heat transfer is taking place for the phase change. The heat transfer is not utilized for boiling the Maggi or boiling the vegetables, but the heat transfer is utilized in converting the phase change, and that's why it will be taking more time. It will be taking more time. Now I think this is clear. Okay, that's why it will be taking more time. That's why it will be taking more time. Are you clear with this, everyone? That's why it will take more time. Okay, so I have written this one thing: at different pressure, water boils at different temperature. Water boils at different temperature. Is this clear? Is this clear? So there are some examples. See this. These are some examples that at 1 atmospheric pressure, the boiling temperature, the saturation temperature is 100 degrees centigrade. At 10 bar atmospheric pressure, 10 times 10 bar, it is 180 degrees centigrade. Sir, at 3.17 kilopascal, just see the value, the saturation temperature is 25 degrees centigrade. Is this clear? So as the saturation pressure increases, the saturation temperature also increases. And why cooking is taking more time? Because the heat utilized for boiling is more compared to the heat cannot be utilized for, you can say, boiling the vegetable. The heat is lost for the phase change. Because water will be having the phase change. That's why it will be taking more time for making the Maggi. Okay, so that's why Guru will tell, sir, it is taking more time for making the Maggi on the mountain. So I'll come down, I'll eat the Maggi, and then I'll go up once again. Okay, chaliye. Now what is the saturation pressure? Sir, the pressure at which the substance changes the phase is called the saturation pressure corresponding to the temperature. At a given temperature, the pressure at which a pure substance changes the phase is called the saturation pressure. Okay, sir. Sir, for 100 degree centigrade, the saturation pressure is 1 atm. For 150 degree centigrade, the corresponding saturation pressure is 5 bar. For 180 degree centigrade, the corresponding saturation pressure is 180 degree centigrade, the corresponding saturation pressure is 10 bar. I hope now this question and this confusion is pretty clear. I hope now this question and confusions are pretty clear. Now, I want to make the TQ diagram. Okay, now I want, actually, now, I always try to discuss everything in a very detailed way with the students, but sometimes the link breaks. Whenever someone disturbs me, my link breaks. Link टूट जाती है, फिर वो मजा नहीं आती. You miss some examples, you miss some good points that you are having in mind to discuss. Obviously, the examples, we cannot mug them up. Obviously, we cannot mug up the examples and come. Exactly. So, the point is now, TQ diagram. We are having the constant pressure process onto the TQ diagram. We are having the constant pressure process. Okay, nearly 5 hours getting over. Just give me a minute. Huh? So now see this. Now let's say we are plotting the constant pressure lines. Constant pressure line. Understand this very well. Initially from 20 degree centigrade to the saturation temperature, what you are doing? You are supplying the heat, so pressure will increase. Now this is the, you can say, constant pressure and constant temperature heat supply. That means yahan pe we were having saturated liquid and now we will be having saturated vapor, and then this is the superheated region. So this will be the constant pressure line in the subcooled region. This will be the constant pressure line in the wet vapor region, and this will be the constant pressure line in the, you can say, superheated region. So first of all, here this is the sensible heat, this is the latent heat, and this is once again the sensible heat. So now if I'm plotting the points of, you can say, saturated liquid line and saturated vapor line, the curve that I'm getting, this is called your saturation curve. The curve that I'm getting is called the saturation curve. Is this clear? Now there are some points to observe. This is your subcooled region, this is your wet vapor region, and this is your, you can say, superheated region. As you are increasing the temperature at which the heat supply is taking place, your wet vapor region is decreasing. And at a point onto the top of the curve, at the bell point, this will be called bell point, there will be no wet vapor range. There will be no wet vapor region. Hoga kya? As you are supplying the heat, your subcooled liquid will be directly converted into the superheated vapor without having any mixture phase, and that point is called the critical point. At the critical point, your latent heat will be 0 and your wet vapor region will not be present above the critical point. At the critical point, your latent heat will be 0 and your wet vapor region will not be present. Okay, so what is a saturated liquid curve? Sir, the specific point where we start to vaporize is called the saturated liquid point. The specific point where we start to, you can say vaporize is called the saturated liquid point, and this condition of liquid is called the saturated liquid. The locus of all the saturated liquid point is called the saturated liquid curve. This one is the saturated liquid curve, the starting point of vaporization. That means we are having, you can say, the liquids onto this left side, wet vapor onto the right side. Okay, sir. Sir, saturated vapor curve, the specific point where water is completely converted to vapor, where the water is completely converted into vapor is called the saturated vapor point, and locus of all the saturated vapor point is called saturated vapor curve. Sir, in case of pressure cooker, pressure is decreased, then it's consumed less time for cooking. Nahi. Generally the pressure in the pressure cooker is 3 bar. Generally the pressure in the pressure cooker is 3 bar. Okay, that means it is more than the atmospheric pressure. It is more than the atmospheric pressure. So corresponding आपका जो saturation temperature होगा ना राकेश, वो भी बढ़ जाएगा. अब saturation temperature बढ़ गया मतलब आप लोग जो heat supply करोगे, it will be utilized for boiling the vegetable and not for the phase change. इस वजह से आप लोग कम समय में you can have the, you can say, cooking done. आप ओपन वेसल में करके देखो, साथ में प्रेशर कुकर में करके देखो, आपकी ओपन वेसल में ज्यादा समय लगेगा. जनरल प्रेशर जो होता है 3 बार होता है. दैट्स वाई आपके वहां पे वो प्रेशर रिलीफ वाल्व होता है. वो बोलते हो ना, वो सीटी नहीं बोलना, दैट इज अ प्रेशर रिलीफ वाल्व. व्हाई इट इज अ प्रेशर रिलीफ वाल्व? बिकॉज द प्रेशर इज अबव अ स्टैंडर्ड वैल्यू, तो वो प्रेशर को रिलीज कर देगा. आर यू गेटिंग माय पॉइंट राकेश? वहां पे प्रेशर कम नहीं होता, इट्स जनरली 3 बार. कभी प्रेशर कुकर फटते हुए देखा है? कभी प्रेशर कुकर को ब्लास्ट होते हुए देखा है आप लोगों ने? हैव यू सीन द प्रेशर कुकर ब्लास्टिंग? Okay, in my neighborhood some years back, they were having the pressure cooker of open type. See, two types of pressure cooker are coming. One is having the lid that is totally going inside. एक की lid ऐसे अंदर चली जाती है. And second one is having the lid which is getting clipped outside like this, which is having clipped outside. So ये जो outside वाले होते हैं ना, they have the tendency of bursting. They have the tendency of the bursting. If the pressure relief valve is not releasing the pressure, if the pressure release valve is not releasing the pressure, so ye wala will not burst. But this one na, it will not burst away, but it will just open the top lid. And you know I had seen that top lid of the container was stuck in the, you can say, huh, you can say it was stuck in the, you can say this, क्या बोलते हैं इसको, छत में, in your, you can say, roof. It was stuck in the roof. It was directly stuck in the roof. How big impact? That is a pressure release valve only. That's not fusible plug directly. Fusible plug अलग चीज होगी बच्चा. That is a pressure relief valve only. Okay. Is this clear now? So वो पूरा का पूरा छत में फंस गया था. And you know the biggest problem is if your mother, auntie, everyone, anyone is standing there na, they may be exposed to the burns because the temperature will be correspondingly high. That is the problem. उस बात का डर ज्यादा लगता है. They may suffer the burns क्योंकि if you are making khichdi, if you are making any other thing, you are boiling the vegetables, there will be water, there will be vegetables also, they will spread up everywhere. Luckily when I had seen this, no, you can say, human damage was there. We were lucky enough, not me, matlab our neighbors were lucky enough, but this is a thing that you should know, the pressure is high. Okay, is this clear? So I hope this point is pretty clear. Now critical point. Now there are important things about the critical point. Sir, where the saturated liquid curve and saturated vapor curve meet with each other is known as the critical point. It is a point at which the liquid directly converts into vapor. At the critical point, the latent heat is zero. The latent heat is zero. So for water at the critical point, the critical pressure is 220.8 bar and critical temperature is 374.17, I think, 17 degrees centigrade. Please correct this, it should be 17. Okay. Now degree of subcooling. Okay. Now let's discuss this very clearly. We will take some time and we'll discuss this. Okay. Just give me a minute. Okay, degree of subcooling. Degree of subcooling. Sir, the subcooled liquid is also called the compressed liquid. The subcooled liquid is also called the compressed liquid. Why, sir? Sir, if the actual temperature of liquid is less than the saturated temperature of the liquid, if the actual temperature of liquid is less than the saturated temperature of a liquid at a given pressure, it is called subcooled liquid. I told you the temperature is less than the saturation temperature at a given pressure, it is called subcooled liquid. Okay. The difference of the saturated temperature and actual temperature is called the degree of subcooling. If you want to see the graph, onto the graph, you can see this. If the temperature is 20 degrees centigrade, saturation temperature is 100. So 80 will be the degree of, you can say, subcool. The saturation temperature minus the actual temperature, this will be the degree of subcool. This will be the degree of subcool. I hope this is clear. This will be the degree of subcool. Okay, sir. Sir, what is the point? क्या होता है? Now understand this beauty, why it is called compressed liquid. Sir, actual pressure is more than the saturation. ऐसा क्यों होता है? Our temperature is 20 degree centigrade. Our temperature is 20 degree centigrade. Correspondingly, what will be the saturation pressure? Sir, corresponding saturation pressure should be less than the atmospheric pressure. Corresponding saturation pressure should be less than the atmospheric pressure. हाँ sir, it should be less than the atmospheric pressure. But the point is, the pressure is atmospheric pressure. That means your pressure is more than the saturation pressure, and that's why the subcooled liquid will be feel like it is compressed. उसके ऊपर एक दबाव आएगा, and that's why the subcooled liquid is also called the compressed liquid. Are you getting the point? Because the actual pressure is more than the saturation pressure corresponding to that actual temperature. Is this clear? So degree of subcooling is given by T saturation minus T actual. T saturation minus T actual. Similarly, the degree of superheat in the superheated region is given by T actual minus T saturation. T actual minus T saturation is given by the degree of superheat. Sir, what is the, if the actual temperature of vapor is greater than the saturated temperature of the vapor? Repeat karu. See, this is very, you can say, slightly complicated thing. Understand this very well. Let's say my liquid is at 20 degrees centigrade. My liquid is at 20 degrees centigrade. Sir, the corresponding saturation pressure will be 100% less than the atmospheric pressure. The corresponding saturation pressure will be 100% less than the atmospheric pressure. Yes, sir. But actually, the pressure that is acting onto the liquid is atmosphere. Although it is subcooled, but actually the pressure that is acting, it is more than the saturation pressure. So the pressure is more than the saturation pressure, and that's why the given subcooled liquid feels that it is compressed, and that's why it is also called the compressed liquid. Are you getting my point? Are you getting my point? This is the physical feel of, you can say, compressed liquid. This is the physical feel of the compressed liquid. Okay, degree of superheat. Sir, if the actual temperature of vapor is greater than the superheated temperature of vapor at a given pressure, the vapor is called the superheated vapor. The vapor is called the superheated vapor, and degree of superheating is T actual minus T saturation. T actual minus T saturation. Okay, sir, very well done. Wet vapor. Sir, everything at saturation. Pressure, temperature, both at saturation. Okay, sir. Sir, dryness fraction. Mass of vapor divided by mass of liquid plus mass of vapor. Mass of vapor divided by mass of liquid plus mass of vapor. Mass of vapor divided by mass of liquid plus mass of vapor. Clear, sir? Sir, dryness fraction, let's understand this. Now, this is your saturation curve. This is your saturation curve, and let's understand the dryness fraction in the different conditions. So first of all, the dryness fraction at point 1, we are having complete liquid. Yahan pe we are having complete liquid. There will be no traces of vapor. We will be having saturated liquid. That means mass of vapor is 0. So the dryness fraction will be 0 at this point. The dryness fraction will be 0 at this point. Sir, at this point, fourth point, we will be having, you can say, complete vapor, saturated, dry and saturated vapor. You can see this, we will be having dry and saturated vapor. That means mass of liquid will be 0, and that's why dryness fraction will be 1. dryness fraction will be 1, but in between, as you are moving from this 1 to 3 point, at point 2, your liquid will be more than the vapor. At point 2 liquid will be more than vapor, and at point 3 your liquid will be less than vapor. So the dryness fraction at point 2, that is x2, will be less than the dryness fraction at point 3 x3. I hope this is clear. X2 will be less than x3. Is this clear, everyone? X2 will be less than x3. Is this clear? Okay, now one by one, final formulas. One by one, the final formulas. Last topic of the day. Two topics are left over. We will discuss this very beautifully in the special classes. Specific enthalpy. Now we'll go very slowly. Okay, specific enthalpy. For point 1, look at this curve. At point 1, हमारे पास है, we are having saturated liquid. So enthalpy will be directly taken from the steam table corresponding to pressure, which will be called HF. For the saturated liquid at point 1, we will directly take the enthalpy HF at corresponding pressure. Okay, sir. At point 2, what is point 2, sir? Saturated vapor. So enthalpy at point 2 will be directly taken from the steam table at a corresponding pressure, that is your Hg. Is this clear? Hg at the corresponding pressure. Sir, point 3 in the subcooled region. This is point 3 over here. Now understand this beautifully. Understand this. Sir, enthalpy change from process 1 to 3. We want to calculate the enthalpy change. Enthalpy change is given by C delta T. Liquid hai, CPCB mat bolna. I had already told you. So this can be written as H3 minus H1 is equals to C T3 minus T1. Yes or no? For you can say change from 1 to 3. H3 will be equals to H1 plus C T3 minus T1. So H1 क्या है? Sir, HF plus C. T3 is the actual temperature. This is T3. This is T3 and this is T1. That is the saturation temperature. So बच्चा enthalpy change is given by HF minus T, HF minus C, T saturation minus T actual. H3 in the subcooled region, it is given by HF minus C, T saturation minus T actual, and this is nothing but the degree of subcooling. So HF minus C delta T, this is called the degree of subcool. Is this clear? So enthalpy change in the subcooled region is nothing but HF minus C delta T. HF minus C delta T. Are you clear with this, bacha? HF minus C delta T. Boliye. Are you clear with this? Tell me. Similarly, in the superheated region, H4 will be given by Hg plus Cp delta T. That will be your degree of superheat. H4 will be equals to Hg plus Cp delta T. That will be degree of superheat. Okay, sir. Enthalpy change clear. Sir, entropy change for state 1, S1 will be equals to SF. S2 will be equals to Sg directly from the steam table. Sir, for state 3, here the problem will be you will have to apply the formula of entropy change for the solids and liquid. I have given you this formula. C ln T3 by T1. So S3 will be S1 minus C ln T saturation upon T actual. I hope you are clear with the formula. S3 will be equals to S1 minus C ln T saturation upon T actual. Is this clear? Is this clear, bacha? Tell me. Clear. Okay, sir. Similarly, in the superheated region, this will be Sg plus. Now, how to remember this? Sir, in the subcooled region, this will be Sf minus C. This will be S1 minus Sf minus C ln, which is bigger, sir, T saturation upon T actual. T saturation upon T actual. But when you go in the superheated region, this will be Sg plus. Obviously the entropy will increase, temperature increase, entropy increase, temperature decrease, entropy decrease. So this will be Sg minus T actual upon T saturation. Always high temperature upon low temperature, and take the temperature in Kelvin. In wet region, very easy to remember. Vf plus x Vfg, Uf plus x Ufg, Hf plus x Hfg, and Sf plus x Hfg. Is this clear? So with this we are stopping up over here. I hope you would have enjoyable session. Today. So with this, at the end we will be having some announcements for you. I hope you are aware about the All India mock test for GATE 22. How many of you are aware about this? Every Sunday we are having this January 2 to January 30, where the questions are curated by top educators that covers your entire syllabus. Experience the actual exam like setting, get your All India rank, and identify the areas of improvement with the detailed video solutions after the All India mock test. So you can scan this QR code and enroll for this through the link in description using my code SHAILESH VLive. Unacademy Combat, crack GATE with Combat. You can enroll for this using my code SHAILESH VLive and get a chance to win Samsung tab, JBL speaker, Amazon vouchers, and many more things. So these are the things for you. Offer alert. Now you can go for the plus subscription with 12 plus 2 months. You can go on the 12-month subscription. You will be getting 2 months extra. These are the different batches for your respective branches. You can enroll for plus using my code SHAILESH VLive. Thank you very much, bachcha log, for the support that you provided me till the end. Bachcha log, hydraulics marathon is also next. Next marathon is marathon on hydraulics. How many of you are excited for that? Not on 14th. I will have to change the date. On 14th, I am not available. So it will be on 16th or 17th. Hydraulics marathon. Evolve batch also. In Ascent batch also, Abhishek sir is starting. Strength of material now. End game guidance for GATE and ESE 21 interview. Just see the interview panel. You can enroll for this. SM Azad sir, our very own Mondal sir, and Kulkarni sir, Sudhakar Rao sir. So these are special class times, sir. 10 p.m. we will be meeting tonight for maths. I'll be publishing that class just now and I'll update you with the link. So I hope you will enjoy this session. Don't forget to like the video. Share it with your friends. You can search me on Unacademy special app. Unacademy special classes, SHAILESH VAIDYA. You can search me by my name. You will find me, and you can come on the special classes and plus using my code SHAILESH VLive. So for now, this is SHAILESH VAIDYA signing off. Like the video, share it with your friends. Subscribe the Unacademy Accord YouTube channel. Jai Hind, Jai Bharat, and Vande Matram. Bye everyone. And now it's time to take rest.